Discrete mathematics is important for IT, machine learning, search engines, databases and algorithms, encryption, and more. This course is an introduction to this group of mathematical sciences, and it focuses on the most important topics related to discrete mathematics: combinatorics, number theory, prime numbers. You'll also learn about the pigeonhole principle, the stars and bars principle, Stirling's number, and the Chinese remainder theorem. Carl Kurik developed this course.
Welcome to the course on discrete mathematics. In this course, we will cover only a portion of this field, or rather this collection of mathematical fields, because discrete mathematics as a whole is simply too vast. On the beginning, let's say, what is discrete mathematics? It is a field, or as mentioned, even a collection of fields, that focuses on the study of structures and objects that can be counted, meaning those that are equinumerous with the set of natural numbers. In the other words, 1, 2, 3, 4, 5 objects, we can count them, right? Even if there are infinitely many. So, we are concerned with things we can count, like the number of swimming pools, not with continuously varying quantities like the amount of water in each pool as it fills up, which could be any positive real number. So we study structures that are countable, either finite, where we can simply give the number of elements, or infinite, but still countable in the sense of having a one-to-one correspondence with the natural numbers. Natural numbers are just the start. Integers and even rational numbers are also countable, and in fact there are just as many rational numbers as there are natural numbers. We will explore that idea later. And this is exactly where discrete mathematics comes in, focusing solely on the stepwise structures. Take for example a sequence of events like rolling a die. You have the first roll, second roll, third roll, fourth roll, and so on. There's no such thing as a 5 roll or a square root of 2 roll. We don't even consider half a roll. No fractional steps here, right? So we can count those rolls. As I said earlier, discrete mathematics is essentially a collection of branches of mathematics or a subset of other mathematical fields branches, because some areas of mathematics deals with both countable and uncountable structures. Discrete mathematics focuses exclusively on the countable ones. Here are just a few examples of fields that fall under discrete mathematics: graph theory, number theory, mathematical logic, linear programming. Note here, despite the name, this is not directly related to computer programming. Linear programming is a branch of mathematics that studies optimization problems involving linear equations and inequalities. So no, it's not connected with programming. Cryptography, combinatorics. In this course, we will focus primarily on combinatorics and selected topics of number theory. We'll mention maybe some other fields as well. Let's illustrate this even more with some real-world examples. Imagine planning a trip to the city. You have several cities to visit, and each route has a cost. Cost in terms of time, money, or fuel. You want to optimize your route. The number of cities is usually finite and often quite small, right? And discrete mathematics provides the tools to analyze such problems. Or think of digital photos on your phone or in the cloud. A photo is just a collection of pixels, and each pixel has a specific color from a limited set. Discrete mathematics helps us model such data, compress it, and analyze its structure, store it in various formats, convert it between formats. All of this involves massive amounts of data, and discrete mathematics plays a key role in making it manageable. Of course, this also applies to processing audio, videos, texts, and other structured data, which are typically finite and discrete in nature. Another important example is cryptography. Encrypted messages often rely on prime numbers, and discrete mathematics is fundamental here, both in finding large primes and in designing encryption algorithms that keep our data secure, protect it as it is written from unauthorized access. So the applications of discrete mathematics are everywhere, from data encryption through network design, all the way even to artificial intelligence. To understand, to summarize, discrete mathematics is the study of step-by-step processes and countable structures. It includes not only combinatorics and number theory, which will be our main focus here, but also graph theory, cryptography, logic algorithms, and more. Thanks to these tools, we can model, analyze, and solve real-world problems, which is exactly what we will try to do throughout this course. Let's get started. Welcome. Our first topic in discrete mathematics will be permutations. There are two main ways to understand permutations. They are quite similar. First, a permutation can be seen as any rearrangement of the elements of a set. For example, if you have the set AB, then AB and BA are two different permutations. Both include the same elements, just in a different order. Alternatively, we can think of a permutation as a function, or more precisely, a mapping. We won't go into the formalities here, that performs this rearrangement. Now, in the first interpretation, if we take the set 1, 2, 3, then its permutations are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So there are 6 in total permutations. This means that in a permutation, no elements can be lost. If something is present in the original set, it must also appear in the result. In the second interpretation, we think of a permutation as a function that, for a set like ABC, returns a new arrangement, say ACB, swapping the second and third elements. Second goes to third B, and third goes to second C. So in this sense, when we say permutation, we might actually be referring to a permuting function. For example, one that transforms 1, 2, 3 into 1, 3, 2 by swapping 2 and 3. Yeah, this is what function does, swapping those two elements. Such a function is commonly written in Cauchy's two-line notation, where we indicate that first element goes to first, second element goes to third one, and third one goes to second. Or first maps to first, second maps to third, third maps to second. You will notice something interesting here. If we apply this permutation twice, we start with 1, 2, 3, then get 1, 3, 2, and then applying the same swap again, second and third element, we return to the original arrangement, 1, 2, 3. We'll talk about this soon. It's an example of a cycle. Now if, as in our case, the elements of the set X are numbers, here 1, 2, 3, we can write the mapping more simply. 1 maps to 1, 2 maps to 3, 3 maps to 2. Sometimes this kind of notation is also used even when the set elements aren't numbers. In that case, we treat the numbers as indices, as indexes. Quite simple idea, right? Yes, they are simple. Even though permutations are a relatively simple concept, they do have real applications and are used to solve interesting problems. One of them, which we'll implement, is an algorithm that generates all possible permutations of a given set. Password cracking. If a password is rearrangement of known characters, and an attacker may try all permutations to guess it. A brute force approach directly tied to combinatorics. This is why a longer password is safer. The traveling salesman problem. This classic problem involves finding the shortest possible route that visits a list of cities and returns to the starting point. And it's all about evaluating permutations of cities. Imagine you have 7 cities, and traveling from city A to B has a certain cost, from B to C has another cost, and so on. Every connection between the cities has some associated cost. The goal is to visit all 7 cities while paying as little as possible, for example in terms of fuel or money spent on travel. The cost can be, this paying thing can be, for example, time. Encryption algorithms like DES. Some encryption methods like DES, data encryption system, rely on specific permutations of bits or bytes as part of the process to obscure data. It is a relatively old encryption algorithm, but it's had many successors that continue to use permutation as part of the encoding process. This is a math problem. An interesting math problem is counting the number of possible K cycles in permutations of n elements. And that leads to interesting counting problems. To move forward, we first need to understand a few important things. The first one being, what exactly is a cycle in a permutation? A cycle is any permutation of the form, similar to this. So, a cycle is a permutation where the elements return to their original positions after a certain number of steps. Here, 1 maps to 3, and 3 maps to 1. After applying the permutation twice, the elements go back to where they started. 1 will be 1 and 3 will be 3. Similarly, 2 maps to 4, 4 maps to 5, 5 to 2. We can see that here that this permutation consists of 2 disjoint cycles. One cycle has length 2 and the other has length 3. We can write this permutation in cycle notation. So here 1 goes to 3, 3 goes to 1. Here 2 goes to 4, 4 to 5, and 5 back to 2. And we can convert between this cycle form and the two-line Cauchy notation. Both describe the same permutation, the same cycles. Every permutation consists of at least one cycle. Sometimes the entire permutation is a single long cycle, such as 1 maps to 2, 2 maps to 3, 3 to 4, 4 to 5, 5 to 1. Right, then the whole permutation is a cycle. In other cases, we might have a fixed point permutation, meaning nothing changes. 1 maps to 1, 2 maps to 2, 3 to 3, 4 to 4, 5 to 5. In that case, we technically have 5 one-element cycles. As we said, a permutation with no smaller cycles, that is one that moves all elements in a single closed loop, is itself a single cycle. The second topic is a permutation of a multiset. Note here for non-English students like myself. In other languages, it is often a permutation with repetition. But in English, permutation with repetition is something different. Okay, so up until now, we've worked with elements like 1, 2, 3, 4, 5, no repetitions. But if elements can repeat, like in a list 1, 2, 2, 3, 4, we are dealing with permutation of a multiset. For example, in a word barbarian, many rearrangements will produce the exact same word barbarian, like swapping the first B in barbarian with the second B on fourth place results the same rearrangement. The result still reads barbarian, so they are not unique permutations. What we were working so far, permutations with no repeat elements, they are regular permutations, or we call them permutations of a set, not a multiset, or simply permutations without repetition. Now the key question is, how many permutations are there? We saw earlier that for 3-element set X, ABC, there are exactly 6 permutations. So for a setup of n distinct elements, the number of permutations is n factorial. This reads factorial, where factorial means multiply, compute product of all numbers from 1 to the given 1. If n equals 1, it is just 1. If n equals 2, then 1 times 2 is 2. If n equals 3, then it is 1 times 2 times 3, so 6. So for permutations of a multiset, like in a word barbarian, the formula for counting unique permutations is n factorial divided by n1 factorial times n2 factorial times nk factorial, where n1, n2, and k are the frequencies of each repeated element, and k is the number of distinct elements. So for the word barbarian, B appears 2 times, the letter A appears 3 times, R appears 2 times. We'll see that in a moment. Let's look at some examples. Example is the word disk. The word disk has no repeated letters, so the number of permutations is 24. 1 times 2 times 3 times 4. And here we've listed all 24 possible arrangements. Of course, most of them are not words, in a sense that they have no meanings, but they are still arrangements, right? On the other hand, for the word papaya, where P appears 2 times, A appears 3 times, we have 60 possible arrangements. Because 6 factorials is 1 times 2 times 3 times 4 times 5 times 6, which is 720. 2 factorial is 2, 3 factorial is 6, 2 times 6 is 12, and 720 divided by 12 is 60. So 60 ways. And we have all of them here. And there are 15,120 rearrangements of the word barbarian. We won't list them all here, at least not now, but we could write a program to do that later. But we can compute. Why 15,120? So letters are 1, 2, 3, 4, 5, 6, 7, 8, 9 in total. So in numerator we have 9 factorial. 9 factorial. Divided by, in the denominator we have b and b is twice, so 2 factorial. A appears 3 times, 3 factorial. R appears twice, so 2 factorial. I and n appears once, 1 factorial, 1 factorial. We don't need to put 1 factorials, but when we put all those numbers, 2 plus 3 plus 2 plus 1 plus 1 should be 9, and so it is. Then we know that we have checked all the objects. 9 factorial, we try to compute this. 1, 2 times 2 times 3, 4 here, 5, 6, 7, 8, 9. 2 factorial, 3 factorial, 2 factorial, and that's it. 1 factorial is 1, yeah, and multiplying by 1 changes nothing. 1 times 2 times 3 cancels out. 1 times 2 is 4, so this cancels out, and this is 5 times 6 times 7 times 8 times 9. It's always an integer. Factorials are all integers. So it equals 5 times 6 times 7 times 8 times 9. Multiplication is commutative, so we can multiply in any order we like. I, for instance, want to multiply 5 with 6 and 7. So it is 30 times 7, 210. 8 times 9 is 72. And it equals, we can check it, 72, all without 0. 72 times 21 is 72. 4, 14. It is 2. 1, 1 more, 5, 1. So it is 1, 5, 1, 2, and 0. So yes, there are 15,120 ways to rearrange the letters of barbarian without creating duplicate results. Okay, in the next lesson, we will try implementing something related to permutations in code. See you there. Welcome. To work with permutations in Python, all we need to do is import permutations from the itertools module. So we write from itertools, import permutations. And that's basically it. We are ready to start using permutations, but if we simply call permutations like print permutations, for example, using word disk, where all the letters are different, and we run it, we'll see that we got itertools.permutations object at some place in memory. what we actually get is an iterator, meaning we can iterate over it to retrieve the elements one by one. Let me mention right away, we won't be using any advanced Python features in this course. So even if you are more familiar with a different programming language, you should be able to follow along just fine. So we have an iterator, but we don't yet see the actual elements. If we want to get the permutation as a list, we need to convert it to a list. We need to convert this permutation iterator to list. And we run it. Here, yes, we have disk, dix, DSIC, and so on. It should be 24, but it's not the perfect way of displaying it. There are tuples of characters, not full strings, right? So let's join the characters in each tuple to form proper strings. We can do this using a list comprehension. So we can put a list here. Dot join. Not this, but x for x in. Okay, so x will be every of those tuples, and we will join it to one simple string. You can see it, and we have it. We can assign it to a variable, let's say diskperm or diskpairs. We can print them and print the length of the list diskpairs. And it should be 24, right? 24. Next, we can do the same thing with the word barbarian. So we change here to barbarian, run it, and there are 362,000 permutations. Notice that some characters repeat, and as a result, we get many times the same word. Here, N-A-I-B-A-A-B-R-R, it's the same here, right? We got many times barbarian. It shouldn't be disk pairs, maybe we call it pairs, because it is not disk right now. If you want only the unique permutations, we need to convert the list to a set. We can do it by putting set here, or just using set comprehension, the same way as list comprehension. And then we should get our 15,120 permutations. A quick warning here, the number of permutations grows very fast as the length of the input increases. This is because the factorial function grows very quickly. You can import factorial from the math module, from math import factorial, and let's see, print factorial of 9. It is our 362,000, as we had for barbarian when it was list comprehension, when we had duplications. And when we do, I put a Ctrl-D to repeat the line. When we put 12 instead of 9, we'll see that there is 479 million permutations. So the result is enormous, and generating all those permutations would take a very long time. For example, if we try to generate all permutations of A, B, C, D, E, F, G, J, I, J, if I'm reading it correctly, 8, 9, 10, it will take some time. Now we can see it. When we add another letter, it can take a lot of time. Maybe it will not finish it during our life. No, maybe it is, but it will take a lot of time. Okay, we can stop it. So if you only want to know how many permutations there are, not generate all of them, it's better to compute the count using the factorial function instead of generating all permutations and converting them to a list or the set, what takes a lot of time. And if you want to count the number of permutations with repeated elements, like for Barbarian, we should write a custom function for that. Let's go ahead and create such a function. We can call it how many permutations. We'll pass an input, for example, the string. It can be any iterable collection, but for us it will be string. And it will return an integer. Now, the first thing we need to do is figure out how many times each element appears, right? How do we do that? The easiest way in Python, maybe pass here, is to use default dict structure from collection module. From collections, import default dict. With default dict, we don't need to check manually whether the key already exists or not. Maybe let's see that. Normally, we would like to do something like that. We have Barbarian. So we go with B. We assign that B occurred the first time, the same with A, the same with R, but now with B, it occurred previously, so now we only increment the value, add 1, yeah? So it is twice now. Let's program both versions. So normally, we create a regular dictionary called letters. And now for each letter in text, if this letter was already in the dictionary in letters, if letter in letters, then we add 1 because it occurred again. But in other case, we need to assign 1 because it is not in our dictionary yet. Okay? Now to calculate the number of permutations. Permutations of a multiset where elements repeat. We compute numerator, it equals simply to n factorial. Numerator factorial of n. Regardless of that, if it is a permutation with or without repeated elements. N is the length of text, so length of text. Now, when it comes to denominator, you remember from the presentation, right? It's the product of the factorials of the counts of each repeated element. If we are dealing with permutations without repetitions, like disk, it is 1 times 1 times 1 times 1. So we are just multiplying several copies of 1 factorial. The product is still just 1. This means that the denominator doesn't actually change the result. So it will work for permutations of set or multiset as well, for both of them. Okay, the denominator is not this. Well, it's actually not going to be that simple. We first need to calculate the factorial of the number of occurrences of each element. So, for the letter in letters, we need to compute factorial of how many times it appears in text. Factorial of letters of this letter. This is one way. Or we can add here count, go by letters.items and use count here. We don't really use letters, so even we can go by values. Okay, and those are just factors. Now the denominator is product of all those factors. So on the beginning it is 1. For factor in factors, we multiply the denominator. Denominator multiplied by current factor. Now we have the denominator. Finally, we return the value of numerator divided by denominator. We can check if this code works. So we know this. Maybe we can comment this out. It should be 15,120. So instead of doing that, or after doing that, we can call how many permutations in the word barbarian. And it is 15,120. And now if we try it with a much longer word, so comment this out with like electrocardiographic, graphic. When we call the old version, it will never finish. Yeah, it will take a lot of time. But if we comment this out, but run this function for electrocardiographic, we'll see that there is this number of permutations of those letters. We know it without having to generate them because that would take far too long. So, as I mentioned earlier, this code replace, we can greatly simplify or shorten this code using default dict. Instead of checking if the letter was in dictionary and adding one or assigning one, we can use default dict with integer. And this means that for every new letter, there is already assigned 0. 0 is assigned for any new key. So we just add for letter in text, add 1. If it is in dictionary, it will be incrementing. If it is not, then it is 0, so we'll increment it to 1 as well. And it should give us the same result. We can remember 422,378. And now we have the same amount. You can see how quick the program is. We can check also if it is working for permutations without repetition. So for the disk, it should be 24, right? So now we have a function to count how many permutations exist, both for set and multiset. And we also know how to generate permutations using built-in tools like permutations function from itertools. In the next lesson, we'll look at how to build such a permutation generator ourselves, like this function permutations. So we will explore algorithm, one of the many algorithms for generating all permutations. See you there. Hello, as I said, there are many algorithms to generate all possible permutations. One of the simplest is Heap's algorithm, which allows you to generate all possible permutations in such a way that each time, maybe we can see it. I will zoom it. Okay. Each time only 2 elements swap with each other. So here we have A, B, C, D. After the first swapping 2 elements, A and B, we have D, A, C, D. C, D stays, remains where it is. Then during the second swap, B swaps with C, and so on, up to B, C, D, A. Always only once, only pair swaps. And that's it. We know that it doesn't go from A, B, C, D to D, C, B, A, but just guarantees us that the only 2 elements will change each step, right? Because normally if we were doing this, where we would like to have A, B, C, D, then A, B, D, C, the next element normally is A, C, B, D. But here we have 3 changes, B to C, D to B, and C to D, right? Whereas here we swap only 2 elements each time. Let's go back. Close this. 100%. And we can see that this algorithm is incredibly simple. Here it is presented in a different way. K is actually the number of elements. So in Python, we can always count it using len. We have a list of elements. K is a number of elements on the beginning because we have recursion here. So initially it is the number of elements. If you don't know what recursion is, it is the calling of a function by itself. So permutations call permutations with normally other arguments. We'll talk about recursion more in future. So we have a recursion call for the same set, but k1 smaller. Now, for I from 0 to k minus 1, if k is even, we swap the current element with the last one, last in the sense of k. And if it is odd, we swap the first element with the last. And again, we have a recursive call. We will write a little more Pythonic code. So we can make heap permutations function. The heap permutations. We have two inputs, data and length, or we just put it as k, like in Wikipedia, because it's not necessarily the length of the whole array, just the length of the whole array at the first time. Now, if k is 1, we can see it. If k is 1, we just write the array. If k is 1, as we have seen, we print data as it is. Otherwise, so return here. Otherwise, for every I from 0 to k, for I in 0 to k, we could write it like this. Of course, we can write simply k because range has a default range k, default value of 0. We perform the operation recursively, heap permutations data k minus 1, as remember. Now, if k is even, then we perform, as we have seen, swapping the given element with the last. So if k modulo 2 is 0, this is even, data I, data k minus 1, we swap this data k minus 1 with data I. Else, in situation k is odd, we swap first element with the last one. Data of 0, data k minus 1, data k minus 1, data 0. And that's it. You can see that we have one recursive call. Here there was 2, but it was with k minus 1, so I moved it after for loop and merged with that. We can see it. Elements equals 1, 2, 3. And heap permutations, elements, and len of elements initially. Okay, let's see that. For the 3 elements, we have 6 permutations. 1, 2, 3. Then we are swapping 1 with 2. Only one swap. The same 3 with 2. 1 remains, and so on. We can see the same with 1, 2, 3, 4, 5. It should be 120 of them. You can add information which one it is. But we can see that again we swap 1 with 3, but 5, 4, 2 here stays where it was. To illustrate this even more, I wrote such a program, quite simple one. It is permutations of colored balls, where we can see permutating elements. For example, we can start animation for half a second with 3 balls, and we can animate this. So we see how they changed, and we can do like it was much faster, because half a second for 5 elements, it is 1 minute. So now it should be less than half a minute, and we can see how it looks like. Of course, you can improve the code to see, for example, 3 rows, the last 3 rows, to see even more that only 2 are swapping. But yeah, we cannot see all 120, especially if it is small. Of course, we can write a program that every of these permutations is saved as an image, and then merge this image to see something like it was on Wikipedia. Okay, this lesson is all over. I invite you to the next ones. Hello, now when we know many aspects of permutations, let's learn about different type of permutations. A K-permutation, sometimes R-permutation, of a set, also partial permutation sequence without repetition or variation, is an ordered arrangement of K distinct elements selected from the set. So, for example, for our set X, 1, 2, 3, those are K-permutations. We can say that there are 3 one-element K-permutations, 1, 2, 3, just like that. 6 two-element K-permutations, 1, 2, 1, 3, and so on. And 6 three-element K-permutations, which are, in fact, permutations, right? So yes, the normal permutation is a special case of K-permutation where K equals N. And we have other type, a K-tuple of a set, also known as permutation with repetition, sequence with repetition, or variation with repetition, is an ordered arrangement where each element can be selected multiple times. So in fact, it is not permutation, but it is often called that way. So for the set X, 1, 2, 3, some examples of K-tuples are 1, 1, 1, 2, 3, 3, 2, 1, or 3, 3, 2. There are 3 one-element K-tuples, 1, 2, 3, the same as for K-permutations, 9 two-element K-tuples, 27 three-element K-tuples. In fact, there can be 4-element K-tuples, 5-element K-tuples for 3 elements, because elements can repeat, right? So K-permutations, K can be up to N, from 1 to N, but for K-tuples, there is no upper bound. And again, we can say how many permutations there are. The number of K-permutations of n element set, so without repetition, is given by this formula, n factorial divided by n minus k factorial, or the other form of the same formula. So we start with n minus k plus 1 times plus 1 plus 1 plus 1 up to n. The number of K-tuples, now with repetition, from an element set is given by the formula n to the power of k. So we have an example how many 3-element sequences can be formed from a set of 7 elements, without repetition and with repetition. We have these formulas. Alternative version of this example, of this exercise, could be how many 3-letter words can be formed using only the letters A to G, right? Because we have 7 elements, so A, B, C, D, E, F, and G, and we are considering how many sequences we can form without repetitions, like A, B, C, like A, B, D, and so on. So this is P, N is 7, K is 3, 7 factorial divided by 7 minus 3 factorial. It is 7 factorial divided by 4 factorial. shorthand here, you add 1 to the denominator, it is 5, and times 6 up to this number. So it is 210. There are 210 sequences like that. And when elements can repeat, like ABC again, but also ABB, AAA, and so on, we have T73, and it is just 7 to the power of 3. So it is 49 times 7, it is 50 times 7, 350 without 7, so it is 343. Okay, so those are two, let's say, new types of permutations, but in fact we will not use them too much, because in the next video we will learn much better way to analyze exercises like that and to compute the results. See you there. Hello. Right after K-Permutations and K-Tuples, we move on to the topic of the rule of product, which is a broader concept than the two previously mentioned, but also easier to remember. By the rule of product, also multiplication principle, we call this theorem that claims if a process consists of n steps and there are A1 options or choices for the first step in the process, A2 options, choices in the second step of the process, and so on, then the number of possible outcomes of possible possibilities is A1 times A2 times AN. Important note here, the number of options available at each step can't depend on the choices made in the previous steps. So if we have 10 choices at the second step, it must be 10 choices regardless of which of the A1 options is chosen. Example. A man getting ready to leave his house can choose from 5 pairs of pants, 8 shirts, and 3 pairs of shoes. In how many different ways can he get dressed for going out? By the rule of the product, number of ways is 5 times 8 times 3, which is 120. And that's it. That's the number of ways, yeah? So in each step, he can choose, let's say, constant number of clothes. I mean, he's not a woman, so after choosing pants, he still has 8 shirts. Here does not apply situation when specific pair of pants is not compatible with one shirt, right? More complicated example. Many years ago in the United States and Canada, there was a telephone number format known as 2 letters, 5 numbers. So the numbers were created by choosing 2 letters from uppercase alphabet and then 5 digits, in fact. Here is 5 numbers, that was the name, but there was 5 digits, right? So an example is PL12345, which meant dialing 12345 through the telephone exchange center plaza. That's why PL, not from Poland. So the first 2 letters usually referred to the name of the local telephone exchange. And again, how many different subscribers could there have been at most during that time? Not so many. So the first letter could be any of the 26 letters of the English alphabet, from A to Z. Regardless of the first choice, the second letter could also be any of those 26 letters. Then there were 5 digits, any digit from 0 to 9. So we can use a rule of product to compute that in total there were 67,600,000 possibilities. So the standard couldn't last up to this date, but back then was reasonable. The rule of product is a more general concept than underlies permutations, including K-Permutations and K-Tuples, and we can see it. So the rule of product as a permutations. When we have 7 floors, including the ground floor, and 6 people that enter the elevator, and they want, we don't know for what purpose, maybe they need to investigate something, but they won't get off on a different floor, then how many different ways they have. So on the first floor can get out anyone from those 6 people. On the second floor, any one of 5 remaining, and so on and so on. You can also think that first person has 6 choices, then the next person has 5 choices, and so on. So the total number of possibilities is 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial, 720 ways. It is just a permutations, right? Because there are 6 people, 6 floors to get off. They are on the ground floor, right? So we just need to permutate them all. Now the rule of product as a K-permutations. The same situation, 7 floors but only 3 people, and they also want to get off on a different floor. So the first person has 6 choices, the next person has 5 choices, and the next person has 4 choices, 4 floors to choose. So in total it's 6 times 5 times 4, which is 120, and it is exactly the formula for K-permutations, right? 6 factorial divided by 6 minus 3 factorial, which is 3 factorial. And we didn't need to understand it or remember that it is K-permutations. We just multiply. And again, the rule of product as a K-tuples. Now we have the same amount of floors, 5 people, but they can go whenever they want. Of course, when they are on ground floor, they don't want to go to ground floor. So the first person has 6 choices, 6 floors to choose. The second person has again 6 floors to choose, and so on and so on. Each of the 5 people have 6 choices. So firstly 6 choice, second 6 choice, third 6 choice, and so on, 6 to the power of 5, which is 7,776. And it is exactly as how many there are 5 tuples with repetitions of the 6-element set, or how many there are 5-letter words consisting each solely of the letters A, B, C, D, E, F, but they can repeat. So the rule of product replaces everything we know so far: permutations, K-permutations, and K-tuples. We don't need to use them anymore. So the rule of product says that if the first bag or set contains n1 objects, the second bag contains n2 objects, and so on, the kth bag contains nk objects, then if we randomly select one object from each bag, the total number of different possible outcomes, final states after all selection, is multiplication of how many objects there are in each bag. Again, remember that choosing one from one bag does not change the number of elements in the second bag, right? And the last information. The role of product is closely related to the logical connector AND. When you hear AND, you can read it as multiply. So in the first example, 1 of 5 pairs of pants and 1 of 8 shirts, it means 5 times 8. And 1 of 3 pairs of shoes times 3. Each occurrence of the word AND corresponds to a multiplication operation. So it is extremely easy. Every time we are considering how many ways there are and we can build a sentence only with AND as a connection, then it is a rule of product and we just need to multiply possibilities. Okay, let's see some more difficult examples. See you in the next lesson. Hello, now when we know the rule of product, we can solve many combinatorial problems. I've chosen 5. Let's do them all. Exercise 1. How many 5-digit odd natural numbers are there that contain only the digits 0, 1, 2, 3 in the decimal representation? So we have 5 places. Places, I mean digits here. There is a constraint that the numbers should be odd. So the last one can be only 1 or 3. So there are 2 options. So as you can see, I will put the number of options above the lines, and options, if I put options, I will put them below the line. Now let's go from the left to right. As the first digit can be 1, 2, or 3. It can't be 0, right? The natural number can't start with 0, so there are 3 possibilities. Now it can be any of those 4 digits, so there is 4, 4, and 4. And this is the way that normally we can solve problems with the rule of product. So the answer is 3 times 4 to the power of 3 times 2, which is, let's count it, 6, 3 times 2, 4 times 4 is 16, times 4 is 64, and it is 6 times 4 is 24, 6 times 6 is 360, so it is 384 plus 20, right? There are 384 numbers like those. 5 ones, 1, 2, 3, 0, 3, and many other that are 5 digits, odd natural numbers only with those 4 digits. Okay? Let's go to exercise 2. How many 4-digit even natural numbers are there in which the decimal notation contains only the digits 2, 4, 7, like 72, 72, and so on? It is similar, but we have 4 digits, so 4 lines, and it is even natural numbers this time, so only 2 numbers, 2 digits can be at the last place, 2 or 4. But on the beginning can be any of 2, 4, 7, 2, 4, 7, and 2, 4, 7 again, right? So we have 3 possibilities, 3 possibilities, 3 possibilities, and when we multiply it, it is 3 to the power of 3 times 2, which is 27 times 2, which is 54. Now exercise 3. Consider all 4-digit codes formed only from the digits 1, 3, 6, 8, with each of these digits occurring exactly once in each code. How many such codes are there? So we have 4 digits, 4 places to put a digit, right? We do not have any information that those codes should be odd or even, so we can start from the beginning. At the beginning, we have 4 digits, right? If we choose one of them, we have 1 less. If we choose 3, we have 1, 6, 8 now, right? Then we have 2 options, and then we have 1 option. For example, if we have chosen 1, we have 6, 8 here, and the same if we have chosen 6, we have only 8 here. So the answer is 4 factorial, which is 24. We didn't need to think that it is a factorial, right? We just computed. Now, 2 different vertices are drawn simultaneously from the vertices of the cube ABCDEFGH. What is the probability that these vertices will be the ends of the diagonal of the cube ABCDEFGH? So let's see the cube. Maybe I am able to draw it. Okay. We have a cube. A, B, C, D, E, F, G, H. We haven't talked about probability yet, but in this course, we'll consider only classic probability. So it means that probability equals to how many options passes our constraints divided by how many options there are. And that's it, okay? So probability is a fraction, how many possibles are good for us, how many possibles there are. Okay. We want to draw simultaneously from the, okay, two different vertices. So we have, in general, we have one of 8 options, and after that we have one of 7 options, which is 56. But we want those vertices to be a diagonal of the cube. So if we choose E and H, it's not the case. A and E, it's not the case because it is a side of this cube, right? It is this line of this cube, not a diagonal. The same with A and F. It is diagonal, but of this side. It is a diagonal of side ABFE, which is a square. Diagonal of A from A is to G, right? This is a diagonal of a cube. The same with B and H, and similar. So on the beginning, we can choose any of those vertices. There are 8 of them, but since we have chosen, for example, H, we have only one possibility, B, to be diagonal of the cube, so only one then. The probability is 8 divided by 56, which is 4 divided 28, which is one of the 7. Okay. Now, the last one, exercise 5. A player rolls a symmetrical 6-sided die twice and calculates the sum of the numbers rolled. Calculate the probability of event A that the sum of the numbers rolled is equal to 4 or 5 or 6. So again, probability is how many possibles are good for us divided by how many possibles there are, and those how many possibles there are is often written as the size of omega, which is the size of a set of all options. But it is on the first die we have 6 options, and on the second die we have also 6 options, which is 36. You can see that I omit those lines. I don't put them anymore because they are not necessary. Yeah? They were only for the beginning to understand the rule of product. Okay, but how many good events there are? We can count them. If the first roll is 1, then on the second roll must be 3, then the sum is 4, or 4 the sum is 5, or 5 the sum is 6. If the first die has 2 points, right? Points of the die. Then on the second die must be 2 points, or 3 points, or 4 points to be sum 4, 5, or 6. If the first die is 1, the number of dots is 3, then on the second die the number of dots must be 1, 2, or 3 to make the sum 4, 5, or 6. Now if the first die is 4, on the second die we have only options 1 or 2. We cannot have sum 4 if there is 4 on one dice. If on the first die we have 5 points, dots, then on the second must be 1, and then we have sum 6. If the first die have 6 points, dots, then there is no option to have the sum 4, 5, or 6, so the set is empty. How many options there are? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 options are good, and there are 36 options. So the probability of the event A, that the sum of the numbers solved is equal to 4 or 5 or 6, is 12 divided by 36, which is one of the three, which is approximately 0.333 and so on, right? So you can see how the rule of product is simple in use, right? Okay, in the next lesson we will check some of those computations programmatically. See you there. Hello, I've run IPython, such an interactive Python shell, and now if you want to count how many there are, completely not optimally, but just how many 5-digit odd numbers that have only the digits 0, 1, 2, 3 in their representation, we can use for loop. So let's say that how many is equal to 0 for now. For I in range between 10,000, we go from 10,000, which is the first possible number, to the last possible number, which is 99,999. Since the interval is open, I add a 1 here, so that 99,000 and so on is also taken into account. Now I make the condition that the number must be odd. That is, the number is not divisible by 2, so the remainder is equal to 1. If I divided by 2, the remainder is equal to 1. Then I change the number into a string. Then the string I change to set. So I have set of digits, right? Set of digits. Okay. And I check whether the set of digits is only 0, 1, 2, 3. What I mean is if those digits are a subset of digits 0, 1, 2, 3. We can see it in a moment, so let's stay. If set of digits is subset of the set, it is string, so I need to put it in apostrophes, 0, 1, 2, or 3, then we want to count it. So how many plus equals 1? Initially we have how many equals to 0. And then we can check how many, and it is 384, which is exactly what we were supposed to get. Why I haven't checked if a set of digits is exactly 0, 1, 2, or 3? Because it would pass only if it is like this number, but it wouldn't pass when it is 5 ones, because 5 ones has only one digit, 1. So we cannot check if set of digits is equal to 1, set of the only element 0, 1, 2, 3, because then this case wouldn't be counted. You can check it, right? Okay, go back. What about the probability exercise? So very similarly, we can also write a program. We can simulate dice throws. Twice throwing the dice and whether our condition will be met. Our condition is when the sum is 4, 5, or 6. And we can see how often we get it right, and this is the same as probability. Okay, this is neither a perfect way to solve this programmatically, nor an optimal way in terms of speed, but it is a very simple way. And in this way we can quite quickly check whether our result makes sense at all. Quickly I mean in terms of writing the code, not code running. For this we will import, so from random import randint, from random library we import randint, randint. Okay, we write down the number of simulations, so let's let it be 1,000,000, so 10 to the power of 6. for each simulation, in range n, for each of them, now we are actually drawing the numbers from 1 to 6. We should also write successes, for example, right? And okay, we are now drawing the numbers. So the number A is rand-end between 1 and 6, and the number B rand-end again 1 to 6. Here both ranges are inclusive in rand-end. So successes initially are equal to 0. And now if A plus B is in set 4, 5, or 6, in 4, 5, or 6, we increase the number of successes by 1. Successes plus equal 1. Okay, we press enter and wait a while. We can check the successes. It is 333,000. Okay. We count the probability P in that way that it is the number of successes, divided by all the number of events, which is n. So the probability is in this way. We can show it without print even. Probability is P, and we can multiply it by 100, see it as a percent with 2 decimal places with rounding. So it is 33.33%. So we computed it correctly. You can see, of course, that if you compute it many times, you can get different answer. Now let's again compute P, and again it is 33.37. To get closer to our correct answer, math correct answer, we can increase the number of events, how many times those dice are rolled. So we can change n to the power of 7, which is 10 millions, and then if we compute it, it will be much more accurate, so it should be 33.33 always. So this is a problem in this way, that we can have a wrong answer if n is quite small. You can see that even here we don't have a good answer, but when we repeat it, we should get 33.33 much often that for the first way, when n was only 10 to the power of 6. It is not accurate yet, yeah? You can change n to 10 to the power of 8, and then it really should be 33.33, but it will compute for some time. I will cut the video here, and you can see that when you increase the number of events, the result is much more accurate. Okay, 15 seconds later, we can compute the successes, and it is 33.33. So the math way is much more precise than this way. Okay, that's it for this lesson. See you in the next one. Hello, related to the rule of product is the second rule, the rule of sum. And this is because the rule of product is insufficient. By the rule of sum, also the addition principle or the addition rule, we call the theorem stating that. This is my definition that is correct but suited for solving problems. If we have to break down the multiplication rule, the rule of product, or any other analysis into separate disjoint cases, The number of possibilities we are interested in is the sum of the number of possibilities in each of these cases. Example 1, which is obvious. In the 3 drawers, we have in turn 5 balls, 4 balls, and 3 balls. First drawer has 5 balls, second drawer has 4 balls, and the last drawer has 3 balls. In how many ways we can choose one ball from among the first 2 drawers? Here is the solution. From the first drawer we choose one of the 5 balls, or from the second drawer we choose one of the 4 balls. In total, 9 ways. This is pretty obvious, intuitive. Anyone on the spot would answer that if we have 5 balls in one place, 4 in another, and someone asks us to give one ball, we can choose one of the 9. But you can already see the rule here. There are separated cases and we add possibilities. And a more serious example too, how many 5-digit even numbers are there with different digits? It may seem that we can solve this with the rule of product, and we will try. A solution attempt, we write down our underlinings, 5 lines. Well, and we can start with the last element, due to the fact that the condition is set there. Parity depends on the last digit, we start from it. We put one of 5 digits there, 0, 2, 4, 6, or 8 at the last place, right? Number must be even, so here must be 0, 2, 4, 6, or 8, right? Given what we know from the rule of product, we would simply insert a 5 there, because one of the 5 digits. And now there is a question. How many digits can we now put in the first place? Here. Well, it would seem that 8. Because we can't put a 0 at the very beginning, and we can't put the 1 that we put at the end, right? So by default, we can put here one of the 9 digits at the very beginning. From 1 to 9, you can't put a 0. If we inserted 2, 4, 6, or 8 here at the very end, we cannot put them at the beginning as well. So 8 possibilities, but yeah, by default, we can insert one of 9 digits there. But if there is a 0 at the end, we still have 9 possibilities. If we put 2, 4, 6, 8, we cannot put 0 and, for example, 2. Here we have 8 possibilities. But if it is 0 here, then we cannot put only 0 here. We can put 1, 2, 3, up to 9. So 9 possibilities. So we don't know whether to insert 8 or 9 here, because it depends on what we inserted here at the end. And we have this conclusion. If, while analyzing a problem, we notice that we cannot solve it using only the multiplication rule, the rule of product, and that a different number must be used in a given step depending on the case, then we consider these cases separately and sum the results. So now let's solve it. We wanted to use the rule of product here. We already know that it is insufficient. The result depends on whether there is a 0 at the end or whether there is a one of these digits at the end. We break down the solution. On the left side, if there is a 0 at the end, if 0 stands at the end, then there is one particular digit, a 0, one particular digit, and if it stands any of these, it means one of the 4 digits, right? One possibility, 0, 4 possibilities, 4 numbers, 2, 4, 6, or 8. Now we go from the left. If a 0 is inserted here, how many possibilities are there? As I said, you can insert any number from 1 to 9. So there are 9 possibilities. If, on the other hand, we inserted a 2, 4, 6, or an 8 here at the end, for example, imagine that we put a 6 here, then you can put digits from 1 to 5, or 7, or 8, or 9 here, so there is 8 possible digits here. That's how much we insert. Now we are considering the second place in both cases. If here is inserted a 0, and here any of the 9 digits, for example 1, here it can be any digit from 2 to 9. There are 8 possible digits. Similarly here, if a digit is inserted here, suppose 2, and here was suppose 5, then there would normally be 10 here, but you can't insert those 2, so there are 8 possibilities, right? 8 here and 8 here. After that, we go as usual. Since all the digits are 10, and we cannot use this digit, this digit, this digit, we can put 7 digits here. And again, there are 10 digits in total. We cannot put one of those that is put here. We cannot put that is on the beginning. We cannot put that one that is on the second place. So we have 7 possibilities and then 6 and 6 here. We have 2 different cases depending on whether there is a 0 at the end or not. And we have to, by the rule of product, calculate separately the first case with 0 and separately the case without 0. The result for the left side that is marked in blue, it is the product of 9 times 8 times 7 times 6. It is normal, the rule of product. For the right side marked in green, it is the product of 8, 8, 7, 6, 4, also by the rule of product. For the first case, we have 3024 possibilities. For the second case, 10,752 possibilities. A total of 13,776 possibilities. That is, there are so many 5-digit even numbers with different digits. We can check the result very quickly in IPython. How many is already typed? And now, like this. For I in range, we go from 10,000 again, 5 digits, to 99999, and we add a 1 because the interval is right open. So we want to take 99999 into account. We want even numbers, so is even is equal to I, the remainder when we divide it by 2 is equal to 0. Yeah, this is a bool value. About different digits now, we convert a number into text and text into set. And we want to check if that set of not repeated elements has length equal 5. 5 different digits equals to if len is of that set is equal to 5. If both cases, both constraints, conditions pass, if it's even and 5 different digits, then we increase the value of how many plus equal 1. Okay, we check how much we got out, how many, and it is 13,776, exactly what was in the presentation. Okay, let's go back to the presentation. Just as the rule of product, multiplication rule, involves the conjunction and, the rule of sum, addition rule, addition principle, involves the conjunction or. Here by or we mean a conjunct that only one of the situations at a given time is true. 0 at the end or another digit at the end. Either we were in this situation or we were in that situation. And we count how many possibilities there are in total, being unaware of which situation will happen. Okay, so if we see or in the text, that's probably where the addition will be. The rules of product and sum have much wider, broader applications and are used, among other things, in combinations. This will be covered in this course in future lessons. Formally, we can write. I found a very interesting definition while preparing this presentation. The definitions from the presentation about the rule of product and that one in this presentation about the rule of sum are correct. Here I will present different equivalent definitions. Rule of product. If a choice involves making k decisions in succession, one after another, where the first can be made in A1 ways, the second in A2 ways, the nth in AN ways, then such a choice can be made in A1 times A2 times A3 times AN ways. We know that. Now the rule of thumb. If a choice involves making one of k decisions, where the first can be made in a1 ways, the second in a2 ways, and so on, the nth in an ways, then such a choice can be made in a1 plus a2 plus an ways. Where is the difference? The difference is here. Decisions in succession on consecutively, sequentially, k decisions. Just like we have 5 underscores and consecutively, sequentially decide. Sequentially does not have to be from left to right, because in our case we used started from the last one, right? We usually should start where there is a condition. For example, that the number must be even or odd, and then from left to right. So here is k decisions in succession, sequence, and here one of k decisions. Like in our example, one of the decisions is that a 0 is at the end, and one of the decisions is that at the end is 2, 4, 6, or 8. And these cases should be finally added up, summed up. These texts, those definitions you can see, are almost identical. It is a specially chosen vocabulary to write down the definition of both rules, just like that, almost identical. Okay, finally I will remind you that in the addition rule, the rule of thumb, decisions must be mutually exclusive. That is, if we have to choose one ball from 2 drawers, like in the first example, we cannot take half from one drawer and other half from the other. Yes? There will be more about situations where these choices are not mutually exclusive in the future. Okay, that's everything here. See you in the next video with more examples. Hello, so we have 3 exercises for the rule of thumb. Let's do them. If you want, you can stop the video now and do them yourself. Then go to the end of this video and see if you have good results. Exercise 1. How many 4-digit numbers are there that are divisible by 5 if the digits can repeat? So we have exercise 1.a, and if there are 4 digits, we have 4 underscores, 1, 2, 3, 4. At the end, if they are divisible by 5, can be 0 or 5, so 2 digits. At the beginning can be 9 digits, because from 1 to 9 there cannot be 0. And here 10 and 10. We put multiplications here. And 9 times 2 is 18. And times 100, it is 1800. And that's all here. Point B. The digits cannot repeat. So, at the end can be 0, the specific digit, and then here can be any of digits from 1 to 9, so 9. Then here cannot be this digit that it is here and this 0, so 8 and 7. Similarly, if at the end is 5, the specific digit, 1 digit, then at the beginning cannot be 0 and 5, so we have 8 possibilities. And here cannot be this digit here and this 5, so 8 again, because 0 can be here, right? Here was excluded, and here it is possible to put 0, and 7 here. I don't put those dots for multiplications anymore. We know that they are there, and I will not put ones in multiplications because it changes nothing. So the result is like this. And we can compute it. You can compute it on calculator or by hand. I will make some fun here. So for example, we have 8 and 7 here and 8 and 7 here. So it is 8 times 7 before the parentheses, then times 9 plus 8. So it is 56 times 17. And to compute that, we can write 56 times 17 is 20 without 3. So 56 times 20, 56 times 2 is 112 and 0 at the end. And 3 is 100, 150 and 18, so minus 168. And that way we can compute that. 20 without 8 is 2. We have 12 here. 112 minus 60 is 50. We have 1000 and minus 100 is 952. Here, by the way, there is an element of a test to see if we have a good result, so such a cursory check, because this result, well, the digits cannot repeat, must be always smaller, so this must be always be greater than the one where digits cannot repeat, right? So when digits can repeat, it's always greater than where they cannot repeat. So here, so that way we can easily check if we probably have a good answer. Okay, exercise 2. Exercise 2. Point A. How many 5-digit numbers are there that are divisible by 25 if the digits can repeat? So when numbers are divisible by 25, when at the end is 0, 0, or 25, or 50, or 75. And because digits can repeat, we could do it that way. At the end can be 0 or 5, so 2 digits. And if it is 0, so just before the 0 can be 0 or 5, so 2 digits. And if it is 5, before 5 there can be 2 or 7, so also 2 digits, and we can put 2, but the writing is clouded here. Why 2? Why not 4? Because we have 4 digits here, right? 2 because those two or those two, not 4 possibilities, right? But let's improve that. Even if it is digits can repeat, situation when digits can repeat, we can always break those cases. So we can put 0 here, the specific digit, and 5 here, the specific digit. If there is 0, we can put 0 or 2, 0 or 5, 0 or 5 here. So 2 possibilities. And if there is 5 at the end, we can put 2 or 7 at this place. So again, 2 possibilities. And now it is clear why 2. Okay, digits can repeat. So here can be 9 digits, and here 10 or 10, 10 or 10. And we just need to compute that. In fact, it is the same number here and here, so we have 9 times 10 times 10 times 2 times 2, because we have twice the same case. This is 1,800, so it is 3,600, the same as amount of seconds in an hour. Okay, point B. The digits cannot repeat. So, again, let's start with 0 at the end. If there is 0 at the end, digits cannot repeat, so 0, 0 can't be the case. So the only case is 50. Again, specific digit not at the end, but the previous place. So we cannot put 0 or 5 here. There is 8 possibilities, and here again, there cannot be 0, 5, and this digit, so 7 and 6. And the second case when there is 5 at the end, the specific digit. So before that, there can be 2 or 7, so 2 possibilities. Then here cannot be 5, let's say 2, and cannot be 0. So we have 7 possibilities. Here cannot be those 3, 0 can be, so 7 and 6. And again, we have quite a nice computation. 7 times 7 times 6 times 2, because 7 times 6 is repeated here and here. So we can compute it that way. 7 times 6 is 56. And in parentheses we have 8 plus 7 times 2 is 14. So it is 56 times 22. And 22 is again times 20 times 2. 56, I said. Sorry, 7. It was when it was 8 times 7. 7 times 6 is not 56. It is, okay. Let's erase it. 7 times 6 is 42, right? Yes, 42. So we need to erase that as well. Okay, 42. And again, 42 times 20, 42 times 2. 42 times 2 is 84, so we have 840 plus 84, which is quite easy. It is 924. And that's all. So you can see the rule of sum here and here. And you can see that even if we use a multiplication rule, the rule of product, you can always split the cases to use a rule of sum instead of rule of product. Yes, of course, in one case we multiply the possibilities. Okay? Exercise 3. In a certain soccer team, there are 3 defenders, 5 midfielders, and 2 forwards. The coach decided to choose 2 players from different positions, for example, for interview, for television. In how many ways can he do it? So, we have soccer area, soccer field, probably. That's the name. Okay. We have place where ball wants to go. Here and here. Let's say we have one team, so here are defenders, D, and D, 3 defenders, 5 midfielders, so they are here, midfielder, 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 and midfielder, and 2 forwards, forward and forward. Okay, so the coach wants to choose 2 of them, but from different positions. So he can choose one defender, and midfielder. This is one case. Fielder. In how many ways can he do that? He can choose one of 3 defenders and so multiplication, one of 5 midfielders, right? So we have 5 here, and 3 times 5 is 15. He can also choose differently defender and forward player. Forward. So then one of 3 defenders times one of 2 forwards. So 6 possibilities if he wants to choose defender and forward. And the last case is that he wants to choose midfielder. We assume that it doesn't matter if he choose defender and midfielder or midfielder defender, right? Because because normally there is no difference in order of choosing people, right? Midfielder and forward. There is the last case. So there are 5 midfielders and 2 forwards. So we have 10 possibilities. And to compute how many possibilities there are, we can see that those are cases that does not repeat. So we can choose, they are disjoint, right? So we can just use the rule of thumb. So the total number of possibilities is 15 plus 6 plus 10 equals 21. Okay, I think you can easily program Python program or other programming language programs that computes those values to check if they are correct. But we can talk how to program this algorithm, this choosing. It's 31, sorry, not 21, 31. Sorry. Okay, how to program a program that computes that, how to do it. Let's see that. So we have how many? 3, 8. We have 10 people, and we can call them that way. People equals defender, 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 midfielder, 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 and forward, forward. As always, we can put how many equals 0. And now we are choosing 2 people for be in range. How many people there are? -1, because we want to choose one of those. And if we choose 1, we choose people from the right? It is obvious, because if we choose a defender, we need to choose midfielder or forward. If we choose midfielder, we only want to choose forward because the case defender and midfielder was already considered. Okay? So, for j in range I plus 1, 2 len of people. And you can see that here we have choices up to here, because at the right of this forward there is nobody, so we step back. For I, the last I can be here, and then j can also be chosen. Okay. That way we'll consider all possibilities. Person 1 is people from I. Person 2 is people j. And in that way we can choose D and D if I is 0 and j is 1. D and M, and FF. Yeah, right? So that's why we have I plus 1. In that way, of course, we can choose D and F, for example, but we are sure that I is not equal j. And now, if person 1 is different from person 2, they are not from the same era, we increase how many plus equals 1. And it should be 31. And that's right. So that's simple program. You can analyze it. Of course, you can write it differently. It's not that hard to do it. Yeah, we saw how rule of product and rule of sum are powerful. It was much easier to compute it mathematically than write a code, and quicker. In the nearest lessons, we will see that rule of product and rule of sum, they are both not sufficient for all cases, and we will cover another rule. See you there. Bye. Hello. Before we jump to the new rule, the new principle, we need to understand two types of notations that we will use in this course. First, the sum notation. The result of addition, called the sum, can arise from the process summation of a large number or even an infinite number of numbers, often following a certain pattern, formula. In such a case, writing the sum explicitly becomes cumbersome. For example, when you have sum like that, so it is sum of squares from 1 to 12, 1 square, 2 square, 3 square, and so on up to 12 square. Instead of the full expression, we can write the sum as 1 plus 4 plus 9 plus 3 dots plus 144. However, if we are dealing with a situation where the last element is unknown, we haven't calculated it yet, like here 12 square is known that it is 144, but 99 square, maybe we don't know, or we don't want to compute it right now. But we know the number of elements to be summed. We can use the following notation: 1 square plus 2 square plus 3 square plus dots plus 192 square. We don't know how much is 192 square, but we want to sum all squares from 1 to 192. And this is nice short notation. However, it is not enough. For example, next we may encounter a sum of such compressed sums. So, sum of all integers from 1 to 100, then sum of squares from 1 to 100, then sum of cubes from 1 to 100. And again, it's going to be cloudy. Where is what? To highlight the separateness of these sums, we can use parentheses. Then it is more obvious what is going to be summed here. However, we may deal with a large number of such parentheses, in which case we write sum of integers, sum of the squares, sum of the cubes, 4 power, 5th power, plus dots up to 102nd power of integers from 1 to 100. You can see that it's going to be hard to read or understand even if we use dot notation. We may also arrive at a situation where these sums are infinite. Infinite should be lowercase here. Though the result may or may not be finite. For example, sum of squares of fractions, right? 1 square plus 1 divided by 2 square plus 1 divided by 3 square, it is 1 divided by 9, plus and so on. The same with third power, the same, up to 102 power. All this leads to the need to shorten, simplify the notation. Even though those parentheses have infinite number of numbers, all those sums are finite here. And it is hard to read this notation, right? So we need to have short and simplify one. And here where sigma notation comes in. The summation notation, sum, sigma, refers to the notation where to the right of the large Greek letter sigma, we write a formula or rule for generating the successive elements to be summed. So on the right hand of sigma, there is a formula. Below the sigma sign, we write the index and information about the starting point of the summation. Mostly it was 1 in our cases. While at the top, we write the number of which we want to stop the summation. In our case was 102, substituting into the index. So notations like those, 1 plus 4 plus 9 and up to 144. The second one plus 4 plus 9 plus dots plus 144, which is shortened. Or with squares without computing exact values, 1 square plus 2 square plus 3 square plus and up to 12 square. As well as those I equal 1 up to 12 I square. And the same, but not below and up, but on the right hand of sigma side, are all equivalent. So to understand that, here we have formula and we put numbers. I equal 1 square, then I equal 2 square, 3 square, 4 square, up to this point with it, with 12 square, And between all those squares, we put plus. And that sigma notation means exactly that. So some cases, this is 1 square, 2 square, 3 square, up to 192 square. So this and this means the same. Here we have a nice situation when we had already a sum of all integers from 1 to 100, sum of all integers from 1 to 100 to the square power, to the cube power. We can write it that way. From I equal 1 to 100, I. From I equal 1 to 100, I square. From I equal 1 to 100, I cube. And this can be even shortened because it is sum, right? If it is sum, we can rearrange elements. So 1 plus 1 square plus 1 cube, 2 plus 2 square plus 2 cube, plus 100 plus 100 to the square power plus 100 to cube power. We can write it that way. So we can write it I plus y, I squared plus I cube from I equals 1 to 100. And this is exactly the same. We can write it that or in rearrange order, it doesn't matter. Here we have I equal 5 up to infinity to I. So when I is 5, 2 times 5 is 10. When I is 6, 2 times 6 is 12, 14, 16, 18, 20, and up to infinity. The same here, I equals 1 to infinity, 1 divided by 3i. So I is 1 is 1 third, I is 2 is 1 divided by 6, I is 3, it is 1 divided by 9, and so on. And now sums can also be nested. You remember that situation? We can add some colors here, and you can see that this is one sum, right? So here we have sigma from I equals 1 to infinity. I am putting it with mouse, so maybe it's not ideal handwriting, but that way. Here we have the same situation, I equal 1 to infinity, but it is 1 divided by I to the power of 3. The same situation, and this is I equal 1 to infinity, 1 divided by I to the power of 102. And those sums, this plus this plus this, the only difference is here, 2, 3, 4, 5 up to 102, and those 2, 3 up to 102 can be written with sigma sign as well. So this is how we write it. First, this is this green part that we already discovered, and here are those powers. So how we compute it? First, we assign I equal 2. So we have j equal 1 up to infinity, 1 by j to the power of 2. And this part. Next, plus, because sigma is plus, and we put I equal 3. J equal 1 to the infinity, 1 divided by j to the power of 3. Plus the same, up to 102. J equal 1 to infinity, 1 by j to the power of 102. And all those sums are those green parts. So instead of writing this, we can write only this thing. Typically, nested sums are not encountered multiple times. So mostly it is nested twice like here. If you want to indicate that we are summing all or certain elements of a given set, we write the membership symbol for the index under the summation sign. Example, we have a set of results from rolling a 6-sided die, First there was 3 dots, then 4 dots, or points, 4 dots, 4 dots, 6, 6, and so on. And if we want to sum all those numbers, we just write the notation sigma for every x from x uppercase set, sum x. And that represents the sum of all elements of the set x. We can write some constraints here, while the notation sum all x from the set x, where 2 divides x, represent the sum of all even elements of the set x. So here it means that we sum 4 plus 4 plus 4 plus 6 plus 6 plus 2 plus 2 plus 2 plus 2 plus 6. This means exactly that. And at the end, let's see some selected properties of the summation. We saw it already when we have the same limits below the sigma sign and above the sigma sign. We can put those two things in the same sigma sign. The same with difference. If we have c times ai, we can put c, which is constant, outside of the summation. For example, if we sum from e equals 2 to 10 to I, which is 4 plus when I is 3, it is 6 plus, and so on up to I is 10, so 20. Instead of that, we can write that it is the same as twice sum from I equal 2 to 10 I, and it is 2, and I is 2 plus 3 plus 4, and so on up to 10. So it is the same. We can always put the constant outside of the sigma sign. And if we have nested sum, where those limits are different, but this part based only on this indicator, and this part bases only on this iterator, we can separate those sums and compute the multiplication, the product of those results. Okay, that's it. Don't worry about those things if you are new to them. We'll not use them heavily. It is the most important thing to understand that when there are sums and there is a formula, we can shorten the writing. We can shorten how we write this sum. Okay, that's all in this lesson. Similar idea to sigma sign set union. Just as the sigma symbol is used for the notation of numerical summation, the union symbol can be used for sets in similar situations. The notation A1 union A2 union A3 union up to A100 can be written in one of the following ways. Limits I from 1 to 100, AI, or I is from 1 to 100, AI. Those are the same. Similarly, infinity notation, A1 union A2 union A3 and so on is written as this we know from sigma sign, I more or equal 1, AI, or just sum as union, right? Union of all sets that are written here. The last notation is incorrect if we do not intend the union of all of the given sets. For example, if you want union only odd sets, A1, A3, A5, we would write I equal 1, or here I more than or equal 1, and that 2 is not dividing I here and here, but we cannot put it here. And just as the sigma symbol is used for the notation of numerical summation, the union symbol can be used for the sets in similar situations. Similarly, for the intersection of sets, there is the set of intersection notation, that is upside down union symbol, and for the multiplication of numbers, we can use the large pi notation. Examples: when we have A1 all numbers from 0 to infinity, all integer numbers. A2, all numbers from 0 to infinity but without 1. A3 without 1 and 2 and so on. Then union of all those sets is the same as A1 because none of those next sets after A1 adds any element to A1. But the intersection is 0 because it is the only number that appears everywhere. We can have another example. For example, A1 is all those, or maybe start with A2. Sorry for that. And we put all divisible by 2, 2, 4, 6, and so on. A3, all divisible by 3, 0, 3, 6, 9, and so on. And A5, for example, all divisible by 5, 0, 5, 10, and so on. So the sum of them will be all those numbers. So 0, the next is 2, the next is 3, the next is 5, not 5, 4. Then is 5, 6, then would be 8, and so on. But there would be no 1 and 7, we know. And, okay, this is close bracket, let's say. And intersection of those AI would be all those numbers that appears in all those sets. So 0, 2 not, 4, 6, 8, 10 no. Probably the next would be 30, I guess. Yeah. 30, 60, 90, and so on. Because 30 is the least common multiplication, right? Okay. So that's what those two notation means. And as with sums, we know what does it mean. I equal 3 up to 8, I squared by 3. It means 3 squared by 3, 4 squared by 3, 5 squared by 3, up to 8 squared by 3, divided by 3, and sum all those numbers. And the same with pi means the same numbers, but not sum, but multiplication of them. Okay, now we are ready for the new principle. See you there. Hello, we return to our rule of sum. The addition rule, as you remember, describes the way of counting the cardinality, the size of the set, of two disjoint sets, specifically the union of two disjoint sets. We had the situation where the coach either chose a certain person from defense, one person from midfield, or one person from defense and one from forward, or one midfielder and one forwarder. This situation could not overlap in any way. They were disjoint. For disjoint sets A and B, we have the size of union of those two sets is equal the sum of their sizes, where this sign, this bracket, this module of set denotes cardinality, the size of the set, finite or infinite, of the set S. More generally, for disjoint sets A1, A2, up to AN, we have size of union of all sets is equal to sum of sizes of individual sets, which reads as the cardinality of the union of sets is equal to the sum of the cardinalities of the sets A1, A2, up to AN. Equivalently, we can write sum with dots. However, this formula does not hold if at least one pair of sets AI, AJ is not disjoint. That means we cannot simply break them into several subcases and add the number obtained in each subcase if those cases can overlap. In the next lesson, we will see many examples when such situations occur. But now we have the inclusion-exclusion principle. The inclusion-exclusion principle allows us to count the number of elements of the union of sets that are not necessarily disjoint, when cases may overlap, repeat. The formula for the two sets, A and B, then it is the size of union A and B where those sets can overlap is equal to size of the A, size of the B, minus the intersection of those two sets. Visually, it looks like this. We have customers who buy both fruits and vegetables. We have certain customers for fruits, maybe 10 of them, certain customers for vegetables, maybe 10 of them as well. This doesn't mean we have 20 customers, because some of them bought both fruits and vegetables. We only know that the number of customers is at most 20, as long as our store only sells fruits and vegetables. We have an example situation. Customers for fruits, someone counted them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 customers for fruits. And another person is tasked with counting customers who bought vegetables. 1, 2, 3, 4, 5, 6, 7. 7 customers for vegetables. They have vegetables in their shopping basket. If we have a third person, a third salesman, clerk, who counts people who bought both fruits and vegetables, who have both in their basket, they will count 4 people. And the total number of customers is the number of fruit customers, the number of vegetable customers, which is 18, minus the customers who bought both fruits and vegetables because they were counted twice. And we have 14 customers. If you only knew that there are 11 customers for fruits and 7 customers for vegetables, no one counted people who bought both, we could only estimate the number of customers. We could only say that the number of customers is at least 11 because 11 people bought fruits, so there must be at least 11 customers, and at most 18 if those groups were disjoint, if no one who bought fruits bought vegetables, and similarly in other way, yeah? Then we could only approximate the number of customers that is between 11 and 18 with those numbers. So if we only counted fruit customers and vegetable customers separately, we could only conclude that thing, that the number of clients is between 11 and 18. From the formula for not disjoint sets immediately follows the inequality that if we don't know if sets are disjoints or not, we know this inequality that the size of union of two sets is less or equal the sum of individual sets, the size of them. If they are disjoint, this is equal. If not, this is less. Such diagrams, like the one we saw a moment ago, are called Venn diagrams. So this part was counted once, this part was counted once, but this purple part was counted twice. So if you want to know the area, let's say the size of A union B, we need to subtract this area once. Yeah, because it was counted twice. So the formula is like we saw. For 3 sets, we have a Venn diagram and the formula. So the sum of those 3 sets is A plus B plus C, but then this part, A and C, was counted twice. We need to subtract it. Then A and B, this part, was counted twice. We need to subtract it. And B and C was counted twice. We need to subtract this. But then when we see this part that belongs to every of those 3 sets, it was counted once in A, once in B, once in 3 times, then subtracted once, subtracted twice, subtracted for the first time. So it was not counted, so we need to add it again. And that's how this formula looks like. So the cardinality formula of the union of two non-disjoint sets A and B is, for 3 sets it is this formula. The cardinality formula for the union of 4 non-disjoint sets A, B, C, D is sum of individual sets, then subtract all pairs, then add all triples, the intersection of 3 sets, then subtract 4 sets, and so on and so on. Add sizes of intersection of 5 sets, subtract 6 sets, add 7 sets, and so on and so on. Right, general principle. Add the cardinality of the individual sets, subtract the cardinality of the intersection of 2 sets, add the cardinality of the intersection of 3 sets, subtract the intersections of 4 sets, add the intersections of 5 sets, subtract, add, and so on. We can write it like that. The general formula for the cardinality measure of the union of a finite number of sets. But in fact, we don't need this. In typical problems, school, university, the inclusion-exclusion principle is used for 2 to 4 sets. For a larger number of sets, computers are used. So, an example of non-disjoint sets. People enrolling in Polish, German, and Spanish courses. Those are 3 sets. By the way, here in gold is the statement that if these sets were disjoint, that is, a person enrolls either in the Polish course or the Spanish course or the German course, only one and exactly one of them, they cannot enroll in both or none, then we simply sum that part and the rest is not needed. But if those sets, and normally that is the case, are not disjoint, because people can enroll one or more language courses, let's write this. If 10 people enrolled in the Polish course, 10 enrolled in Polish course. Course should be lowercase. 6 in German course. And 4 in Spanish. And those sets, those people, had to enroll in only one course, so those sets are disjoint. We know that there are 20 people, right? This is obvious. 10 people in Polish course, 6 in German course, 4 in Spanish course. If those courses are at the same time, people cannot be on both, we have 20 people, right? But if people could, or students could enroll to 1 or 2 or even 3 of those courses, we only know that there are at most 20 people and at least 10 people that this amount of the greater set. And we cannot say anything more if we don't have more data. If we know how many people enrolled to both Polish-German, Polish-Spanish, and German-Spanish, and we know how many people enrolled to all of them, we can say how many people there are, for example, right? We'll see that in a moment in the next video. See you there. Hello, now we have 4 exercises, I know you see one for now, for our new principle when cases can overlap. So we have a group of students was asked whether they have a dog or a cat at home. The chart shows the results of this survey. So 15% of students have a cat at home, 65% of students have a dog, and 25% answer that they don't have neither a dog nor a cat. But some people that have a cat have a dog as well. and we don't know yet how many of them. Determine what percentage of the responders do not have a dog. So this is quite easy. Exercise 1a. As always, you can solve the problem and then check your results with my video. Do not have a dog. 65% of people have a dog. So 100% minus 65%. It is 35% of people do not have a dog. But exercise B, exercise 1b, have both a cat and a dog. And this is what I wanted to discover. To solve this, we need again do this Venn diagram. Normally in the probability, but not only, here as well, we draw a rectangle that represents 100% of people. So this is 100%. There is a circle or a disk that uses 65% of this area. So for example, we have I have a cat is set A, I have a dog is set B. So the area of B is 65% of this rectangle. So this is B. 15% of this rectangle is set A. And there is an overlap, maybe, but probably there is. I have neither a dog nor a cat is this place, right? Everything except A or B. So everything except A or B is 100% minus 25%, which is 75%. That means A union B encloses bounds an area of 75%, but A plus B, so A union B is equal 75%, which is equal the size of A plus size of B minus the overlap. A is 15%. B is 65%. So we have 75% equals 15% plus 65% is 80% minus the size of this area that overlaps. So how much is this area? What's the size? It must be 5%. So A intersection B, people who have a dog and a cat, or many dogs and many cats, are 5% of students. And this is exactly our inclusion-exclusion principle. Now, exercise 1c is much easier. Have a cat and do not have a dog. So, have a cat and do not have a dog is this place, right? Only this without this overlap. So we know that A is 15%, this overlap is 5%, so the answer is 10%. And the last, exercise 1D, have a dog and do not have a cat. 65% of people have a dog, only 5% of them have a cat as well, so the answer is 60%. So the most difficult part was the point B, which involves our inclusion-exclusion principle. Okay. Exercise 2. The similar as it was on the presentation. The students could enroll in language courses, Polish, German, and Russian. 11 students enrolled in the Polish course, 8 students enrolled in German course, 6. In the Russian course, 5 Polish and German, 4 Polish and Russian, 3 German and Russian, 2 students enrolled in all 3 courses. How many students in total enrolled in the courses? We assume that they needed to enroll at least at one of them. So, how many students is the size of this union? And we know that it is the size of A, the size of B, the size of C, minus the size of 2 sets, the intersection of them, all combinations, and not A but B, B and C, plus the intersection of all of them, as we already have seen at Vienna Venn diagram. So we want to know this. Let's A be people who enrolled on Polish course, B German, and C Russian. So it will be 11 plus 8 plus 5 minus 11 plus 8 plus 6 minus 5 minus A and C is 4 minus 3 plus 2. And that's all. We need to count it. 8 cancels out with 5 and 3. 6 minus 4 is 2, plus 2 is 4, plus 11 is 15. And that's the answer. You could thought that this principle is a hard thing, but as you can see, it's a simple equation. Exercise 3. In a school with 100 students, the students could enroll in language courses. They had to enroll in at least one of them. Italian, Spanish, and Portuguese. We have 100 students, and again, how many students enrolled in one, second, third group, Italian and Spanish, Italian and Portuguese, Spanish and Portuguese, how many students enrolled in all 3 courses. So, the same formula, so I will not write it anymore. It is 100 is equals 72 plus 50 plus 38 minus 30 minus 18 minus 19 plus students that enrolled in all 3 courses. So there's intersection of those 3 sets. Okay, so 100 is equal 72 plus 38 is 110 plus 50 is 160 minus 30 and 18 is 48 and 19 is 58, 67. $100 is equal 160 minus 67 is 93. So this unknown number must be 7, right? 7 students enrolled in all 3 courses. And yes, this is such simple. And the last one, exercise 4. In the new banking app, the bank has stated that each customer must choose a 4-digit PIN, but pins that contain 3 consecutive identical digits are considered invalid. How many valid pins can customers create? And here we have 2 ways to compute that. Let's use our new Inclusion-Exclusion Principle. So we have 4 digits. Inclusion-Exclusion Principle. 4 digits. Pins that contain 3 consecutive identical digits are considered invalid. So, in general, how many pins there are possible? In the first digit can be any of 0 up to 9 digits. 0 is also K for pin number. It is the same here, here, and here. So there are at most 10,000 valid pins. But we need to exclude some invalid ones. For example, if we choose one digit here, 1 of 10, it is, for example, 5. Then if we set 5 here, the complete number, and 5 here, complete number, then it doesn't matter what number we put here, 1 of 10. So here was 0 to 9, but we choose, for example, 5. All those pins are invalid. It is 100. It is similar situation when we have, for example, 1 of 10 digits here. We use the same digit in that place, for example 7, and here 7, and here 7, and it doesn't matter what we put here, 1 of 10 digits, it's also invalid pin number. But in that case, we counted twice a situation, so invalid pin numbers are in total, let's say, 200. But we counted twice situations where 4 digits are the same. For example, 0, 0, 0, 1, 1, 1, 1, 1, and so on up to 9999. We counted them twice as invalid numbers. So how many there are? N of 10, but here is the same, here is the same, here is the same, so there are 10 of them, right? And we need to subtract them from invalid ones. So the total number of valid numbers is 10,000 minus 100, they are invalid, minus 100, they are invalid, plus 10 because they were excluded twice. And this is 9,810. This is the correct answer. This was one way to do it. But there is a second way. We can use the rule of sum and the rule of product. Rule of sum plus the rule of product. Again, we have 10 digits here, 10 digits here, 10 digits here, 10 digits here, at most 10,000 digits. But we could count invalid ones in that way to have disjoint sets. So invalid ones are the one where we put any number here, any digit, and this digit is the same, this digit is the same, but this is different. So we do not use the same digit. Like here is 555, so here n 0 to 4 or 6 to 9, right? Then we have to exclude it situation when here is any number, any digit from 0 to 9. Here is the same, here is the same, but here we do not repeat the same digit for the 4th time, so we have 9. And we need to add situation because we haven't counted it yet, where all 4 digits are the same. So here is n of 10 digits, here is the same, here is the same, here is the same. So the number of numbers, pins that we need to exclude is 90 plus 90 plus 10. So it is 190. So the correct answer is 10,000 pins minus 190 invalid ones. It is 9,810. So we counted it in 2 ways. One of them is with disjoint sets, and we just use the rule of product here, here, and here, and the rule of sum here and here, right? there is no repeated situation in any of those three sets. All we don't care about ensure that those cases don't overlap, and we just compute cases that we cannot use where those three are repeated and here is any digit. Those three are repeated and here is any digit, but some cases overlap, so we need to count them as well and use the formula for Inclusion-Exclusion Principle. So we have two ways, and many times we can use two different ways, and the results must be then the same. Okay, that's all in this chapter. See you in the next one. Hello, at the beginning of this course I mentioned that discrete mathematics deals with sets that are equinumerous with sets of natural numbers. We will go over this information on what this equinumerosity is. To compare the cardinality size of finite sets, it is enough to count the number of elements in each set and compare these numbers. We know this, yes? We have two bags or sets, right? In the first bag there are 4 elements, in the second bag there are 5 elements. 4 is less than 5, so there are more elements in the second bag. Quite a simple rule. However, we do not have the ability to count the elements of infinite sets. But this is also something that discrete mathematics deals with, because it deals primarily with natural numbers. We can't count all the natural numbers and see how many there are, right? Because it would take us exactly infinite time. What therefore? Therefore, it would be necessary to count the elements also in these bags in a different way. Another way to compare the two sets can be the childish method. This is my name for this method, which allows comparing sets without knowing numbers. This child's way is exactly the way a child, 2 years old, 3 years old at the most, quite small, completely unfamiliar with the idea of numbers, would be able to tell that the number of elements in one set and in the other set is the same. For example, we give the child to check when we make tableware that the number of cups and saucers are the same. What does the child do? The child puts the cup on the saucer, the cup on the saucer, the cup on the saucer. Thud, crash, the first cup and saucer on the floor, then the second, then the third, and when it's all broken, it will find that not a single cup or saucer remains. This means that the number of cups and saucers turned out to be the same. Of course, it is enough to put these cups on the saucers to determine this, but if we add the element of smashing on the floor, we can additionally determine how many saucers are missing. For example, because there are 2 cups left on the table, right? But this is already ascertained by us. As I said, the child does not have this knowledge of numbers and at the time is able to determine whether 2 sets are equal or not. And in this way, we can also compare infinite sets. Let's see that this way works with an example with bags. We have 2 bags. If the child were to determine whether the number of elements is the same, it would be enough for him or her to tie such a golden thread between the elements of one and the other bag, so as to use all the elements in one of them, here in the first one, right? All of them are used. And we find that some elements from the second bag are still untied, and we no longer have no tied elements in the first set from bag 1. This means that there are more elements in the second bag. Conclusion: the second bag has more elements. So we don't need to count the elements to determine whether 2 sets are of the same size. If you use all the elements in bag 1 to bind to the elements in bag 2, and all the elements in bag 2 are used in this way, then both bags would have the same number of elements. What is lost here is the information about how many elements there are, but we know that there are or there aren't the same number. And that's often what we want to know, if it's the same, not exactly how many, right? Also, when we compare the numbers, so on which number is greater, we don't need to know by how much. The question was which one is greater. So, 2 sets, finite or infinite, A and B, are equinumerous if every element of set A corresponds to exactly one element of set B. And here is an assumption that all the elements of set B have been used. That is, you can't do in such a way that with one chain from the bag here, we connect multiple elements of the other bag. So we cannot do this. That is not allowed. And it's not allowed that an element remains unbound in one bag or the other. If either of these two situations will happen, we do not find equinumerosity. As elementary as it sounds, this is exactly the definition of equinumerosity, only it is more mathematical. Definition of equinumerous of sets. Two sets, finite or infinite, A and B, are equinumerous if there is a bijection between them, a one-to-one and onto function. What does this even mean? You don't need to understand it because it's exactly the same as what we wrote above, but in general, the function means that from one element can go at most one string. So, like those golden ones, right? From one element goes only one string. So the situation when for one element we connected two strings is not a function at all. The definition of function is precisely that. It is a certain mapping that assigns to each x, which is precisely an element of the source set, at most one y, which is at most one element in the target set. That is, two strings can't go because then it's not a function. And an one-to-one injection function means that at most one string is also pinned to each element. That is, an one-to-one function is not a situation where this element is pinned to two source elements, right? If that's the case, that two source elements are pinned to one target element, it is a function at all because two source elements can be assigned to the same value, but it is not an one-to-one function. And the fact that the function is so-called onto, more professionally that it is also a surjection, means that we have used every element from the target bag or from the target set. And this is exactly the same definition as we had before. They mean exactly the same. So, okay, the definitions are equivalent. The latter is strict, mathematical, but means exactly the same thing as the former. The sets are not equinumerous if such a function, such a matching, does not exist. If we are not able to connect all the elements one-to-one, it means that the sets don't have the same size. Not when we failed trying to do so, but when there is really no such possibility, right? Example, prove that there are as many even numbers as odd numbers. So, if we are able to connect, in quotation marks, with a string, every number from one set to every number from another set, it means they are identical number of numbers. So the numbers simply need to be paired. We have even numbers like 2, 4, 6, 8, 10, 12, 14, and so on. Odd numbers 1, 3, 5, 7, 9, 11, 13, etc. And we need to pair numbers. Yeah, solution, it is enough to pair the numbers 1 with 2, 3 with 4, 5 with 6, and so on. That is, we pair this number with this one, this number with this one, this number with this one, and so on. Notice that every even number has been used exactly once, and that every odd number is used exactly once. Not only every odd number was used, but it was connected to each number in even set. Yes, and that means that these sets are equinumerous, that they have the same size. According to the second, more mathematical definition, it would suffice to write that we have a function that for a given number n, whereby it would have to be written that n belongs to the set of odd numbers. So n belongs to odd numbers. This function for any odd number is adding a 1, because that's what we do. Changing 1 to 2, 3 to 4, we add 1. So, because there is a function that takes all possible numbers, odd numbers, and we have all possible even numbers on this side, we have a function that is bijection. There are actually the same number of numbers. Let's see if we had even numbers with 0, we would have exactly the same situation. So we have 0 here, and like we had this pairing 1, 2, 2, 3, 4, 3, 2, 4, 5, 2, 6, we would have 1, 2, 0, 3, 2, 2, 5, 2, 4, 7, 2, 6, and so on. So the formula for the function would be f of n is equal to n minus 1. So there are as many even numbers as there are odd numbers, whether or not we take 0 into account. Okay, so much for the basic concept of equinumerous, equality of sizes. See you in the next lesson. Hello, such equinumerosity, equivalence and cardinality, is studied in set theory, a whole branch of mathematics. That's why we cannot afford, at least in this course, to focus on comparing sets because it could easily become a course in itself. However, I've selected some sets which I believe are worth knowing to be equinumerous. Sets that are either finite or are equinumerous with the set of natural numbers are called countable sets. We also remember this from the first lesson of the course that discrete mathematics deals with such cases. We already know what countable sets are, right? Those that can be numbered using natural numbers. Then they can be numbered completely. Theorem. The sets of natural numbers with and without 0 are equinumerous. Let's prove it. We have two such sets. Let's call them n0, the natural numbers including 0, and n1, the natural numbers starting from 1. We construct a sequence of pairs. So 0 is associated with 1, 1 is assigned to 2, or 2 is assigned to 1. It doesn't matter here. 2 with 3, 3 with 4. And so in fact we are creating such a mapping that 1 is assigned to 0, 0 points to 1, 1 points to 2, 2 points to 3, and so on. We can see that we will number all the elements in this way. All elements from 0 to infinity will be numbered with numbers from 1 to infinity. Exactly. Notice that each element from n0 corresponds to exactly one element from n1, and that every element from n1 will be paired. Therefore, these sets are equinumerous. This completes the proof. Yes, this proof is so simple. There's no need to look for sophisticated formulations. Alternatively, we can define a function, a bijection, that transforms elements from set n0 to n1. That means we again take all elements from the source set and match them one-to-one with elements in the target set. Each element in the target set is paired with exactly one from the source set. The formula here is exactly the same as for even and odd numbers. Why? Because when we go from 0 to 1, then from 1 to 2, we add ones. It's just 1 plus 1 plus 1 forever, right? F of 0 is 1. F of 1 is 1 plus 1, 2, and so on and so on. So this function describes those arrows that I previously put. In theory, we can write, notice that the function assigns exactly one, always distinct, value from the set n1 to each element from n0, and that every number from the set n1 is an output of the function f. Therefore, the sets are equinumerous. I put this in square brackets because the word bijection refers to this whole definition. We must remember that when we use the word bijection, it means we assign exactly one element, not that we assign both 1 and 2 to 0, and in reverse, each 1 and 2 must be assigned exactly once. Not that both 0 is assigned to 2 and 2 is assigned to 2. No. That means bijection. Every element is used in both sets, and each element is used exactly once. So instead of writing out the whole pairing, we can just end the proof here if we have used the word bijection. Of course, there is nothing wrong with always creating a sequence of pairs, drawing lines or arrows, and writing that we are performing such a pairing, even without knowing a formula. That's also always correct. Returning to the point. Let's notice that n1, the natural numbers from 1 to infinity, and n0, which includes 0, are equinumerous. And that is the conclusion. Adding an element to an infinite set or removing an element from an infinite set does not change the size of the set. What's more, adding or removing an infinite number of elements from an infinite set does not change its cardinality, size. If we take the set of natural numbers with or without 0 and add 100 elements to it, say 100 negative numbers, the cardinality of the set does not change. That's how it works for infinite sets. If we add a finite number of elements, the size of the set remains the same. In other words, 100 elements plus infinite set equals the same infinity. Now an example from outside discrete mathematics, because we are dealing here with continuous sets, not stepwise ones. I mean, between 0 and 1 there are infinitely many numbers, but it nicely illustrates how it works. So consider two intervals. The set from 0 to 1, excluding 0 and 1, and the set from 0 to 1, including 0 and 1. And both are equinumerous. That is, the cardinality size of set A equals the cardinality size of set B. Let's prove that sets A from 0 to 1 without 0 and 1 and C, same as A but with 0 added, are equinumerous. If we can do that, then we can also add number 1, right? In the same way. First we add 0, adding 1 is done analogously. So to do so, let us split the set A into two disjoint sets. A1, the set of fractions with numerator 1. So 1 second, 1/3, 1/4, 1/5, and so on. There is no 1 divided by 1 because it is 1 and 1 is not in set A. And A2, the remaining numbers from the set A. So for example, in A2 there are numbers like square root of 2 divided by 3. It is in A2, of course, as well. So maybe write it that way. Also, 2 sevenths is in A and A2, right? Also, logarithm with base 3 of 2 is in A2. So there are infinite numbers in A2, also in A, and only those are in A1. In the same way, all these numbers I mentioned belongs to the set B and to the set C. And now we can define a function that maps set A to set C, and this is a bijection. The formula might look complicated, but it's actually quite simple. It says, if we are dealing with a number from the second set, we leave it unchanged. That is, the root of 2 by 3 corresponds to the number the root of 2 by 3. If we take a number 1 second, we assign it to 0. And for any other fraction, which is not 1 second, from A1, we assign it the fraction 1 by n minus 1, which means 1 second becomes 0, 1/3 becomes 1 second, 1/4 becomes 1/3, 1/5 becomes 1/4, and so on. Let's see it. So we have set A, which has a lot of numbers, like this one, like this one, like this one. It is also in A. Like I said, logarithm base 3 of 2, so 3 to what power gives us 2. And there are those numbers. 1 second, 1/3, 1/4, and so on. Those are infinite many, and those are infinite many. We have set C, which has the same numbers, exactly the same numbers, all of them, which I cannot write them all, and this becomes this one, this becomes to this one, we assign the same number to the same. But C also has 0, and then has also those fractions. The first part is done. We connect all numbers that are not those fractions to themselves. Now we assign 1 second to 0 and 1/3. 3 minus 1 is 2, so 1/3 we assign to 1, 2. 1/4 to 1/3, 1/5 to 1/4, and so on. What have we written? That if x is, f of x is, let's say, a strange number, then we just copy it over. This one maps to that one, this maps to that one, and so on and so on. No change. If x is 1, 2, we assign it to 0. An additional number 0. We are now including 0. If we are dealing with any other fraction from the list, this list, starting from 1/3, we map it to the previous one, right? So to 1, 1/3 maps to 1, 2, 1/4 maps to 1, 3, and so on. And we can see that all elements of set C, including 0, have a corresponding element in set A, which doesn't include 0. So indeed, adding any element, or even an infinite number of elements to an infinite set is always possible. Okay, if you got a bit lost here, that's okay too, because we won't be dealing with such so-called continuous cases, like sets from 0 to 1, since discrete mathematics doesn't focus on them. But you can also try to show the equivalence between C and B now, between sets C and B, meaning add the number 1 to set C, creating an analogous function or mapping, just as exercise. And we'll move on in the next video. Hello, returning to the sets that discrete mathematics deals with, that is, countable sets, we have a theorem stating that the set of natural numbers and the set of integers are equinumerous. For every natural number, including 0, we define the following function. Again, we are mapping natural numbers with 0 to the set of integers. If we're talking about 0, we assign 0 to 0, right? For every even number, we divide it by 2. For every odd number, we add 1 to it, divide by 2, and then put a minus sign in front. What does it mean? That means that 0 maps to 0. 0, if n is 0, the value is 0. If n is 1, n is odd, so 1 plus 1 is 2, divided by 2 is 1, minus 1. If n is 2, n by 2 is 1. The next, 3 plus 1, 4 divided by 2, 2 minus 2. 4 divided by 2 is 2, and so on. 5 will be minus 3, 6 will be 3, 7 will be minus 4, and 8 will be 4. And so on, of course. So what do we have here? We can see that on the left we have natural numbers, and on the right integers. And we won't run out of natural numbers to enumerate all integers, so they must be the same size. Although this does not change the fact that natural numbers are indeed a subset of integers, right? So we can write that natural numbers are a subset of integers. We have integers, and maybe put dots here, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and so on. And natural numbers are only those, 0 or without 0, right? Those are natural numbers. So natural numbers are a subset of the integers because integers include both the natural numbers and their negatives. And if we try to match natural numbers with 0, in that way that we connect 0 to 0, 1 to 1, 2 to 2, 3 to 3, and so on, then we would run out of natural numbers before we could number all the negative ones. But note that the definition was different. The definition said that if we are able in any way, for example, by reorganizing the elements of a given set, here a set of integers, not as 1, 2, 3, 4, 5, and then negatives, but 0, -1, 1, 2, -2, and so on. Negative, positive. We can write down all of them. If we are able to number the set so rearranged set with natural numbers, then although the set of natural numbers is contained in the integers, they are the same size. And of course we have this diagram. We know from the school that here are integers and natural numbers are a subset of integers. But it doesn't change the fact that they are as many as integers, natural numbers as integers. If it seems somehow complicated to you, if you think that here is a certain mishmash, this is true. These concepts were created by Cantor in the at the end of the 19th century. All of these things, these saucer assignments that we are actually doing here, were invented by Cantor in the 19th century. And so George Cantor got tangled up here, wondering how one set could belong to another even though they have the same number of elements, etc. He also proved that the set of rational numbers is smaller than the set of irrational numbers, yet between any two elements of the set of irrational numbers there are infinitely many rational numbers even though there are fewer of them. And so here, forgive the phrasing, he got so tangled up that he ended up suffering from mental illness. Specifically, George Cantor first struggled with depression and later his psychiatric condition prevented him from continuing his work. So if this is difficult for you, rest assured it was no easier for its creator. Okay, let's move on. This fairly complicated proof with a function can be written more simply. We can just create pairing. We have rearranged integers and we create pairs. The first number is natural number 0, 1, 2, 3, 4, 5, 6. And on the right we have integers, all integers 0, 1, -1, 2, -2, 3, -3, and so on. Notice that natural numbers, including 0, is contained within the integers, yet every integer has a corresponding natural number. Therefore, these sets are equinumerous, have the same cardinality size. From the fact that we know that sizes of natural numbers with 0 is the same as size of natural number starting from 1, we conclude that the sets natural numbers starting from 1 and integers are also equinumerous. To put it differently in the simplest possible way, to avoid falling into philosophical reflections that might lead us to question the meaning of existence, let's observe that we have integers listed alternatively, positive, negative, and so on. We then number them. This is the first number. This is second number, third number, fourth number, fifth number, sixth number, seventh number, eighth number, ninth number, and so on. So, again, natural numbers are a part of integers, yet we have enough natural numbers to number all integers. And that implies that they must be the same amount of them. So, we can see that we can write it with arrows. Every integer number can be assigned to natural number, even though natural number is a part of integers. So we need separate two things, containing that one set is contained within the other set. This one thing, and different thing is cardinality, the sizes of infinite sets. Those are two different things. So we see a clear correspondence. So no matter how much it seems like there are more integers, this isn't true. And it's worth remembering a new definition. A given set is a countable equinumerous with the set of natural numbers if it can be enumerated, numbered with natural numbers. Of course, finite sets are all countable. And now examples of countable sets. First, natural numbers. With 0, without 0, by definition, are countable. The union of these sets, natural numbers and a finite set A, has the same cardinality as natural numbers. As we discussed, adding finitely many elements doesn't change a set's cardinality. I mean for infinite sets. The set of integers, because they can be numbered. The set of even numbers, similarly the set of odd numbers. Why? What does it mean? Theoretically, evens should be half of natural numbers. But again, we have natural numbers. So 1, 2, 3, 4, 5, and so on. And we can number them with only even numbers that are part of natural numbers. So we can number 2, 4, 6, 8, 10, 12, 14, 16. If we can number one set with, in quotes, smaller set, those sets are the same size. The set of rational numbers is also equinumerous with natural numbers. That is, all fractions, 1/2, 1/3, 5/6, whole numbers, 5, -5, etc., taken together have the same cardinality as natural numbers. We will see this in the next lesson. The set of prime numbers, again, because we can enumerate all natural numbers with prime numbers, so they need to have the same cardinality. And now examples of uncountable sets. The set of real numbers. There is no way to create a function, arrows, or numbering that maps natural numbers to all real numbers. It's impossible. This has been proven. We cannot enumerate all real numbers. The set of irrational numbers, real numbers that aren't rational, this is also uncountable and moreover larger than the set of natural numbers. The interval from 0 to 1 on the number line, whether open or close, any interval in fact, is uncountable. The set of all subset of the set of natural numbers. In other words, the power set of natural numbers, set of all subsets. This too is uncountable. It cannot be numbered. How we can imagine that? Let's say we have only 6 natural numbers. So we have 0, 1, 2, 3, 4, 5. Now from 0. Let's try to write down all subsets of this set. So we have singletons, 0, 1, 2, up to 5. Then we have pairs, 0, 1, 0, 2, up to 4, 5. Then we have triples. Then we have 4 elements, 5 elements in one set, and the last element is the whole set itself. So, when we have only 6 natural numbers, there is so the size of this set is 6. Let's say all those subsets are the set A. The size of A is 2 to the power of 6. It's 64. So for 6 numbers, we have 64 subsets. And when we take all the natural numbers, infinite many, we have even more infinite subsets. And we cannot match natural numbers with their all subsets. Now 2 key terms and notations. The cardinality of the set of natural numbers is denoted by the symbol Aleph 0, Aleph null or Aleph 0. In other words, there are Aleph 0 natural numbers. So a countable infinite set is referred to as having cardinality Aleph 0. Aleph is the Hebrew letter, the first Hebrew letter, as I remember, and with the subscript 0 indicating it's the smallest infinite cardinal. Uncountable sets, like the real numbers, irrational intervals, or the power set of natural numbers, are collectively described as having the cardinality of the continuum. This is denoted in various ways across literature, so Aleph 1 in fact assuming the continuum hypothesis, but yes, normally we assume it. This factor C for the continuum, 2 to the power of natural numbers, the set of natural numbers, this is how we put power set of natural numbers, 2 to the power of aleph 0, or the size cardinality of real numbers. All means the same, assuming this continuum hypothesis. So the set of natural numbers represents the smallest possible infinity in terms of cardinality. Every smaller infinite set has the same size as natural numbers, while the continuum is the smallest possible infinity that's larger than the first one. And of course we can continue this hierarchy, aleph 2, aleph 3, aleph 4. Aleph 2 is the smallest infinite set, larger than aleph 1. Will we be studying this? No, not in this course. That's the domain of advanced set theory. For our purposes, I wanted to focus on certain fundamental concepts. So if you didn't grasp some parts, don't worry, we won't be using them. The key takeaways I wanted to emphasize are: there exist different sizes of infinities. This is crucial. Real numbers and natural numbers are both infinite, but they have different sizes, different cardinality. The second thing, what I wanted to emphasize is sets equinumerous with natural numbers are called countable, and these are only ones discrete mathematics deals with. They are step-by-step collections like 1, 2, 3, and so on. Also 1/2, 1/3, 2/3, 1/4, and so on, where between any two elements you could theoretically insert many others. Also important, there are infinite sets that aren't equinumerous with natural numbers, the real numbers being a prime example, but we won't be working with them in this course. Discrete mathematics doesn't deal with them. Finally, I wanted you to remember how to recognize when two infinite sets have the same cardinality. If you can pair all their elements in one-to-one correspondence, match them with arrows, then they are the same size. If you take just one thing from this lengthy lesson, let it be this matching principle. If you have understood more than that, I'm absolutely delighted. See you in the next one. Hello, and now all that's left is to show that the set of rational numbers is countable, that is, it has the same cardinality as the set of natural numbers. This isn't as straightforward as it may seem. Finding a way to enumerate the rational numbers isn't an easy task. First, let's recap what we already know. Two sets have the same cardinality if there exists a one-to-one pairing between all elements of the sets. That's our saucers and teacups method. Sets do not have the same cardinality if such a pairing does not exist. Now when we cannot do that because we haven't figured it out yet, but because no matter how hard we will try, it's impossible. Adding infinitely many elements doesn't change an infinite set's cardinality. Meaning if we add a finite number of elements, the cardinality, the size of an infinite set, doesn't change. Now here's our case. If for two sets A and B, A is a subset of B, and you can enumerate B using elements of A, then the sets A and B have the same cardinality. So if A is a subset of B, so we can think about it like A is smaller, in quotes, smaller set, but with that smaller set we can enumerate all elements of bigger set, then they have the same cardinality. Every infinite subset of natural numbers is equinumerous with natural numbers itself, meaning it's countable. So the set of prime numbers, triangular numbers, lucky numbers, happy numbers, yes, such numbers exist. Perfect numbers, all of these are a subset of the natural numbers, but since they are infinite sets, they must be equinumerous with the set of natural numbers, because the natural numbers are, in a way, the smallest infinity possible. And now, at first glance, the set of rational numbers appears infinitely larger than natural numbers. If we place the natural numbers on a line 0, 1, 2, with 0 here, up to 10, of course it goes on infinitely, between any two natural numbers, we can insert infinitely many rational numbers. And the natural numbers themselves are, here marked with tiny yellow circles, the natural numbers are also rational numbers, because every natural number can be expressed as a fraction of that number over 1. So, between any two natural numbers, we can put infinitely many rational numbers, and those natural numbers are also rational numbers. So how could we possibly enumerate these rational numbers using natural numbers? Yeah, natural numbers and integers are a subset of rational numbers. Between any two integers, there are infinitely many rational numbers. That's what we already know from the picture. And equinumerosity occurs if all these rational numbers can be numbered. And now let's try to achieve exactly that. Let's try to enumerate all rational numbers. There are several proofs of this equinumerosity that the set of rational numbers is countable, can be enumerated using natural numbers, meaning they are of the same size. We will use the diagonal method. This method goes by different names, but we'll call it the diagonal method because we are moving along the diagonals. Here's how it works. We create a table where the columns represent numerators and the rows represent denominators. So here are numerators and here are denominators. We fill the table like this. Here we write the numerator, for example, 1 over the denominator 1. So it is 1. Here 4 over 3. 3 over 4 and so on, right? Filling in all the elements. So here is 2/5, here 6/6, which is exactly 1, just like 1 over 1, and so on until the entire table is filled. I've moved the table over so everything fits on the screen. First, 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3. We are just rewriting those columns because the denominator is 1. Next, we divide each numerator by 2, right? Here are numerators and denominator is 2, so every of those numbers are divided by 2. Then by 3, by 4, by 5, by 6, and so on for all. This way, we list all possible fractions. Every conceivable fraction appears in this table, because no matter what fraction you think, like 7/11, you just go to column 7 and row 11. And at their intersection, you will find 7/11. Similarly, 11/7 is found at column 11 and row 7. So indeed, this table contains all possible fractions, right? There is no fraction you can think of that doesn't appear somewhere here, though some appear multiple times. Now the diagonal method means we will list these numbers by following diagonals. So first, this diagonal, I will try to show it, then the second one, then the third one. Unfortunately, these diagonals aren't perfectly even, but that doesn't matter. I've colored them appropriately. So, not here, it goes here, right? And similar here. We will list them in this order. So first we have the number 1. We are moving diagonally through the table. Next, diagonal 2 and 1/2. The following diagonal 3 and 1/3. I'm not rewriting numbers that have already been listed. We are skipping duplicate. Next diagonal, then the next one, and we can continue this infinitely. You'll notice that this way we're listing all fractions from left to right. As we said, whether it's 7/11, 11/7, or 177, they're all here. We just need to reach column 100 and row 77. At some point, they will appear on some diagonal and will be included. In this order, we are listing all possible positive fractions, and simply we can number them. Right? All the fractions are numbered now. So I just numbered it by 1, this by 2, this by 3, this by 4, by 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. And interestingly, we'll never run out of natural numbers to enumerate all these infinitely many possible fractions, right? Let's look back here. For example, these fractions. 1/3, 1/2, 2/3. 1/3 is here, 1/2 is here, 2/3 is here. No matter what fraction we imagine, they will eventually appear here, so we have successfully enumerated them all. We can enumerate all possible rational numbers using natural numbers, so they have the same amount of numbers, the same cardinality. But wait, there are more rational numbers because we also have negative numbers, and 0 is also rational number. But in reality, just as we have enumerated the positive ones with natural numbers, we could use negative integers to enumerate all negative fractions and assign 0 to 0. Thus, for all rationals, positive, negative, and 0, we can show equinumerosity with integers, and equinumerosity between integers and natural numbers is already known to us. Okay, a few final remarks. First, you could write a Python program or use another language that implements this diagonal method to locate any given fraction. For example, user inputs 1 and 6 for 1/6. The program responds it's the 17th number in the diagonal enumeration, like here. We are only considering positives here. User inputs 133 and 3 for 133/3. We return it's the 725th rational number. The program would give the position for any user input fraction or integer like 6 appearing in 12th position. This is a fascinating exercise. I've included a sample solution with the course materials, so you can check how I solved it. Second, you can read more about that diagonal method. The diagonal method is typically used to demonstrate unequal cardinalities between sets. In fact, this same method proves that we cannot enumerate all numbers between 0 and 1 using natural numbers, meaning real numbers have different cardinality. There are more real numbers than natural numbers, and the proof is here. It is done with diagonal method. The proof shown here might be slightly challenging, but I believe you are fully capable of understanding it. So the diagonal method thus serves to prove either equinumerosity or non-equinumerosity of sets. Other things, when you go to cardinality page on Wikipedia, you will review everything we have covered. Those arrows, right, that there is a bijection. We can find this information about Aleph null or Aleph 0 and continuum. There is information about George Cantor here. So all the information we've got, they are here. Here are those informations that I showed you already, that in those ways we can write cardinality of real numbers. So all the information that we covered are here. Of course, there are much more here, so you can read about them. Okay, that concludes this lesson. I will see you in the next one. Hello, now we'll talk about the most known, popular subset of natural numbers, prime numbers. Just a quick reminder from school, prime numbers are natural numbers greater than 1 that have exactly 2 divisors, 1 and themselves. Examples of prime numbers 2, 3, 5, 7, 11, 13, 17, 19. Composite numbers are natural numbers greater than 1 that have more than 2 divisors. Examples of composite numbers: 4 is divisible by 2, 6 by 2 and 3, 8 by 2 and 4, 9 by 3, and so on. Theorem: there are infinitely many prime numbers. The proof was already provided by Euclid around 300 years before Christ. To prove that there are infinitely many prime numbers, we can assume the opposite, that there are only finitely many primes. This kind of proof by assuming the opposite is called proof by contradiction. If there were only finitely many prime numbers, we could list and number them. So 2 would be the first prime number, 3 the second one, and so on up to n, where n is the largest prime number and k is its index. Thus p1, p2, p3, p4 up to pk would be all the prime numbers in existence. We could then construct a number that is the product of all these primes, meaning the number L equals 2 times 3 times 5 times 7 times 11 times all primes up to the last one. Or using the notation for these primes, L is equal to P1 times P2 times Pk. The number L is obviously a composite number and is divisible by all the prime numbers. It's divisible by 2, 3, 5, 7, 11, and so on up to n. Now let's consider the number m that is equal to L plus 1. That is, 1 more than L. What do we observe? M is not divisible by 2 because L is divisible by 2 and the next number divisible by 2 would be L plus 2. M is not divisible by 3 because L is divisible by 3 and the next divisible number would be L plus 3. Similarly, it's not divisible by 5, 7, 11 or any other prime up to n. The number m is greater than pk, the last one, and it's not divisible by any of the numbers 2, 3 up to n. It has only two divisors, 1 and itself. We have a contradiction. M must be a new prime number, but this contradicts our initial assumption that we had already listed all primes. Therefore, our assumption was false, and there are infinitely many prime numbers. Basic properties. There are infinitely many prime numbers. Although not every natural number is prime, primes are a subset of natural numbers, but there are infinitely many primes, so they must be countable, the same size as natural numbers. We have also indirectly proven that there are infinitely many composite numbers because every number L, the product of all primes up to some pk, up to some n, is composite, and since primes are infinite, so are such composites. 0 and 1 are neither prime numbers nor composite numbers. 0 is neither prime nor composite, it has infinitely many divisors. Every non-zero integer divides 0. A divisor is, of course, a number which divides a number without remainder, without fraction. 1 is also neither prime nor composite, its only divisor is itself. Every composite number can be written as a product of prime numbers, like 70 is 2 times 5 times 7. 100 is 2 times 2 times 5 times 5. There is only one even prime number, 2. Every other even number is divisible by 2 and thus composite. All other primes are of the form 2k plus 1. For every natural k, 2k is even, so 2k plus 1 is odd and can be prime. For divisibility by 3, primes other than 3 itself must be of the form 3k plus 1 or 3k plus 2. Numbers like 3k or 3k plus 3 are divisible by 3 and thus composite. For k more than or equal 5, primes can only take the forms 6k minus 1 or 6k plus 1. This is a useful property and we'll explore it further later and prove it later in one of the next videos. So how to find prime numbers? One of the simplest yet effective methods for finding prime numbers is the so-called Sieve of Eratosthenes. Finding prime numbers using the Sieve of Eratosthenes. We list all numbers from 2 up to some limit, here 100. This is the range we want to search for primes. We mark the first number that hasn't been crossed out, this is 2. Now we move in steps of 2. 4 is no longer a prime number, 6 is no longer a prime number, 8 is no longer a prime number, and so on, here up to 100. I've marked them in violet, but on paper they are usually crossed out. Once we finish and reach the end of the set, we take the next number that hasn't been marked or crossed out, this is 3, which is a prime number. Now we move in steps of 3. 6 is already crossed out, but 9 wasn't. 12 is already crossed out, but 15 wasn't, and so on. Next, we take the number 5, which hasn't been crossed out yet, and move in steps of 5. 10, 15, 20 were crossed out, but 25 wasn't. Additionally, we cross out 35, 55, 65, 85, and 95. Then we take 7 and cross out 49, 77, and 91. All the remaining numbers, the unmarked ones, are prime numbers. But shouldn't we keep crossing out further? No, because once we've reached a number greater than the square root of the last number is in our set, here the square root of 100 is 10, all the remaining numbers won't be crossed out. And they are already prime numbers, meaning they always were, we just now know it. This leads us to an important conclusion, which we'll justify shortly. To check if a given number is prime, we don't need to try dividing it by all natural numbers from 2 to 1 less than the number itself. It is enough to try dividing it by prime numbers smaller than it from 2 to the square root of the number. Justification. There are numbers whose only non-trivial divisor different than 1 and the number itself is their square root. For example, 9 has the only divisor 3, different than 1 and 9. These numbers are called square numbers, because 9 is 3 square. When dividing a square number by its square root divisor, we obtain the square root divisor. 9 divided by 3 is 3. If there is a divisor greater than the square root, for example, 8 has a divisor of 4, and 4 is greater than the square root of 8, dividing will give a number smaller than the square root, because 8 divided by 4 is 2. Since dividing by a larger number gives a smaller result, right? Dividing by square root gives us a square root. Dividing by a larger number greater than the square root always yields a smaller result. So in fact, to verify if a number is prime, it's enough to check divisibility only by 2, 3, 5, and subsequent prime numbers, up to the largest natural number not exceeding the square root. Example, is 101 prime? 101 doesn't divide by 2. 101 is odd. 101 doesn't divide by 3. Reminder, a number is divisible by 3 if the sum of its digits is. For 101, 1 plus 0 plus 1 is 2, and 2 isn't divisible by 3. So 101 isn't divisible by 3. 101 isn't divisible by 5, because the last digit isn't 0 or 5. 101 doesn't divide by 7, and that's all. At the end, 101 is a prime number, right? This way, we can quickly verify if a relatively small number is prime. In the next lesson, we'll program these two key insights. See you there. Hello, here we have the code of the program I mentioned last time, which is which number in the diagonal method the specific rational number is. You can review this program, I highly encourage you to do so, and we move on to write the algorithm for the program that generates prime numbers. We can do this in two ways, using Sieve of Eratosthenes. We can write a for loop for e in range up to 1 million and generate all primes in specific range, here up to 1 million. We can go, of course, from 2 because 0 and 1 are not primes. And the second idea is to find a million prime numbers. Then we'll write it in this way. Y, some list of primes, is less than 1 million. Search for the next primes. So we are looking much further than for a million. We want the first million prime number, so the last one will be more than 1 million. So in the beginning we need some prime numbers, specifically a 2, but I mean we can insert 2, 2 and 3, 2 and 3 and 5. Those we know to be prime numbers because we have to check the subsequent numbers with them. Now the one to be checked will be 3, so current will be 3. And initially we can consider a given number to be prime, so is prime is equal to true, but it is not if it is divided by some prime numbers we already have. That is, for any prime number for p in primes, if current is divisible by prime from the list without remainder, it means it is not a prime. If prime is equal to false, and we break the loop. And now, if our condition in for loop never succeeded, it means that this prime is a prime number, so we can add it to the list. So primes append current one. And we need to increase the number we are considering to be a prime now. So current is 3, and what will be the next one? All the primes except 2 are odd numbers, so we can go with steps of 2. So plus equal 2. Okay, we would like to see if that works correctly. So let's print the first 100 primes and the last 100 primes. We know the first ones like 2, 3, 5, 7, 11. And we know that the last ones, it should be minus 100. The last ones are bigger than 1,000,000. We can try to run it, but we don't know how long it will work. So we would like to break it. And we could print the current prime number. For example, here, this is one way. And we can see that it is only 50,000, right? So it will take some time. Let's decrease it to 100,000 primes. And we will see how long it will take. It would be nice to see the actual time that it took. So we will write a time measurement in a second. It should be go farther than 100,000 number because we are looking for 100,000 primes. So it is much bigger than 100,000, right? So in the meantime, we can write import or from time import perf counter to measure the time. We can start measuring time here, start perf counter, and we can stop doing that after printing those primes. Stop perf counter, and we can print how long did it take. So print it took stop minus start. Let's round it to 2 decimal places. Seconds. Okay, we can see that this is correct, right? 2, 3, 5, 7, 9. 9 is not a prime number. Oh, we should have added this. This is why maybe this loop was working so long, because we should add those this number, current number, to primes only if is prime is true. So if is prime, let's add it to the list, right? And then add 2 and check the next one. Okay, we would like to know how long does it take. And okay, it should end in some minutes. I will be back when it finishes. Okay, now it's working. 2, 3, 5, 7, 11, and so on. And the last prime is 1,299,709. Maybe we can write it down that the last is like this. Maybe we can show only the last 10. And it took 7 minutes. 7 minutes and 16 seconds. So this is a long time. Okay. And now we can consider how to speed up the code. One of the properties of prime numbers and this sieve of Eratosthenes was that we don't need to check every prime number if it divides the current considering number, we only need to do so up to the square root of the number, right? So we can import from math import sqrt, import sqrt, it means square root, right? So we can write square root here. Current square root is square root of the current number. And if p is more than the square root of this number, if p is more than current sqrt, it means that none other number can divide it. So we can put break here, and because square root any float computation is not precise, we could do conversion to integer and add 1 to this current sqrt. So if square root from 9 is not 3 but 2.99999, it still will work. Okay, we can check how fast the code is now, and if the result is the same. We can see that it speed up extremely, right? So it is 3.12 seconds. So now we can look for 1 million primes. So change it to 1 million, run it again, and it will be quicker than 100,000 in a previous way. So this is for 100,000 primes. And the last is like this. And now we will know how it is for 1 million primes. Okay, let's check how fast it will find 1 million primes. So now it took 92.23 seconds. And the last one is 1,548,000, right? We need to check that. No, it is 15,485,863. This is the last one. It should be here. This is the millionth prime number. And the question is if we can speed up it even more. Yes, we can. If you remember, we don't need to check every odd number like 3, 5, 7, 9, 11, and so on. We can check only 6k minus 1 and 6k plus 1, right? So instead of checking 3, 5, 7, 9, 11, and so on, we can check for k equals 1, it is 6 minus 1 is 5, and 6 plus 1 is 7. The next ones, 2 times 6 is 12, minus 1 is 11, and 2 times 6 is 12, plus 1 is 13. And we do not check 9 at all. But to do so, we need to change primes to be 2 and 3, because this method with 6k minus 1 and 6k plus 1, it works from 5 and more. So instead of having current, we have k equals 6. We have two numbers, a equals k minus 1, b equals k plus 1, and at the end we change k plus 6. 6, 12, 18, and so on, and 1 minus and 1 plus this k. Current sqrt can be sqrt from the bigger number. And what is a current number to check? We can check current in A and B. We have two numbers to check. Okay. Again, is prime equals 2. For prime in primes, if p is more than current sqrt will break if current divides by p equals 0 is prime false break. If is prime append. And that's all. I think it's correct. We will see in a second. And we'll see how fast it is now. So it should be much faster because we do not check every odd number, but only pairs with steps that is equal to 6. Okay, let's check that. We again have numbers, and we'll see how fast is it going. And it is 72 seconds, so 20 seconds less. That's a lot. Of course, there are better algorithms than this clean sieve of Eratosthenes, but I wanted just to show you how to find prime numbers in specific range and all prime numbers up to some point. And we should see if the number, the last one, is correct. It is, and the beginning ones are also correct. So this new algorithm is also correct. Okay, that's all in this lesson. See you in the next one. Hello, now we will learn more about prime numbers. First, let's check that indeed if p more or equal 5 is a prime number, then p equals 6k plus or minus 1, where k is any integer. We've already checked that with a program, but let's verify it with a mathematical proof. Well, numbers in terms of division by 6 can be equal to 6 times something, so p equals 6k, and that is not a prime number because it is divisible, for example, by 6. Those numbers are like 6, 12, 18, 24, and so on, so they are divisible by 6. 6k plus 1, for example 7, which is 6 times 1 plus 1, 13, 6 times 2 plus 1, or 19, 6 times 3 plus 1. And for such numbers, we don't know if p is prime. We need to check it for every p. For the next case, p equals 6k plus 2. P is not a prime number because 2 divides 6k plus 2. For example, for k equal to 3, we have 6 times 3 plus 2 is equal 20. So it is divisible by 2 and we'll always get an even number. If p equals 6k plus 3, then p is not a prime because 3 divides p. For example, let's take k5. 6 times 5 is 30 plus 3, 33. And 33 is divisible by 3. This notation means that 2 divides p and here 3 divides p. Similarly, a number cannot be a prime if it's 6k plus 4 because again 2 divides p. But 6k plus 5 could be prime, we don't know yet. Thus, therefore, a number p can be prime only if p equals 6k plus 1 or p equals 6k plus 5. However, the numbers generated by 6k plus 5 are the same as those generated by 6k minus 1. For example, 23 is 6 times 3 plus 5, but also 6 times 4 minus 1. Of course, the domain is shifted for 1k, because for 6k plus 5, the smallest number we can generate with positive k is 11. But 6k plus 5 for positive k or 0 is the same as 6k minus 1 for positive k. Thus, indeed, the only possible prime numbers for p more or equal 5 are of the form p equals 6k plus minus 1, where k is positive integer. And now we have this theorem. If p is a prime number greater than or equal to 5, then 24 will divide p squared minus 1. It's quite interesting that we don't have an explicit formula for prime numbers, nor a fast method for generating primes, yet all prime numbers from 5 upwards, when squared and reduced by 1, are divisible by 24. The proof. We can use the fact that every prime p from 5 upwards is in the form 6k plus minus 1. K should be positive integer here, but let's imagine it is written. So instead of p squared minus 1, we substitute p with 6k plus minus 1. Using the algebraic identity, first we have 36k squared, then twice the first term times the second, keeping the sign, then 1 squared is 1, and minus 1, right? So this one is from this square, and this minus 1 is rewritten. We're left with 36k squared plus minus 12k. We can factor out 12k, giving 12k times 3k plus minus 1 in parentheses. Now this part is divisible by 12. In fact, 12 is obviously divisible by 12. But for the whole expression to be divisible by 24, it's enough if the second part, 3k or k times 3k plus minus 1, is divisible by 2 when it is even. Then the number squared minus 1 will be divisible by 24. Yes, we know that 12 is divisible by 12. It is enough to show that 2 divides the rest. If k is even, then 2 divides k, so it divides everything. We are finished then. If k is odd, then k equals 2l plus 1 for some integer l. And for 3k plus 1, because, we have plus or minus, yes, it is or. It is not plus and minus simultaneously. So we need to check both. When there is plus 3k plus 1, we substitute k with 2l plus 1, and it equals 6l plus 4, so it is divisible by 2. When it is 3k minus 1, we again substitute k with 2l plus 1, and it is 6l plus 2. So again, it is even. So in either case, 2 divides k times 3k plus minus 1, meaning the entire expression is divisible by 24 quaterat demonstrandum. Now maybe an example. Let's take 7. It's a prime number. If we square it and subtract 1, we get 49 minus 1, which is 38. And 38 is divisible by 24. If we take another prime, say 11 squared minus 1, it is 121, minus 1, it is 120, and it is again divisible by 24 because 24 times 5 is 120. It's quite surprising that all prime numbers from 5 upwards satisfy this property. Now there's Fermat's little theorem. If p is a prime number and a is an integer such that a is not divisible by p, then we have this equation. It is congruency. We'll talk about congruences later. In formal terms, it reads a to the power of p minus 1 is congruent to 1 modulo p. But in plain terms, since we haven't covered congruences yet, we'll do it in this section. A number a raised to the power of p minus 1 leaves a remainder of 1 when divided by p. Example, 88 to the power of 100, we can write it as some number times 101 plus 1. Here, p, the prime number, is 101, and any number that is not divisible by 101, so for example 88, to the power of 1 minus, so 101 minus 1 is 100, so any number to 100 that is not divisible by 101 gives a remainder 1 in this equation. Yes, so 88 to the power of 100 leaves a remainder of 1 when divided by 101. In particular, any number not divisible by 3 when squared leaves a remainder of 1 when divided by 3. At first glance, this might seem like a minor detail, that what remainder of a number leaves when divided by a prime, but this is an extremely important theorem. Next, there's Wilson theorem. It's an interesting but inefficient method for testing the primality of natural numbers. Wilson theorem: a number p is prime if and only if p minus 1 factorial is congruent to minus 1 modulo p, which means a number p is prime if and only if the factorial of 1 less than p leaves a remainder of p minus 1 when divided by p. Example, the number 5 is prime because 5 minus 1 is 4, 4 factorial is 24, and 24 divided by 5 leaves a remainder of 4 because it is 4 5s and 4. So the number like 5 is prime if this number equals this number. And that's all. Another example, 7. 7 minus 1 is 6, factorial 720. And 720 divided by 7 leaves a remainder of 6. And again, those two numbers are equal. So 7 is a prime number. This is also a fascinating theorem, a seemingly simple test in terms of notation. It is simple, but is highly inefficient in practice because factorials grow extremely fast. For instance, 101 factorial is an enormous number, making this method impractical for primality testing or even impossible. Another concept is the pi of n function or symbol. Here pi does not represent the number that is approximately 3.14, but rather a function that counts the number of primes less than or equal to n. So for example, pi of 3 is 2 because there are only 2 prime numbers up to 3. It is 2 and 3. Pi of 100 is 25 because there are 25 primes up to 100. There's also the prime number theorem, which states the number of prime numbers up to and including n, denoted by pi of n, is approximately n divided by natural logarithm of n. In other words, when we approximate pi of n using n divided by natural logarithm of n, the relative error tends to 0 as n increases. So the ratio of n and the natural logarithm of n, which we can compute instantly in Python, gives a very important approximation for the distribution of primes. This does not mean that pi of n and this fraction get closer in terms of absolute difference. No, because pi of 100 is 25 and this fraction is approximately 2171, and pi of 10,000 is 1229 and this fraction is 1085. So the absolute difference is smaller here. Here is much bigger. It is obvious, we see that. But though here the absolute error is smaller, but the relative error, percentage-wise, is actually larger in that case. But the prime number theorem is even stronger. Notice that the second value is always smaller, right? 21 is smaller than 25. 1085 is smaller than 2229, and in fact, precisely for n more or equal 17, an inequality holds that this approximation is smaller. It is always smaller, but for n more or equal 17, the whole inequality holds. So this is always smaller, but pi of n is also smaller than this approximation times 1.25506. So we have a range of this pi of n without calculating it. So yeah, if we want to estimate roughly how many primes there are up to a certain number, we can simply divide n by natural logarithm of n on scientific calculator, and we know that. For example, for n equal 10,000, we know that it is something between 1085 and probably 1400 without computing all the prime numbers. Now, 2 unsolved hypotheses as of today. If you ever solve one of these, you will probably become world famous. The first, one of the most important 2 hypotheses in mathematics in general, unsolved, Goldbach's hypothesis or Goldbach conjecture, is unsolved mathematical problem with a very simple formulation. Every even number greater than 2 can be expressed as the sum of 2 not necessarily distinct prime numbers. That's all. Examples: 4 is 2 plus 2, 6 is 3 plus 3, 8 3 plus 5, and 130 equals, for example, 101 plus 29. And the hypothesis says that any even number can be written as the sum of 2 prime numbers. This hypothesis has been tested programmatically using Python, for example. It is known to be true for numbers smaller than a trillion, but it is still unclear whether it is true always. And you can certainly earn a handsome sum of money for providing that it is always possible to do so, or disproving it, showing an example that there is an even number that cannot be written using the sum of two other prime numbers. And now a much more important, although more difficult, hypothesis is the Riemann hypothesis. It is perhaps the most important hypothesis in mathematics. This is an unsolved mathematical problem which states that all zeros of a certain function, the Riemann zeta function, lie either at negative even integers, called trivial zeros, or on the critical line in the complex plane where the real part is half. We haven't covered complex numbers yet. If you know what they are, it will be easier for you to understand the hypothesis. A full course on them could be made. I really like them, so maybe one day, tell me if you want such a course. The Riemann zeta function formula is this. Whatever it means, we know that we can write those elements of this infinite series, plugging in numbers 1, 2, 3, etc. for n, right? We know that. And the big mystery is we don't know whether all the zeros, so as complex numbers, gives 0 for that function if only the real part equals to a half, right? Even if you don't fully grasp the math here, it doesn't matter. We are not going to solve the Riemann hypothesis now, because all mathematicians combined, most much better mathematicians than me, professors of mathematics, can't tell if it's true. But we know that it's very important. Namely, if the Riemann hypothesis is true, then the value of the prime counting function pi of n can be approximated with much greater accuracy. Moreover, for every number x more or equal to, if the Riemann hypothesis is true, there is always at least one prime number p in the interval x minus 4 divided by p times square root of x times natural logarithm of x, p and x. Yeah, so in the interval of this number and this number, there is always prime number p. Here, pi is normal pi number, so approximately equals 3.14. So the first part, this greater accuracy, we remember that we used this approximation, but we see that it is not too much accurate. So for 10,000, we have 1,229 and approximation is between 1085 and maybe 1400. And with this theorem, if Riemann hypothesis is true, we can approximate this between probably 1200 and 1250, right? So this is crucial. And for the second part, if the Riemann hypothesis is true, for x equal, for example, 10,000, for x equal 10,000, it means that there must be p prime number, that it is smaller than 10,000, not equal even because 10,000 is not prime, and something like 7,900 as I recall. Intuitively, we know that this is more or less the case, but it is also a very important implication. I mean, we know that this is more or less the case for the numbers we checked, yes? Up to the millionth prime number, because we can check it with a program, but whether this is the case for very large ones, we don't know. This is the case if the Riemann hypothesis is true. And so, from the simple fact of what prime numbers are those that divide only by 1 and itself, we ended at the Riemann hypothesis, the most important unsolved problem in math, with huge consequences. And there are also many other implications of this hypothesis. Okay, see you in the next lesson. Hello, now we will talk about GCD and LCM, concepts we mostly already encountered in elementary school, but of course in a very limited way. The greatest common divisor, GCD, of 2 or more integers is the largest positive integer that divides each of them. For example, if we need to find the GCD of 140 and 180, we can list the divisors of 130, all the numbers that divide 130 and the divisors of 180, or the numbers that divide that number. Then choose the largest number that appears in both lists, and that number is 20. So the greatest common divisor of 140 and 180, the largest number that divides both without a remainder, is 20. Such a number always exists. In the worst case, it's 1. Now, the least common multiple, LCM, of 2 or more integers is the smallest number that is divisible by each of them. If we need to find the LCM of 140 and 180, this time we list the multiples, so we count by 140, 280, 420, 560, 700, 840, and so on, and the multiples of 180. And we look for the smallest number that appears in both lists, and that number is 1260. Here, too, such a number always exists, so the least common multiple of these two numbers is 1260. There's a formula that states the product of numbers a and b is equal to the product of their GCD and LCM. Using this formula, it is enough to compute only one of the values, either LCM or GCD, mostly GCD, and the other can be found automatically. And for our example, we could calculate GCD, it is 20, and then automatically use the transformed formula, one number times the other divided by GCD. We plug in our calculated GCD, simplify 120, which gives us 7, and the result is 7 times 180, which is 1260. So it's always enough to calculate one of them, and we automatically get the other. Very important note, this formula works only for the two integers. Finding the greatest common divisor or least common multiple of 3 or more numbers can be reduced to repeatedly applying the two-number version. For the GCD of 3 numbers a, b, c, we first calculate the GCD of a and b inside the inner parentheses, and then we take the GCD of that result and see, meaning we substitute the result here. Similarly for LCM. For example, if we need to find the LCM of the numbers 3, 4, and 5, the least common multiple of these 3 numbers, we first find the LCM of 3 and 4, which is 12. It is the smallest number that appears in the multiples of both 3 and 4. Then LCM of 12 and 5 is 60. In reality, we don't find GCD or LCM by listing all divisors or multiples and searching for the smallest or largest number. At least not for numbers larger than 100, because that would simply take too much time. However, there are better methods. There are 3 basic methods for finding the GCD and LCM. The listing method, we've just seen this one, is good for small numbers in quotes, because it can work for some large numbers like 1,000,000 and 2,000,000. The GCD is 1,000,000 and the LCM is 2,000,000, right? But in general, the smaller the numbers, the more practical this method is. The school or column method, this is the one most of us learned in school. You might have forgotten it, but we'll recall it now. It's good for numbers of a normal size, let's say between 100 and 10,000. And there is Euclid's algorithm. This method works well for all numbers. With this algorithm, we can always quickly find the GCD and LCM. So in principle, knowing just this third method is enough to determine GCD and LCM for any two numbers. We already know how to find the GCD and LCM of 140 and 180 by listing the divisors and multiples. In the school method, we write 140 on the left and find its smallest prime divisor, which is 2. 140 divided by 2 is 70. 70 divided by 2 is 35. The smallest number that divides 35 is 5. It is 7, and the smallest number that divides 7 is 7 because 7 is prime number, and we do the same for 180. We divide by smallest numbers that they should be always prime numbers. In fact, this order is not so important, but by performing this action just by the smallest first divisors, we are basically sure that we are performing it by first divisors at all. Because we could potentially 180 divide by 6, forgetting that 6 is not a prime number. But on the right, there should be prime numbers only. To find GCD, we mark the numbers that appear the same number of times on both sides. So 2 2s and 1 5. That is, if the second number 180 had 3 2s, we would also mark 2 of them only because we have 2 on the left. The GCD is the product of the marked numbers, so it is 2 times 2 times 5, which is equal to 20, because only these are marked in any of the columns. To find LCM, we take one of the numbers and multiply it by the unmarked numbers from the other column. So it can be 180 times 7, because 7 is unmarked on the left, or 140 and 2 3s, because 3 and 3 are not marked on the right. And we have Euclid's algorithm. It works by expressing the larger number as a multiple of the smaller one plus a remainder. So 180, it is 140 plus 40. Then we need to do the same for 140 and 40. 140 is 3 40s plus 20. 3 40 because 4 40s would be more than 140. So it is 3 40s plus 20. And again, in the next step, we take only these two numbers that appears after dot product symbol. Yes, only those numbers always. That is 40 equals to 2 20s plus 0. And that's basically it. And now the GCD is as much as the last marked value before 0, which is 20. This is the fastest method. We can't directly compute LCM using Euclid's algorithm, but we can use the formula A times B equals GCD times LCM. Interestingly, in Euclid's algorithm, we know in advance the maximum number of steps required. It does not exceed 5 times the number of digits of the smaller number. For 140, it is 3 digits. The maximum steps would be 3 times 5 equals 15 steps. In reality, Euclid's algorithm can be optimized further to reduce the number of steps. If you are interested, you can find more details on Wikipedia under GCD Greatest Common Divisor. In the next lesson, we will solve a few problems. Hello, I've prepared 3 exercises here to review the GCD and the LCM and a bit of prime numbers. At the same time, all these exercises come from math books, so they really do occur in real tasks. And let's move on to the first problem. The product of the 7 grades Jane has on her report card is 112,500. What grades are these? So, exercise 1. We have 7 grades. Let's name them from A to G. And the product of them is 112,500. And we assume that grades are from 1 to 6, when the 1 is the lowest grade and 6 is the best. So A, B, C, D, E, F, G are in this set 1, 2, up to 6. And normally we can't solve this. Why? Because we have 7 unknowns and only one equation. In real numbers, we wouldn't manage it. But we know these are natural numbers because they are grades and even specific natural numbers, since all these numbers up to G inclusive from A to G are from the range of 1 to 6. And how to solve this problem? Of course, there are several ways. As always, you can try to do each of these problems yourself and then just check whether you got the same answer as I did. One of the ways is to break 112,500 into prime factors, because we want factors anyway. So, we write this. Maybe more space for that. Divide by 2. It is 56,250. And divide by 2 as many times as possible. So 28,125. Now for 3, we have to check the sum of the digits. 2 plus 8 is 10, 11, 13, 15. So it is divisible by 3. Now to get 28, 9 times 3 is 27. So it will be 9, and I guess we can't do it without a calculator here, so let's open it. 28, 125 divided by 3 is 9,375. 9,375. Again, by 3, 12, 19, 24, so it is divisible by 3 again. It is 9 by 3 is 3, 3 by 3 is 1, and 75 by 3 is 25. 4, 6, 11 is not divisible by 3, the sum is not, so the number is not. So we divide it by 5, and it is, yes, I think 625, 3,125, right? By 5, 125, by 5 is 25, by 5 is 5, and by 5 is 1. So we can write that 112,500 is a product of those numbers. So 2 times 2 times 3 times 3 times 1, 2, 3, 4, 5. 5 fives. 3, 4, and 5. We have 9 numbers to 2, 2, 3, and 5 fives, and we were supposed to have 7. But this is multiplication. Some numbers we can multiply together. We can't multiply 2 and 5 because it will be 10, and 10 is not in our set. Similarly, 3 times 5 is 15, and 15 is also too much for us. But 2 times 3 is 6, and there is a grade 6. So we can multiply 2 and 3, it will be 6, and this 2 and 3, it will be 6. And then we will have 7 marks. 6 and 6 and 5 and 5 and 5 and 5 and 5. 7 marks. So we know grades that Jane has. And that's it. Okay, problem 2. Exercise 2. Calculate the GCD and LCM of the numbers. It is 1,146,992 and 990. We will use the Euclidean algorithm. So we are looking for the GCD of those two numbers. And to find it, we'll write the Euclidean algorithm. So the bigger of them is equal to how many times this number fits in this one. It fits only once because 2 times this number is bigger than that. Plus some rest. So this number minus this will give us the rest. 2 minus 2 is 2. 99 minus 99 is 0, 0. And now we have 6 minus 0 is 6. And 114 minus 99 is like 115 minus 100, so it is 15. And now we will take those two numbers. So 990,990 equals to something times this number plus the remaining. And how much this fits in this number? 6 times 15 is 90,000, so it will be 6. But now we will just use the calculator. So 6 times 156,002 is, and minus 990,990, it is 50, of course with plus 54,978. 54,978. Now those two numbers, 002 is equal to 54,978 times 3, it will be more than 156,000, so it is 2. And we'll check again with the calculator. So 2 times 54978 and minus 156002 is 46,046. Now it is easier. This number is only one this plus 78 minus 46 is 32. 9 minus 0 is 9. And this is 8,000. And quickly from millions we have thousands. Now 46,046 is. And if we don't know how much the number fits in another, we can just divide it, right? So we can just write 46,046 divided by 8,932. Oh, I put 1, so again, divided by 8,932, and it is 5. And just like that, we put this number times 5 and minus this number. So it is 1,386, 1,386 and 5 here. Okay, we are going further. We are using calculator again. 8,932 divided by 1,386. It is 6. 6 times 1,386 is 8,316. And it is easy to subtract. It was 6 and 616. Now 1,386 is something times 616. It is 2, because it will be 1,200. 1,232, so we need 4, we need 5, 1,200, so it is 154, and 616 is 4 times 154, and this is exactly 616, so plus 0. And the last number before 0, or this repeated number, is 154. So GCD of those two numbers is 154. What is this for? Well, if we had a fraction, one number over another, or the one number over the other, or the other way around, so we have 114692 and 990990. Now we know that we can divide both by 154 instead of reducing by 2 and then don't know how to reduce this. We can just reduce it by 154. So it is 1,146,992 divided by 154 is 7,438. And similarly, divided by 154 is 6,435. And those fractions are irreducible, so that's the final form. Okay, exercise 3. Oh, not yet. We have to compute LCM, but it is easy because this number times this number, we can write it here, times 90990 it is the same as 154 times LCM of those numbers, right? So you just need to compute the product and divide it by 154. So LCM of those numbers is the same as 7448 times this number. Okay, so exercise 3, maybe here. Exercise number 3. We don't know what are the numbers A and B, but we know GCD and LCM of them. We can use again this type of method. So we don't know what is A, but for sure there is 2 and there is 5 in prime factors. And the same with B, because it is GCD. So there is 2, some numbers, and 5 for sure. And we know that A times B is the same as GCD A and B times LCM A and B. So A times B is 10 times 100, which is 1000. 1000 is, we can divide it by 10, by 10, and by 10. So it is 10 times 10 times 10. But we know that 2 and 5 are divisors. So A is equal to 10 times some other number. And the same with B. It is 10 times some other numbers. So like that. We can divide by 10 times 10. Let's say this way. And those numbers that we are missing in product is 10. So it is 2 times 5. So somewhere is 2, somewhere is 5. Maybe it is 2 here and 5 here. And it will be GCD of numbers 10 and LCM of numbers 100. Maybe A has 2 and 5 and LCM does not have them. Or this way. Or 5 is here and 2 is here. So we can write the answer that A equals to 2 times 5, but B equals to 2 times 5 times 2 times 5. A is equal to 2 times 5, 2 times 5, and B is equal to 2 times 5. Or A is equal to 2 times 5 times 2, but B is equal to 2 times 5 times 5. Or A is equal to 2 times 5 times 5, and B is equal to 2 times 5 times 2. And they are the only possibilities. Okay, we fit to the one page. That's great. And see you in the next lesson. Bye. Hello, now we will learn about coprimes. Two natural numbers are called coprime, not coprimes here, because coprime is the relation between two natural numbers. So two natural numbers are called coprime, relatively prime, if their only common divisor is the number 1. And examples 16 and 9, both are not primes, but they are coprime because the only common divisor between 16 and 9 is 1. Similarly, 15 and 8 and 7 and 2. It is, like always, this is a simple definition with extremely many properties and even more applications. So, numbers A and B are coprime if and only if their GCD is equal to 1. Two prime numbers are always coprime. Two consecutive natural numbers are coprime. So, 7 and 8, 8 and 9, and so on, they're always coprime. A fraction a by b, where a and b are coprime, is irreducible. For any two different natural numbers, a and b, there exist infinitely many natural numbers n such that their greatest common divisor, a plus n and b plus n, is equal 1. Maybe mark here that GCD is often written without this GCD, so it is often written as just parentheses and some numbers. And it also means GCD. But in this course we will write GCD always. A prime number is not coprime only with its multiples. So 7 is coprime with all natural numbers except 7, 14, 21, and so on. The number 1 is coprime with every positive natural number, and plus means positive natural number. In any sequence of 9 consecutive natural numbers, this is interesting, there is always at least one that is coprime with all the others. It is not the case when there are 8 consecutive natural numbers, but when there is 9 consecutive natural numbers, there is always one of them is coprime with all the others. LCM of a and b is equal a times b when the numbers a and b are coprime. This is important when we have two fractions, 1/3 and 1/7. We don't need to compute LCM to find the common denominator, but just multiply this. 3 times 7 is 21. 3 times 7 is 21. This is 7, this is 3, and it is 10. 21. Okay? Numbers a and b are coprime if and only if there exist two integers, x and y, such that the equation ax plus by is equal 1 is satisfied. So for numbers like 2 and 8 that are not coprime because they are divisible by 2, we cannot find two x and y integers that this equation is satisfied. But for coprime, it is. And if we can get 1, we can get any other number because we can do it multiple times and then get 2, 3, and so on. Numbers 2 to the power of a minus 1 and 2 to the power of b minus 1 are coprime if and only if the numbers a and b are coprime. This is what I have told you. By adding or subtracting some number of coprime numbers, we can obtain any natural number. And here we have a popular puzzle. You probably heard about it in some form. Given two containers, one 5 liters, the other 3 liters, units doesn't matter here. Is it possible to measure exactly 4 liters of water? Is it or not? The containers have no markings, so we need to use the whole container. And we can spot that 5 and 3 are coprime, so we should, maybe it's not the case because we cannot exceed 8 liters here, but we should get every number from 1 to 8. And we can draw this, so we have 5 liters here and 3 liters here. And we can pour water here to the full container and pour this water here, so it will be 3 liters here, 3 liters, and this container will be empty. So we have the situation like here is 3 liters of water. The whole container is 5 liters, and we have the second container, 3 liters, and we can again pour this container fully, and it will be, and we can again pour this water here, so we can only pour 2 liters, right? It will be full 5 liters, and here will stay 1 liter because we pour 2 liters here. After that, we can pour out this water, so we have clean 5 liters here. and we have 1 liter here. We pour this water here. We have 5 liters container and filled with 1 liter. The other container we pour with water 3 liters and pour it here, and then we will have this 1 liter and those 3 liters, so it is 4 liter. Okay, that's it in this lesson. See you in the next one. Hello, now we are going to learn about congruences, which I already mentioned earlier in this course. Now we will see exactly what they mean. A congruence, or modular arithmetic, is a certain relations between two integers. Namely, if number a and number b, when divided by number n, give the same remainder, then we say that a is congruent to b modulo n. When n is known, for example fixed within a problem, we briefly say a is congruent to b. So here is an example. When we divide 17 by 6, not as a fraction, we can simply write that it is 2 remainder 5. This is exactly the same as if we wrote it as a fraction in this way, like 17 divided by 6 is 2 and 5/6, right? Also 11 divided by 6, gives us remainder 5. 6 fit once in 11, so it is 1, remainder 5. Or here we can write it as 1 and 5/6. Since the remainder is the same, this 5 is the same here and here, when divided by the same number and here 6, we say that 17 and 11 are congruent to each other. That is, 17 is congruent to 11 modulo 6, meaning they give the same remainder. Or in a fraction notation, they give the same numerator in a mixed number. This works fine for positive numbers. For negative numbers, we can also consider congruences, remainders, but it's harder to write it in a fraction form. We cannot really say 1 and minus 5/6. I mean, that's not the default way, but we will focus on positive numbers in this course. And so the notation a triple equals b mod n, we read as a is congruent to b modulo n. For example, 17 is congruent to 32 modulo 3, because when divided by 3, both numbers leave the same remainder, namely 2. 17 divided by 3 is 5, remainder 2. 32 divided by 3 is 10, remainder 2. We can write it like I said, or we can write it in that notation that 17 is some numbers of 3's plus 2, 2 is the remainder, and 32 is some number of 3's plus 2 as well, and those two are reminders, right? So 17 and 32 are congruent because they have this number the same when we have 3 and 3 here. As for the word congruence, it was introduced by Gauss. It comes from Latin and it means harmony or agreement. And here it is an agreement equality of reminders, right? Reminder 2 and reminder 2. That's why we call it congruence. Now about this notation, in fact, in different books it may appear with different definitions, but they are equivalent. That is, the 3 definitions I will show now are all equivalent, but in a given textbook it may be introduced in a different way. So let's look at all 3. Numbers a and b have the same remainder when divided by n. That one we already know. Another definition, there exists an integer k such that a equals k times n plus b. We have seen this here right? This notation, 17 equals 5 times 3 plus 2, 32 equals 10 times 3 plus 2. But now we say that 17 is congruent to 32 when we can write 17 equals some k, integer k times 3 plus 32. If we can do that, those numbers are congruent to each other. So, for example, for 17 and 32, modulo 3 means that there exists k such that 17 equals k times 3 plus 32. And indeed, for k that is minus 5, k is an integer, right? So it can be negative. We have 17 equals minus 5 times 3, it is minus 15, and minus 15 plus 32 is 17. So we can write it in that way. If we can write in that way two numbers, they are congruent modulo this number, right? K times this number. Okay, this is the second definition. So if two numbers are congruent modulo the same number, then such a k exists. There is a third definition. The number a congruent to b modulo n means that a minus b and b minus a, it doesn't matter, is divisible by n without remainder. So n divides a minus b, or n divides b minus a. For example, for 17 and 32, modulo 3 means that 3 divides 17 minus 32, it's minus 15, so it really divides. And 3 divides 32 minus 17, it is also 15, but positive one. So these three equivalent definitions are commonly encountered. Each one implies the others. And now, as usual, simple thing like congruence has many properties. This is the obvious one. So 5 is congruent to 5. 7 is congruent to 7. And in fact, it doesn't matter what n equals to. It must be positive integer. Here, a, b, c, d are integers, and m and n are positive integers, so n cannot be negative or 0. If one number is congruent to another, then the second one is congruent to the first one. Transitivity. If the first is congruent to the second and the second to the third, then the first is congruent to the third. Modulo the same n. If two numbers are congruent, then if we add or subtract the same integer to both, they will still be congruent. If a is congruent to b, then multiplying both a and b by some c gives ac is congruent to bc. So they keep the same remainder. Always keep this in mind. Modulo means they have the same remainder. If a is congruent to b and c is congruent to d modulo n, then a plus or minus c is congruent to b plus minus d. Here, respectively, a plus c matches b plus d, or a minus c matches b minus d. The next property that we can multiply a by c and b by d if a is congruent to b and c is congruent to d. The most important property for us, if a is congruent to b, then raising both sides to the same positive integer power m preserves congruence. And the last property, if two numbers are congruent, modulo sum product, then we can cancel factors. You can see that normally we haven't changed this number in modulo, but if we want to divide it by a here, and a is here, we need to divide all of a's, right? To summarize, congruences can be added termwise, subtracted termwise, and multiplied termwise with the same modulus. In general, congruences cannot be divided termwise. We can see it from the 9th point, but to show it, for example, we have 4 is congruent to 12, modulo 4. Why? Because 4, when divided by 4, gives remainder 0, and 12 divided by 4 gives remainder 0. And we cannot divide it in that way that here is 1, here is 3 and modulus preserves 4. Because now 1 divided by 4 gives the remainder 1 and 3 divided by 4 gives the remainder 3. So we cannot divide in that way. So in general, we cannot divide congruences on both sides, but we can use the 9 point here, and we can add, subtract, multiply, add, and power all numbers. Alright, we will do examples in the next lesson. See you there. So, we have these 9 properties, and let's try to solve a problem. Example problem. Prove that the number 107 to the power of 95 minus 133 to the power of 37 is divisible by 10. Now, divisibility by 10. Numbers, when divided by 10, give a remainder equal to the last digit of that number, modulo 10, to the given power. In other words, 107 to the power of 95 is congruent to 7 to the power of 95. This is true specifically for modulo 10. When dividing by 10, 100, 1000, and so on, it is enough to look at the last digits, the same amount of digits as there are zeros in 10, 100, 1000. So it is enough to look at the number formed by the last few digits. For 10, only 1. Now let's see, 7 to 95 equals 7 to power of 4 to 23 times 7 to the power of 3. This is because exponents multiply, right? Here, 4 times 23 is 92, and those powers, we add them, so it is 7 to the power of 95 still. Why to do it this way? Because 7 to 4 is 2401, and the last digit is 1. So, 107 to 95 is congruent to 7 to 95 is congruent to 2401, because this is 7 to the power of 4. 223 times 7 to 3, and again we can omit those 3 digits. We only need the last digit, so that's 1. And 1 to every natural power is 1, so this is congruent to 7 to the power of 3, which is 333, so it is congruent to 3 modulo 10. So throughout, we were just checking the last digit, because we are checking the remainder modulo 10. Also, the next number, 133 to the power of 37, again we can consider 3 to the power of 37. We do the same trick, because 3 to the power of 4 is 81, so we have 1 to 9, it is 1, so the last digit is 3. And that's basically the end of the problem. How so? We were supposed to prove that the difference of those two numbers is divisible by 10. And the combination of the first, let's go back, of first and the third definition tells us if a and b have the same remainder when divided by n, in this case both powers give remainder 3 modulo 10, then it means that 10 divides their difference. So here the number modulo 10 gives remainder 3, and here the number modulo 10 gives remainder 3. This can actually be reached without modular arithmetic, just by looking at the last digit, because when you multiply 7 times 7 times 7 times 7 times 7, last digit will start to repeat, so we can predict that the last digit would be 3, but okay, it gives the same result, 3, and from modular arithmetic we know if two numbers have the same remainder, then their difference is divisible by that modulus. A note here, integers when divided by n can yield one of the remainders from 0 to n minus 1, so if dividing by 10, the remainder can be 0, 1, 2, and so on up to 9. So there are 10 possible remainders for modulo 10. Why 10? Because up to 9 n minus 1, 10 minus 1 is 9. But from 0, we include 0. That's why 10 possible reminders. That means that for any number a, we can split it into n groups. A equal to nk or nk plus 0, a equal to nk plus 1 plus 2, and so on, plus n minus 1. For example, 22 is 2 times 10 plus 2, right? When we have fixed n, every number we can present in that way. Notice when talking about reminders modulo n times k is divisible by n, so its remainder is 0. Here the remainder is 1, here the remainder is 2. And here the remainder is n minus 1, but n is also divisible by n, so remainder is minus 1, right? So n minus 1 is congruent to minus 1 modulo n. So for 10 we can write remainder 9 as minus 1. It's the same thing. That's why we can say a can be equal to 6k plus 5 or a is equal to 6k minus 1. It's the same thing, of course, if we consider k as any integer number, because 5 is congruent to minus 1 modulo 6 by this formula. N is 6, so here is 5 and here is minus 1. Or any another number as 6k plus 4, it's the same as 6k minus 2. Of course, if we talk about modulo 6, because dividing by 6 leaves remainder 4 or remainder minus 2, and so on. If that seems strange, look back at the second definition. There exists an integer k such that a equals k times n plus b. So for example, 11 is equal 1 times 6 plus 5, or 11 is equal 2 times 6 minus 1. And when we talk about reminders, congruency plus 5 and minus 1 modulo 6 is the same. And here we have the same for 5 and minus 1, so they leave the same remainder 5. Okay, that's all in this lesson. See you in the next one. Of course, you can try to solve them without using congruences. In fact, you can always do them without congruences, for example, by trying to directly calculate something like 2 to the power of 20 minus 1 here. But what we want here is to make use of the knowledge we have just gained. So let's start with exercise 1. Maybe here, exercise 1. Prove that for any non-negative integer n, the number 3 to the power of 4 to the power of n, we first need to compute 4 to the power of n plus 23 is divisible by 13. Let's check it for some small n. If n is 0, then we have 3 to the power of 4 to the power of 0 plus 23. 4 to the power of 0, everything to the power of 0 except maybe 0 is 1. So 3 to the power of 1 plus 23 is 26. And 26 is divisible by 13. So we can check n equals to 1. 3 to the power of 4 to the power of 1 plus 23. 4 to the power of 1 is 4. 3 to the power of 4 plus 23. 3 to the power of 4 is 81. Plus 23 is 106, 104. And 104 is probably 13 times something. 8, 80, yes, 8. So it is divisible by 13. For n equals to 2, this would be a problem for us, because 4 to the power of 2 is 16. 3 to the power of 16, I have no idea how much it is. And in fact, when we go to, for example, n equals 20, even computers will have problem. So we need to solve it differently. 1 important mark here that, like you see, it is 4 to the power of 2, 16, not 4 times 2, 8. Because when we have 3 to the power of 4, but everything to the power of n, then we multiply powers, right? Exponents. But when there is no this bracket, it means that we need to erase this number to this power. Okay, so what we want to use is congruences. We have this thing. Start with this. It is congruent to 3 to the power of 4 times 4 to the power of n minus 1, sorry. How is that? Because here is 4 to the power of 1, so powers add, and we have still 4 to the power of n. Why I have chosen this? Because I remember that 3 to the power of 4 is 81, and I like have 1 at the end. Like you see, I don't put mod 13 here, because we know from the exercise that this is the case, so I put it at the end, at least at the end of the line. So we have this thing, so I can write it, you know, we have times product, so we can write it with brackets. So it is 3 to the power of 4 to the power of 4 to the power of n minus 1. It's not, it is equal in fact, but even if it is equal, in congruences we put triple equality, let's say. Okay, 3 to the power of 4 is 81, so we have 81 to the power of 4 to the power of n minus 1. And we can write mod 13 here. We will go to the next line. Okay, now we need some formulas. Maybe you remember from the presentation, a to the power of m is congruent to b to the power of m if and only if a is congruent to b. Let's see, from this perspective maybe. 81 is 13, because we want to use 13, times something plus something. Probably 6, 60, 78, yes. 6 plus 3. So we can say that 81 is congruent to 3, this and this, modulo 13. Because 1 3 is divided by 13, it is 0, 3 remainder, and 81 divided by 13 is 6, 3 remainder. And now we can both sides rise to the power of 4 to the power of n minus 1. So 81 to the power of 4 to the power of n minus 1 is congruent to 3 to the power of 4 to the power of n minus 1. Okay, we have it. We have something. Let's see. We have 3 to the power of 4 to the power of n, something, 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 and then 3 to the power of 4 to the power of n minus 1. It means that when we decrease n, the remainder stays. So in fact, we can do something like that. 3 to the power of 4 times 4n minus 2 this time. Again, 3 to the power of 4, 4. Again, the same thing, 81, and so on. And we will have that it is 3 to the power of 4 to the power of n minus 2, modulo 13. And so on, and so on. And we can repeat this process until n will be 0. n minus 1, n minus 2, n minus 3, n minus 4 all have the same remainder. So at some point we will have n minus n. Modulo 13. So it is congruent to 3 to the power of 4 to the power of 0 modulo 13, which is 3 to the power of 1 modulo 13. So it is congruent to 3 to the power 3. It's congruent to 3. 3 modulo 13. Okay. Okay, and now we need to prove that this number is divisible by 13. But 23 is congruent to 10 modulo 13. I just subtracted 13 from here, and this is 10. So 3 to the power of 4 to the power of n plus 23 is congruent to 3 plus 10 modulo 13, which is congruent to 13 modulo 13. And 13 divided by 13 is 1, and remainder 0. So it is divisible. What was to be shown? Okay, the second task. Exercise 2. Determine the remainder when the number is divided by 12. It looks ugly, but it is extremely simple. 1 factorial is 1. So divided by 12, the remainder also is 1. 2 factorial is 2, so divided by 12, the remainder is 2. 3 factorial is 6, so divided by 12, the remainder is 6. 4 factorial is 24, and divided by 12, the remainder is 0, right? Because 24 is 2 times 12 plus 0. And then 5 factorial, it is 4 factorial times 5. And because this thing is divisible by 12, so the whole thing is divisible by 12. The same with 6 factorial, which is 4 factorial times 5 times 6, and so on. So, in fact, 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 100 factorial is congruent to, the remainder is 1, the remainder is 2, the remainder is 6, and all others are zeros, modulo 12. So the remainder is 9. The remainder is 9. Okay, exercise 3. Show that 2 to the power of 20 minus 1 is divisible by 31. Again, we are trying to use some exponents. For example, 2 to the power of 20. We can do it in one way, 2 to the power of 4 to the power of 5. It is 16 to the power of 5. Or 2 to the power of 20 is 2 to the power of 5 to the power of 4 in that way. And this is 32 to the power of 4. And we'll use the second one. You will see in a second why. So 2 to the power of 5 is 32, which is congruent to 32 divided by 31, modulo 31, which is congruent to minus 9, modulo 31, yeah? As, you know, 6k plus 2, 6k minus 4, or 6k plus 4, 6k minus 2, we just subtract 6, and here the similar thing, we subtracted from 32, 41, and it is minus 9. The remainder is the same. So, we can write, and this is a smaller number, right, than 32. So, we can write that 2 to the power of 20 is congruent to 2 to the power of 5 to the power of 4, modulo 41, and it is congruent to, instead of 32, we can write minus 9 to the power of 4 modulo 80, not 80, but 31. And minus 9 to the power of 2 is 81. So we can write that it is 81 times 81 modulo 41. This is easy to compute manually, but let's go deeper. 82 is divisible by 41. Again, 82 is divisible by 31. So 81 is almost divisible by 31. It needs one more. So in fact, it is congruent to minus 1. And this 81 is also congruent to minus 1 modulo 41. And this is congruent. Minus 1 times minus 1 is 1 to 1 modulo 41. So 2 to the power of 20, when divisible by 31, it gives remainder 1. And minus 1, it gives remainder 0. So 2 to the power of 20 minus 1 is congruent to 1 minus 1 modulo 41, and that is congruent to 0, so it is divisible. As you remember, we can subtract congruences, we can erase them to the same power, we can multiply them like here, and we can subtract and go to negative numbers if it is easier to compute. And fortunately, we have done it in one page, so I didn't need to scroll it. Okay, this is all in this chapter. See you in the next one. Hello, this section on combinations will be much shorter. We will now get familiar with binomial coefficient, the Newton symbol, as it is called in some places, which you might have already seen in high school. The binomial coefficient for numbers n greater or equal k greater or equal 0 is the number n choose k, defined by the formula n choose k is equal to n factorial divided by k factorial times n minus k factorial. So for example, calculate 7 choose 3. 7 choose 3, we put 7 in n place, 3 in k place. 7 minus 3 is 4, so it is 7 factorial divided by 3 factorial times 4 factorial. Now 4 factorial cancelled out with 7 factorial. That is 5 times 6 times 7 divided by 3 factorial. So it is 5 times 6 times 7 divided by 6. We cancel out 6 with 6, and it is 5 times 7, so it is 35. 7 choose 3 is 35. For n and k non-negative integers, the number n choose k is positive integer, so it is equal at least 1. Basic properties. N choose k is equal to n minus k. So, in other words, 7 choose 3 is the same as 7 minus 3 is 4, so those two are equal. 10 choose 2 is equal to 10 choose 8, and so on. N choose 0 is equal to n choose n, because n minus 0 is n, and it is equal to 1. N choose 1 and n choose n minus 1 is equal to n. So for example, 10 choose 1 is 10. We also have a recursive formula, like you see. So using it, we can compute, for example, 5 choose 2. 5 choose 2. So it is equal n minus 1, k minus 1. So it is 4 choose 1 plus 4 choose 2. 4 choose 1 is 4 because of this formula. So it is 4 plus, and we can break down 4 choose 2 again. 4 choose 2, 4 here, 2 here. 4 minus 1 is 3. 2 minus 1 is 1. So it is 3 choose 1 plus 3 choose 2. Without the fraction. 3 choose 2. Again, 3 choose 1 is 3. 4 plus 3. And 3 choose 2 by this formula, it is the same as 3 choose 1. So it is 3 and it is 10. So 5 choose 2 is 10. So it is not a convenient method to compute binomial coefficients, but it can be useful in some proofs. The next one, n choose k, it is n times n minus 1 times up to n minus k plus 1 divided by k factorial 1 times 2 times 3 times k. We have seen it. In this case, 7 choose 3, it is 7 factorial 3 factorial 4 factorial, and 7 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7. 4 factorial is 1 times 2 times 3 times 4. This cancel out and we can put it in reverse order, so it is 7 times 6 times 5 divided by 1 times 2 times 3. So here is 1 times 2 times up to k, and here is 7, 6, 5, and so on, up to n minus k plus 1. 7 minus 3 is 4, plus 1 is 5. So we can always compute that in that way, that we compute the difference between 7 and 3. It is 4. We add 5 and we write 5, 6, 7 or 7, 6, 5, and this multiplication. Similarly, 10 choose 8. If this is a bigger number, we can just use this formula. So it is 10 choose 2. And again, it is 10 times 9. 10 minus 2 is 8, plus 1 is 9. So that's it. Over 1 times 2. And it is 5 times 9, so 45. Another convenient formula is n choose k is equal to n over k times n minus 1 choose k minus 1. So for 7 choose 3, it is 7 over 3 times 6 choose 2. We can use the same formula again. So it is 7 over 3 times 6 over 2 times 5 choose 1. And this is 5, right? 3 times 2 is 6, so it cancels out with 6. It is 7 times 5. So it is 35. And this formula is very efficient. We can go to the last formula. The sum of all n choose k from k that is equal to 0 to n always gives 2 to the power of n. For example, 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose without fraction 4 choose 4. It is 2 to the power of 4, so it is 16. We don't know how much each of these elements is, but there will be 16 in total. So now, why is this binomial coefficient called the binomial coefficient or binomial expansion? We have those formulas that we know from high school, at least for the power of 2 and 3, right? Of course, they are up to every number, every natural number. These coefficients, 2, 3, 3, 4, 6, 4, 5, 10, 5, follow a pattern. So, basically, on the beginning, we have x to the power of this. Then we have x to the power minus 1. So 3, 2, 1, 0. It is x to the power 0, which is 1. The same with y, which is 0. And the power of y increases by 1. Yeah, the x decreases 1 by 1. And y increases 1, 2, 3, 4, 5. This is one thing. The second thing is we have always one element more than in the previous formula. Here we have 1, 2, 3, 4. I mean without those 2 that we just can write simply by x to the power 5 and plus y to the power 5. So we have 4, 3 here, only 2 here, 1 here, and 0 here. And those numbers, 2, 3, 3, and so on, they comes from those numbers. 2 choose 1 is 2. 3 choose 1 is 3. 3 choose 2 is 3. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4. And so on. 5, 10, 10, 5. The same is for situation when there are minuses, not pluses. We only have minus, plus, minus, plus, minus, plus, minus, plus. So ones plus, ones minus, and we start with a positive value. So this works for both positive and negative numbers because we have exactly the same numbers, only the sign is changing. These numbers, these all numbers, which we have here in the formulas as coefficients, can also be obtained in another way, namely using Pascal's triangle. We build Pascal's triangle like this. We start with 1 at the top, then we put ones on the edges, and every inside number is the sum of the numbers above it. So here it is 2. Here 1 plus 3 is 4, 3 plus 3 is 6. This is the situation for 0 power that I haven't written, so x plus y to the power 0 is just 1. So this is for the power 0, this is for the power 1. These are coefficients. This is power 2, 3, 4, 5, 6, and we can see that we have exactly those numbers. 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. And by the way, these are, of course, the correct results for like this. 5, 2 is, this is 0, 1, 2. So it is 10. So if we want to say how much 7 choose 3 is, 7 choose 3, we do not need to compute nothing special. We can simply have a huge Pascal triangle printed somewhere. It would be 7th line. And here is coefficient 0, 1, 2, 3. So 15 plus 20, it is 35. So we can count it also in this way. We have many ways. Okay, that's all for this lesson. See you in the next one. Hello, now we are dealing with combinations. A combination without repetition is defined as any subset of a finite set with distinct elements. Here, the order of elements in the set is not important. This not important order is especially in the set already chosen by us, meaning in the subset. Example, the combinations of the set A, B, C, D, E are: a zero-element subset is simply the empty set. A one-element subset is each of these elements A, B, C, D, E. Two-element subsets are AB, AC, AD, AE, BC, BD, BE, CD, CE, DE. And here one might wonder whether BA should also appear. No, it should not, because AB and BA are for us the same set. In combinations, the order does not matter. BB should not appear, nor AA, because we are considering combinations without repetitions. That is, we do not take the same element two times. Here, three-element subset. Again, we cannot find elements like ABA, because that would mean some element is taken twice, but these are combinations without repetition. And we also do not have CBA, the way we have ABC, because for sets, these are exactly the same set, ABC or CBA. You can compare this to having an apple, a pear, and a plum in a basket. And if someone says we have a plum and apple and a pear, so different order, it is the same thing. This is how all the 4-element sets look, and there is only one 5-element set without considering order. We can see how many sets there are of size 0, 1, 2, 3, 4, and 5. The empty set is 1, there are 5 1-element subsets, 10 2-element subsets, 10 3-element subsets, 5 4-element subsets, and 1 5-element subset. Maybe this reminds you of something, precisely of Pascal's triangle. Namely, 5 choose 0 is 1, 5 choose 1 is 5, 5 choose 2 is 10, and so on. In other words, the number of subsets of a given size in combinations is also known beforehand, exactly with the help of the binomial coefficient. Yes, the number of k-element combinations of an n-element set is given by the formula, and choose K. To emphasize that we are talking about k-element combinations of an n-element set, we often write CKn or CNK, and unfortunately this is not consistent. In some countries it is CKN because we read that in that way, k-element combinations of an element set. But in most countries it is CNK like here. So you need to be careful here. Also, there is known this way of writing it, CNK or again CKN. So you need to be very careful here. I will use this international way of writing it. Now a combination with repetition is defined as any subset of a finite set with distinct elements where elements in subsets may be repeated. Again, the order of elements is not important. Example, the combinations with repetitions of the 4-element set ABCD are. There will be quite a lot of them. Again, the empty set. 1-element combinations are the same as for combinations without repetition ABCD. 2-element ones are AA, AB, AC, AD, BB, BC, BD, CC, CD, DD. Again, there is no CA because AC and CA are the same set, just like apples, plums. Only now we can have apple, apple, like 2 apples, right? Here we have 3-element ones, and for 4-element ones there would be very many of them, so I'm not writing them all out. We have 1 0-element set, 4 1-element, 10 2-element, and 20 3-element. Further, we have 35 4-element combinations of the set ABCD and 56 5-element combinations of the set ABCD and so on. How come 5-element? Well, because elements may be repeated. We may have AAAAA or ABBCC, etc. So in combinations without repetition, it's not always true that K must be less than or equal to N. And in addition, the number of sets of a given size increases with size. It is not the case for combinations without repetition. And yes, again, in the case of combinations with repetition, the condition K is less or equal N does not apply. The number of K-element combinations with repetitions of an, there should be a space, of an n-element set is given by the formula. Again, it can be written as Kn or Nk, mostly it is C with dash on top of it, and that's the formula. We saw here that for 4-element set, there are 23-element subsets. Let's calculate it now. So, C, we have 4-element set, we have 3-element subsets. It is 4 plus 3, 7 minus 1 is 6, and it is 3 here. And we do not need to use this formula, we can just compute it normally. So it is 6 factorial divided by 3 factorial, 6 minus 3, 3 factorial. It is now 4 times 5 times 6 divided by 1 times 2 times 3. 2 times 3 is 6, so it is really 20. Now when to use combinations and when to use K-permutations or K-Tuples. It is easy. In combinations, the order of elements does not matter. And in fact, this is the only distinguishing mark. We may have the exact same problem, but the intention may be different, so we then use combinations, not K-permutations or K-Tuples. That is not the original rule of multiplication and addition. Example, in how many ways can we choose 2 people out of 5? Well, now it depends. If the order of people matters, in the way we choose, for example, in a game where you stand on stairs and it matters who will step on the first stair, if the order of people is important, we cannot just swap them and claim it is the same case. Then in the first place, we have to choose among 5 people. We can choose 1 of 5, that is 5 here. In the second place, on the second step of stairs, we have to choose 1 of 4 people. 5 times 4 gives 20, simply by the rule of multiplication, right? But if the order of people is not important, If we choose a delegation, someone goes to the director. 2 people, it does not matter if we say John and Anna or Anna and John. Then it is simply 5 choose 2, 5 factorial, 2 factorial, 3 factorial, 4 times 5 divided by 2, because 5 factorial divided by 3 factorial cancels, and we get 10. Notice that it is exactly half of the previous result, because for 2 people, lack of order means essentially dividing by 2, since John Anna and Anna John are the same case. Is it always dividing by 2? No. Always, if we have counted in this way, this one, and then realize we actually won it without considering the order, then it suffices not to divide by 2, but by factorial of 2. Here factorial 2, that is 2, but if we had chosen 3 people, then factorial 3. If 4 people, then factorial 4, we would need to divide by the previously obtained result. And let's write it down. Notice that the formula for combinations without repetition, n factorial k factorial n minus k factorial, is the formula for K-permutations, n factorial n minus k factorial, divided by the number of permutations of the subset itself. It means k factorial. In other words, if we choose 3 out of 10 people, but the order matters, then we have some number of possibilities called K-permutations. But if we then decide that the order does not matter, instead of counting combinations from scratch, we just divide by 3 factorial, that is 6. The result we had before we divide by 6. And conversely, if we solve the problem thinking order did not matter, we got, let's say, 55, and then realize that order actually does matter, then we simply multiply the number obtained, for example 55, by the factorial of the subset length. For example, if we chose 3 balls, elements, whatever, then times 6. If 4, then times 24, and so on. Okay, examples of when we use combinations, when order really does not matter, in those cases always does not matter, we will see in the next lesson. See you there. Hello, so we know that combinations with repetition or without repetition are used where the order does not matter. So basically where. Eurojackpot, Powerball and similar lotteries. It does not matter whether 1, 2, 3 or 3, 2, 1 comes out, and it does not matter how we marked it. It is still the same combination. It does not matter in what order we marked those numbers. And a card game, for example, Queen of Hearts, King of Spades, is the same as King of Spades and Queen of Hearts. We have them in hand. We can simply shuffle them and have the same cards. There probably is no serious game where the order of cards in the hand would matter. Probably the only such game is just War, or it is called Battle somewhere. Delegations, meaning we choose 2 people who have to go somewhere or do something. Whether it is Anna and John or John and Anna, that is exactly the same. Choosing places, I couldn't find better translation. For example, we have 3 drawers and we want to put something in any 2. So whether we choose the first drawer and then the second, or the second as first and then the first, it does not matter. We have 10 lockers in locker room and we want to open 3 of them, and it does not matter in which order we open them. Of course, what we put there does matter, and sometimes the order of things placed there. And in all other places where from the context it is clear that order does not matter. For example, forming teams, choosing side dishes for a meal, selecting exam problems, etc. So pizza with the pineapple, corn and ham is the same as pizza with corn, ham and pineapple. Likewise, if for an exam we can select tasks, exercises, for example 3 out of 10, it probably does not matter in what order we do them. And above all, choosing a subset from a set. Similarly for combinations with repetition, when from context it is clear that elements are indistinguishable. For example, distributing identical candies, only the number matters. We have 5 people, we distribute 10 candies, and it does not matter in what order we hand out the candies, everyone get 2. the same candies. Similarly, selecting ingredients for pizza when they can be repeated, like double cheese, double ham, right? Getting a certain amount using given denominations, right? If we want to make $100 using given denominations, like $1, $2, and $5, we can do it in different ways, of course, but whether we have $5 and $2, which is $7, or we have $2 and $5, which is also $7, it does not matter. It is the same $7, right? Creating teams in an RPG game, we have 5 character classes and must form a team of 4. It can be 4 mages or mage knight, mage knight. And again, order does not matter. Mage knight is the same as knight knight, mage mage. Ordering ice cream, free scoops, flavors may repeat. Order does not matter. Creating codes, as long as the code ABBC is considered the same as BBCA. On the internet you can buy digital padlocks where the order of numbers does not matter, only their presence. Okay, example. Determine how many ways we can draw 2 queens from a deck of 52 cards. Information about 52 cards is only information that this is a standard deck of cards. That Joker cannot be a queen, nor that this is not a deck for a game like Black Peter. The solution is simply drawing any 2 from 4 queens. We have 6 ways. It might seem there should be more, but if we check the justification, we can have Queen of Spades and Queen of Clubs, Queen of Spades and Queen of Diamonds, Queen of Spades and Queen of Hearts, Queen of Clubs and Queen of Diamonds, Queen of Clubs and Queen of Hearts, Queen of Diamonds and Queen of Hearts. We have 6 ways. If you think some are missing here, like Queen of Diamonds and Queen of Spades, but that is the second option indeed. So similarly, drawing 2 hearts, that would be 13 choose 2, since there are 13 hearts in a deck. Another example, determine the probability of winning the jackpot in Euro Jackpot. Probability in our course is only the number of favorable events divided by the total number of events. Solution. There is only one winning possibility. We must guess all 7 numbers. So favorable events are in total 1 event. The total number of possible outcome is 50 choose 5 times 12 choose 2, because we need to guess 5 numbers out of 50, and at the same time we need to guess 2 numbers out of 12. We calculated, it comes out 139 millions. The probability equals 1 over this number, and in percent it is about 0.0000007%. By the way, we presented here, whether for probability for this jackpot or whether for cards, with those approaches we will not do too many problems. We still need something. Namely, we need the multiplication and addition rules for combinations. And it will be in the next lesson. See you there. There is not much to say about the addition and multiplication rules in combinations because they work exactly the same as they did for the rest of combinatorics, meaning if it is AND, we multiply, if it is OR, we add. Again, we must make sure that the cases do not overlap. Usually in combinations, this condition is satisfied, but maybe we'll see one example where this is not true. And actually, let's do some examples. In how many ways can we draw 2 queens and 3 kings, or 3 queens and 2 kings? Solution. So from 4 queens we choose 2, and from 4 kings we choose 3 kings. Or from 4 queens we choose 3 queens, and from 4 kings we choose 2 kings. We see that those are basically the same products, because order in a product does not matter, so we can write it as 2 times. We already calculated 4 choose 2 in the previous lesson, it is 6, and 4 choose 3 is the same as 4 choose 1, so it is 4, and the result is 38. In how many ways can we choose 3 cards from a standard 52 card deck such that we have at least 1 ace? At least 1 ace means that we are choosing 1 ace from 4 cards, And from the remaining 38 cards, not having aces, right? 52 cards minus 4 aces. From 38 cards, we choose 2 cards. And this is the part where many people get lost. It is not enough to write choosing 1 ace from 4 cards. We choose 3 cards. Choosing 1 ace from 4 cards would mean that we choose only 1 card. So, 4 choose 1 times 38 choose 2. Or from 4 aces we choose 2 and from remaining 38 cards we choose 1. Or from 4 aces we choose 3 and from remaining 38 cards we choose none. We write it down. Here you can notice that the calculation of 38 choose 2 goes very fast. It is done like that. 38 minus 2 is 36, then the next number is 37 and 38. Or another way to remember how to quickly compute this is by remembering it should be as many numbers in numerator as it says here. So 2 numbers, and now we subtract from 38. 38 times 37, and that's it because we need 2 cards. So if it is small number, simply smaller than half of this, it should be the same amount of numbers here as the button says. You don't need to write it as factorial. So the solution is 4804. Another solution for this is like thinking from 52 cards we choose any 3, except the situation where from 38 cards, that is all but aces, we choose all 3. That is a kind of subtraction rule, that from all cases we subtract those that do not fit. And this will also be 4804. Note that when we solve examples like those, we do not compute it up to the end. Usually it appears as here in golden color. Yes, when you have the answer in the scientific book or a school book, the answer is like this, not 4804. Usually there is no further calculation. Okay, probability is solved similarly. So what is the probability that from a deck of 52 cards we choose at least 1 ace? In the first case, it is the part which is in gold divided by the total number of events, and total number of events is choosing 3 cards from 52. We can see that the probability is between 1/4 and 1/5. We can do the second case as well. That is again what we see divided in golden, divided by 52 choose 3. So why it is 1 minus 38 choose 3 divided by 52 choose 3? Because when we divide by 52 choose 3, which is the total number of events, this is 1 and minus this fraction. And of course the result is the same. In other words, we can use the complementary probability. Complementary probability means from 100%, we subtract the situation we are not interested in. And we are not interested in the situation where from 38 cards we choose 3, that is all except the aces we choose 3. Next problem. What is the probability of winning in Lotto? It is also known as 6 out of 39, a lottery available in Canada, Poland, Germany and Spain, maybe in other countries too. So, what is the probability of winning in Lotto with 3 numbers, 4 numbers, 5 numbers, 6 numbers? In the game, 6 balls are chosen by the machine, the randomization machine, and we need to guess at least 3 of them. And if we guess 4, 5 or 6, we get bigger prizes. So the solution, from 6 chosen by the machine numbers, we guessed 3, but that is not all because we picked not 3 but 6 numbers. And from the remaining 33 numbers, because the lottery is 39, we choose another 3. We chose. It happened. So the probability is exactly that, divided by total number of events, that is 39 choose 6, because from 39 balls we pick 6. And it is about 1.77%. For the probability of getting 4, it is similar. From the 6 numbers we had to hit 4, and from the remaining 33 we hit 2. The probability of hitting 5 is already really low, we see it, and for the 6 is really low. And we can wonder what the probability of winning at least 3 number in Lotto is. This is of course the sum of those 4 probabilities. We can write it like this, that it is probability of hitting 3 or 4 or 5 or 6. And you can see that it is not so much more than hitting just 3 numbers. Divided by total events, that is choosing 6 balls from 49. So you can see that hitting 4, 5, or 6 are very unlike. Here also the notation is not the best because 3 minus 6 is minus 3. Here I meant the probability of winning from 3 to 6. But professionally it is written like this, where x is our event. Complementary probability, that is from 100%, we subtract the situation that 0, 1, or 2 happened, that we guessed 0, 1, or 2 balls. And it is also 1.86. As I mentioned, we will not focus much on probability in this course, so these were possibly the last examples with probability. Now let's move on. In a company, there are 5 programmers and 4 managers. We want to select a 3-person team, but at least one member must be a programmer. In how many ways can we do this? So, one way is to take 1 programmer and 2 managers, or 2 programmers and 1 manager, or 3 programmers and no managers. So the total number of ways is 80. Or by complementary, we are choosing 3 people from 9, and we only do not accept situation when we have chosen 3 managers, because managers there are 4 managers. Now let's see this situation I said on the beginning, that some cases can overlap. So in other words, let's see how the inclusion-exclusion principle works for combinations. Of course, this is a kind of inclusion-exclusion principle because we include the situation that from 9 people we choose 3 and exclude the situation that from 4 specific people we choose 3, but I mean a more complicated example. We have 10 books and 3 shelves. In how many ways can we place the books on the shelves so that no shelf remains empty? So without worrying about empty shelves, we would have, because it is combinations with repetition, 12 choose 2, 66 ways. So if we wanted to put 10 books into 3 shelves, it turns out we have 66 ways. Let's move a little higher. If one shelf is empty, then the remaining 2 must hold all the books. So we have 11 cases when the shelf is chosen. However, we can choose any of the 3 shelves to be the empty one. So in general, we have 33 possibilities of distributing the books into 2 shelves. Now when 2 shelves are empty, then all the books go into a single shelf. This is one situation. And the number of ways to choose 2 empty shelves is 3 choose 2, which is 3. It can be first and second shelf, first and third shelf, or the second and third shelf. So, using 3 shelves in any way, we have 66 ways. Using only 2 shelves, we have 33 shelves. And when using only 1 shelf, we have 3 ways. It is either one of those 3 shelves. Generally, we can put 10 books in 3 shelves. Every book can choose a shelf, and it is a combination with repetition because the order is not the matter. In 2 shelves in 33 ways, in 1 shelf in 3 ways. So the answer in general is 66 minus the situation when we considered only 2 shelves, but when we considered only 2 shelves, it may happen that all the books are in 1 shelf, so we need to plus this again, the situation when we consider 1 shelf. So in general, there are 36 possibilities, ways to put those books on the shelves. I mean when the order does not matter. If 2 books are on the shelf first, it does not matter which one goes first, which one is on the left. We only consider what books are on the shelves. And this is exactly the formula for the inclusion-exclusion principle. Maybe it is this example is complicated, so we can think about it differently. Go back here. So, one interesting note at the end, that these problems can be written in really different ways. So if we have 10 books and 3 shelves, how many ways can we place books on shelves so that no shelf remains empty? It is like the problem, how many 3-digit numbers are there such that the digits sum to 10 and none of the digits is 0? This is exactly the same problem. And I think it is much more easier to understand this. And all the solutions are here. We can read them as 118, meaning in the first shelf there is one book, on the second shelf there is one book, and on the third shelf there are 8 books. And so on. 2 books on the first shelf, 1 book on the second shelf, and 7 books on the third shelf. And here we can nicely see that our calculations were correct. There are 36 ways. So it is often nice to replace the context from the problem with another one that it is easier to understand. Okay, this was a quite complicated example. In the next lesson we will solve a few more problems, probably quite simpler ones. See you there. Hello, now let's solve some exercises. Exercise 1. From a standard deck of 52 cards, we choose 5. In how many ways can the selection be made so that, and the point A, there are exactly 3 cards of the same suit? So, we have exercise 1. And there are exactly 3 cards of the same suit. So, we could write that from the 13 cards, because there are 4 colors in cards, and there are 13 cards of each of them. So from 13 cards, we can choose 3 cards times, and from the remaining 39, we choose 2. And that's it, right? No, because that solves the problem. Another problem that it would be here. There are exactly 3 cards of the color spades or other color, right? Of the hearts. Then from 13 cards we choose 3, but we can choose 1 of 4 colors, so we can do it in 4 ways, right? We pick the color, then from this color we need 3 cards, and then from other 39, 2 other cards. Okay, the point B, there is at least 1 face card. What are face card? Jack, Queen, King, and Ace. There is at least 1 face card. It is easier to compute that there is no face card. So in our case, we want to compute that from 52 cards, we are choosing 5 cards, and subtract situations that we are having all the cards from not the face cards, right? So how many of them there are? There are 4 jacks, 4 queens, 4 kings, 4 aces. So 16, 52 minus 16 is 36. And that's the answer. Okay, something more complicated, exercise 2. Exercise 2. On a plane, n straight lines are drawn so that no 2 lines are parallel and no 3 lines intersect at a single point. How many intersection points are obtained? So we can solve it depending on n. When n is 1, so we have 1 line, like this, there are 0 intersections, right? When n is 2, we have 2 lines, and there is only 1 intersection. When n is 3, then we have how many intersections? 1, 2, 3. When n is 4, now I need to show it somehow. So let's take a look. Like here. And here. So we have 1, 2, 3, 4, 5, 6. And the last one, for now, maybe I will write it here so we have space for that. Let's recreate this image. We have something like this, this and this. And we could use the vertical line. So here. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We can write it down in a table. So we have 2 rows. here is n, and here are intersections. Inters. Okay. This is one way of doing that. Maybe I will write it. Let's write it first approach. It can be done better, but this is more obvious way for me. So, n is 1, then intersections 0. N is 2, intersection 1. N is 3, there are 3 intersections, 4, 6, 5, 10. And can we guess what will be the next numbers? Here we have this 1. This 3 is a sum of 1 and 2. The 6 is the sum of 1, 2, and 3. This 10 is the sum of 1, 2, 3, and 4. So probably it is this way, 21. However, it is, like I said, probably. We need to prove that. And we can see that for every line that we have, the next line will have one intersection more. Here was 0, here is 1, then the new line have 2 more intersections, right? And the previous n was 2. The next line must intersect all of them, so 3 of them. That's why 3. The next one needs to intersect all those 4, so plus 4. So it is correct. So now we need a formula for counting, for example, this 15, right? It is a sum from 1 to n minus 1, 5. So Sn, the summary, is 1 plus 2 plus 3 plus so on up to n minus 1. And this is arithmetic sequence, so the formula is well known. It is the first item plus the last one divided by 2 times the number of items, so it is n minus 1. This makes the formula n times n minus 1 divided by 2. But I would say that this wasn't a fully combinatoric solution. We can have a second approach, the second way of doing this exercise. So, the number of intersections is equal to, look that every 2 lines have one intersection, right? This line with this line have one intersection. This line with this line have one intersection. Every 2 lines can have only one intersection or 0, but those lines are not parallel, so we have one intersection for every 2 lines. So how many intersections is the same question as in how many ways we can choose 2 lines, a pair of lines. So in general, we have n lines and we choose 2. And that's the end of this exercise. We can see that it is n factorial, 2 factorial, n minus 2 factorial. So it is going from the next one, n minus 1 times n divided by 2. And that's all. It's the same, right? Maybe I will close this. Okay, the exercise 3 is much more complicated. How many 10-digit numbers are there such that the sum of their digits equals 5? So, for example, it is 1 to 1, 0, 0. How many 10-digit? 5, 6, 7, 8, 9, 10, right? It is 5. This is an example of the number that follows this rule. What we know is that there cannot be 6, 7, 8, or 9. Those digits can't occur because the sum of the digits would be more than 5. Okay, now we can solve each of the cases. So, when on the beginning is 5, there is only one way, right? It is a number that starts with 5 and then there are following 9 zeros. 6, 7, 8, 9. So there is exactly one way to do it. Okay. When we have 4, then the other number, the other digit must be 1. And we have 2 different cases. It can start with 4, then there is 1 somewhere here. And we have 9 places for that 1. So it is 9. And the same situation when the number starts with 1, we have 9 places to put 4. So again, 9 possibilities. So let's write here the total number. In that case, we have total 18 possibilities for numbers with only 4 and 1 and all other digits be 0. Okay, the next one could be 3 and 2. It also gives us 5. So it is the same situation, right? 3, 2, and somewhere we need to put 2, somewhere we need to put 3. So we have 2 times 9, 18. But with 3, we have other case. We can obtain 5 with 3, 1, 1. And now 3 can be on the beginning or 1 can be on the beginning. So when 3 is on the beginning, we need to choose 2 places for 1s, but the order does not matter. It does not matter if this one goes here and this one goes here, or if this one goes here and this one goes here, right? It doesn't matter. It doesn't matter which the place we will choose the first, right? So it is combinations. We have from 9 places, we need to choose 2. It doesn't matter with which order. And when D1 is on the beginning, it does matter, right? Because then we need to put 1 and 3. And if here is 3 and here is 1, it's a different situation than we have chosen 1 here and 3 here. So first we have 9 places for example, 3, and 8 places left for 1. Right? So 9 over 2 is 8 times 9 by 2. So it is 9 times 4, so it is 36. Maybe write it here that way, and 9 times 8 is 72. Okay, we haven't finished yet, so the next situation could be 2, 1, 1. No, 2, 1, 1, sorry. 2, 2, 1. So on the beginning again can be 2 or can be 1. If 1, we have the same situation as it was here with 3, because then we need to search for a place for the 2 tools. So it is 9 over 2. And we know that it is 36. And here when we have 2 on the beginning, we know that there are 9 times 8 possibilities. So 72. Yeah. The next case is 2, 1, 1, 1. And again, it can start with 2 or it can start with 1. If it starts with 2, it's easy because we need to search 3 places for 3 1s. So 9 over 3. Not over, choose. 9 choose 3. It is 7 times 8 times 9 divided by 1, 2, 3. It cancels out, so 7 times 3 is 21, times 4 is 84. But it can start with 1, then we need to search a place for the 2, there are 9 places, and we need to search 2 places for 1s, but they can be obtained in any order. So this is the answer. Let's compute that. So we have 9 times 8, choose 2. So 9 times 7 times 8 divided by 1 times 2. It is 4. So 9 times 7 is 63 times 4. It is 230 and 12, 200, maybe here, 252. It is 252. And the last one, I guess, I hope, there are 5 ones. 3, 4, 5. Then 1 need to be on the beginning. And 4 other ones can be anywhere. So from 9 places, we need to choose 4. And again, we need to compute that. 9 choose 4. It is 9 things here. 8, 7, 6. Divided by 1, 2, 3, 4. 2 times 4 is 8. This cancels out. 7 times 3 is again 21. 21 times 6, it is 126. Okay, and how many 10-digit numbers are there such that the sum of the digits equals 5? It is the sum of this column. So let's compute that in my favorite calculator, Python. 18 plus 36 plus 72 plus 72 plus 36 plus 84 plus 252 plus 126. It is 715. So the sum is 715. There are 715 numbers like that. Okay, and we need to solve the last one. Exercise 4. A tournament involves 16 teams. In how many ways we can these teams be arranged into 8 pairs? Let's see. Exercise 4. How many ways there are to arrange these teams into 8 pairs? So one pair is easy to pick, because from 16 teams we pick 2. From 16 teams we pick 2, and it does not matter in what order, right? A that is playing with team B is the same as B is playing with team A. Of course, they can be on the different places in the field, but the match is announced the same way. Okay, 16 choose 2, but then from the remaining 14 teams, we want to pick another 2. And from the remaining 12 teams, we want to choose 2. 10 choose 2. Times 8 choose 2. 8 choose 2. Times 6 choose 2. 4. And 2 choose 2, which is 1. But is it a correct answer? No. Why not? Because let's see the situation. First, we have chosen A and B, and then we have chosen C and D. And we have calculated that B and A is the same as A and B, because here the order does not matter. But here is a rule product. And in fact, we have said here that this order does matter, right? In our case, A playing with B and C playing with D is different than C playing with D and A is playing with B. Maybe that's the case. There is no information about that. If you are on an exam, you should write that you understand the problem that way, that those are different arrangements. Okay, then it's correct. But if you want to make that happen, that those are considered as the same arrangements, so this one and this one are the same, and they will not be counted twice, we should divide everything here by 2. But when we have another group, right, we can shuffle them in 6 ways, 3 factorial ways. And for 8 groups, 8 pairs, we need to divide it by 8 factorial. So this is the answer. In fact, the last one we can write, let's name it ways. How many ways? We can write it differently using the product notation with big pi notation. Because what we have, 8 factorial is 8 factorial, so we can divide by 8 factorial. But here we have everywhere 2, so it is over 2, choose 2. And here it is 2, 4, 6. We can rearrange multiplications. So in this order, 2, 4, 6, 8, 10, 12, 13, 16. So it is 2i, where I is from 1, then it is 2, to 8, then it is 16. So it is big pi notation from e equal 1 to 8. 2i choose 2 divided by 8 factorial. I would write it quite better in that way. Okay, those are the answers. I would like to check at least one of those exercises in Python, and I think the easiest will be the third one or the fourth one, so we can choose. We can solve it in Python and check if the answer is really 715, and it will be easier than computing this and checking if the number is the same. So let's do it in Python in the next lesson. See you. Okay, a few things about Python. If you want, you can do this task in another programming language. For example, let's say we would like to compute the first problem. How to do it using Python? We import from math all the important things, but the most important for us is comp. That's from combination. Namely, Python can easily calculate combinations. We can calculate 13 choose 3. Comp 13, 3, it's 286. If we want, we can calculate the first problem, part A. Of course, the formula must be derived on one's own, but the result is easily computable using the comp function. So 4 times comp 13, 3 times comp 39, 2. And that's the result. Similarly, part B, it's comp 52 choose 5 minus comp 36 choose 5. And the answer is like that. We can't do the second problem using Python. Of course, we can calculate this in Python, but we need to drive to this formula on our own. But the third problem, very much so, we can do. Although that might take us a while, we can check how long it takes. So from time import path counter, as you will remember, to check the computation time of the script. We can create a function to perform this task. Let's call this function up to 5. Def up to 5. Okay. Initially, we have how many equals 0. How many numbers there are, right? Okay, let's write start path counter. And now for each number in the interval is from the smallest number, 10-digit number is 1 and 90. So for A in range 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, we could write times or even 10 to the power of 10. But let's write it that way. And the biggest one we are considering is 5 billion. So we write 5 and then 9 zeros. 3, 4, 5, 6, 7, 8, 9. Remember that it wouldn't include the 5 itself, so we add 1. Okay, and we are going to check every one of those numbers. Let's convert it to string using str. So str is this. If a 6 appears in the string, or a 7, or an 8 or a 9, we immediately ignore those numbers. So if 6 in str a or 7 in str a, we could write it in many different ways. Let's keep it simple. Or 9 in str a, then continue. For all the remaining ones, we sum the digits, which means we need a list of digits. List of digits equals to, I will use list comprehension known in Python. There are other ways, for example, normal for loop in other languages. In str_a, list of digits we have. Now we want to have a sum of them, so sum is sum of list of digits. If sum is equal to 5, then it's our case, so how many plus equals 1, and we can print how many we have so far. Print how many and the last added number. Okay, when everything is done, we can print how many at the end. I know it should be above, but we can do it. How many? Okay, and we want to print how long did it take. So let's compute this. Stop equals proof counter, and now print. It took stop minus start. We rounded to 2 decimal places, seconds. That's how long it took. Now press enter and we can run our function. The time will be only measured from when function starts to when it finished, so it's not measuring time now. So we want to run up to 5 and I press enter. We have 294, 329, 330, and we can see that we are still on the first billion, so it will take a while. So at this point I will pause the video and we'll see how long it took and whether it will be 715. Well, now we are about to see if we counted the problem correctly. The only combination left is 5 billion. And on my machine it took 644 seconds, so over 10 minutes. If we tried to count in the same way how many 11-digit numbers have digits summing to 6, we would not get the result quickly, but we would be able to compute it by hand. Of course, the method presented here using our up to 5 function, which simply checks all possible numbers, also passing through 6, 7, 8, 9 digits and only then ignoring them, is not the best algorithm. The better one would be using recursive functions, the backtracking algorithm, but we just wanted to check that our result is correct, so it is. Okay, that's all for this lesson. Hello, now we have 4 problems exclusively connected to binomials, so let's solve them all. Exercise 5, because we last ended at exercise 4. Determine for which natural number n the inequalities are satisfied simultaneously. So we have n choose 8 is more than n choose 7. We know what does it mean, so n minus 8 is n minus 8, and we start with n minus 7 times n minus 6 times, and so on, up to n. And divided by 8 factorial, so up to 8. Is more than, and the same situation here, but we start with n minus 6. n minus 5, and so on, up to n minus 1 and n. and 7 factorial here. You can see that some terms are repeated, this whole thing, so we can divide by it, and we can consider if we really can. N minus 1 times n. Because if n is 6, this whole thing is 0, and we cannot divide by 6. The same if n is 5, 1, 0, and so on. But n is at least 8 in our case, so we can divide it. We consider only binomials where n is more or equal k. So yes, we can. It is n minus 7 divided by 8 factorial is more than, here we divided by everything, so we have only 1, and also 7 factorial. And now we can multiply everything by this factorial, so 1 times 2 times up to 8. And it is, here cancels out everything, so we have n minus 7. And here we have 1, 2 up to 7 cancels out, so we have 8 times 1, which is 8. So n must be more than 15. So at least 16. The same we do with the second condition. We have n8 is more than n9. So this we know, n minus 7 up to n, and is more than n minus 8 up to n, and here 1 times 2 times up to 9. Again, we divide by the repeated terms, so we have 1 divided by 1 times up to 8 is more than n minus 8 by 9 factorial. We multiply by 9 factorial, so everything here cancels out except 9, so it is 9 more. Here everything cancels out, so more than n minus 8. 8 on this side, and we have that 17 is more than n is less than 17, in other words. So n is more than 15, is less than 17, so n must be 16. It's natural number. In our course in mathematics, in discrete mathematics, we only consider integers numbers. So we have n equal 16. Exercise 6 maybe here. Exercise 6. Find the number n given that n choose 3 minus n choose 2 is equal to 13. So it is a problem to use the same idea. N choose 2 equals 13. So we have n minus 3, n minus 2, n minus 1 n divided by 6 minus, what have I wrote without n minus 3, of course, minus n minus 1 times n divided by 2 is equal to 13. So we can multiply by 6, and we can multiply everything, so n times n is n squared, with n is n cube, n times minus 1 is minus n cube, and minus n squared, minus 2 times n is minus 2n squared, and minus 2 times minus 1 is 2. Product with n is just 2n. And here n times n is n squared, so minus 3, because it goes like this. So it's not 3, now it is. So we have minus 3n squared, and we have minus n, so plus n plus 3n. And 13 times 6, because here nothing cancels out, so we have 60 and 24, 84. So it is n cubed minus 6n squared plus 5n minus 84. It equals 0. We look for solutions only among the divisors of the free term. That's how polynomials work. But n must be at least 3. And it can't be 3 because minus 84 will be negative. 4 the same because 4 to the power of 3 is less than 84. So 5 it can't be because it is not a divisor. So it can be 6, it can be 7, and it can be really nothing else because 8 to the power of 3 is a really big number, so it will be too much. So n is 6 or 7, we need to check. So when n is 6, it is 6 to the power of 3 is 216, minus 6 to the power of 3, in fact, is 216. 30 minus 84, it's not, so probably it is n equals to 7. 7 to the power of 3 is 333. We have this on once on the presentation. Minus 49 times 6. 50 times 6 is 300. So minus 6, 1 6 less, it is 294. Plus 30 minus 84, not 30, plus 5 times 7 is 35, minus 84. And if we compute this, it is 0. So the solution is n equals to 7, and you can check that there is no more solution. So n equals to 7. Exercise 7. Exercise 7. Prove that this is correct. And here we need a formula, mainly this formula, so recursive definition for binomial coefficient. N choose k equals n minus 1 k minus 1 plus n minus 1 k. Let's write it. So n choose k equals to n minus 1 k minus 1 plus n minus 1 k. So now we can write that. We can start with this one. 8 choose 4 equals, based on this this formula, it is 7 choose 3 plus 7 choose 4. Here is okay because we want 7 choose 3, but for 7 choose 4 we can adapt this formula again. So it is 7 choose 3 plus, and now n is 7, k is 4, so 6 choose 3. 6 choose 3 plus 6 choose 4. And again we can use this formula. So we write those two terms. And say 6 choose 4, we have 5 choose 3 plus 5 choose 4. We can see that we have those terms, right? Now again, it is not plus but equals 7 choose 3 plus 6 choose 3 plus 5 choose 3 plus 4 choose 3 and 4 choose 4. And now 4 choose 4 is just 1. It is the same as 3 choose 3. It is also 1. So it is what we had to prove. Problem 8 we'll do in the next lesson because it's quite longer. See you. Hello, since we have some time for this lesson, I've added one more problem. The 9th is simpler from those two, but both are quite complicated. Both are at university level. Exercise 8. Prove that for any natural number n more or equal 1, the number 2n choose n is divisible by n plus 1 and by 4n minus 2. So for example, if n is 5, it is 10 choose 5, then we need to prove that it is divisible by 6 and by 18. So of course we need to do it for n. And for that, we would like to use this formula, this one. N choose k equals n over k times n minus 1 choose k minus 1. So let's write it down. So exercise 8, n choose k equals n over k times n minus 1 choose k minus 1. So for us, we can put 2n here and n here. 2n choose n equals 2n divided by n is 2 times 2n minus 1 k n minus 1. Okay? Yeah, you could think if it shouldn't be minus 2 because that's what we do when we assign something for n. For example, when we assign k minus 1 n place, then it should be k minus 1 to k minus 2 because it would be 2k minus 1. But we are not substituting. We just lower the number ones here and ones here. Okay, this thing, it doesn't answer our exercise. It answers exercise 9, but we'll go back to this exercise because it is 2 times some integer, so for sure it is divisible by 2. But here we have n minus 1 and we wanted to have n plus 1. So instead of doing it that way, we will write 2n plus 1, n plus 1 equals 2n plus 1 divided by n plus 1 times 2n divided by n. And now, this integer. So this also must be an integer because it equals. So n plus 1 divides 2n plus 1, or n plus 1 divides 2n choose n, what we need. So one of them is true, at least one of them. So if we prove that this is not the case, then n plus 1 divides 2n choose n. And let's prove that n plus 1 does not divide 2n plus 1 for any n. We can compute GCD of 2n plus 1 and n plus 1. From Euclidean algorithm, we know that we can subtract from this number, right? So GCD 2n plus 1 minus in brackets n plus 1 is just n plus 1. And again we can subtract. N plus 1 minus n is n and 1. So the greatest common divisor is 1. So they are co-prime. And that means that n plus 1 does not divide to n plus 1. So let's write it. N plus 1 does not divide to n plus 1. So it must be this case. And it is exactly what we wanted to prove. Now this thing. So we can use this formula. We have 2n choose n equals 2 times 2n minus 1 n minus 1. What we want to prove is that this thing is divisible by 4n minus 2. But this equals 2 times 2n minus 1. It is obvious that this number is divisible by 2, so we only need to prove that this number, the second one, is divisible by 2n minus 1. So we need to prove that 2n minus 1 choose n minus 1 is divisible by 2n minus 1, and we can prove the bigger theorem. So theorem is that when n and k are coprimes, you remember I don't need to put GCD here, then n divides n choose k. This is our theorem and we want to prove it. If we prove it, it means that this thing is divisible by 2 and by 2 n minus 1, so divisible by 4n minus 2. So we have n choose k equals n divided by k times n minus 1 k minus 1, right? We know that k does not divide n, so it must divide this number. K divides n minus 1 k minus 1. N minus 1 k minus 1 is an integer, and when divided by k, because k divides n minus 1 choose k minus 1, it's still an integer. So it is n times some number, some large number, and this large number is in integers. We wanted to prove that n divides this, but it only means that we need to prove that n divides n times l, where l is an integer, but it is obvious. N divides n times l, and it is l. We know the result. So really, if n and k are coprimes, then n divides n choose k. So we only need to check that 2n minus 1 and n minus 1 are coprimes, because then 2n minus 1 divides this. And it is really the case, the same case, so let's check it. 2n minus 1, n minus 1, we subtract, so it is, I subtract n and minus 1, so plus 1. So it is n minus 1. Again, we subtract, this is bigger, so n minus 1, and it is GCD 1 and n minus 1, so it is 1. They are coprimes, so it is fulfilled that 2n minus 1 divides this, and 2 divides this, so 2n choose n is divisible by 4n minus 2. And that's exercise 8. Now exercise 9. We know one way to prove it. We'll just use this formula, and that's enough. 2n n equals 2 times 2n minus 1 n minus 1. This is an integer because it is always an integer. So this thing is divisible by 2. But I wrote it, this exercise 9, because there is one more way to prove it, and it is by using Pascal's triangle. So for now, let's see if n is 1, and then we have n is 1, we have 2 choose 1, which is 2, and it is divisible by 2. N equals 2, it is 4 choose 2, and it is, we have already computed it, so it is 6. N equals 3, it is 6 over 3, 6 choose 3, so it is 4 times 5 times 6 by 6, so it is 20, and so on. So let's write Pascal's triangle. Up to some point, of course. (21, 35, 35, 21, 7, 1, and maybe one more. 28, it is 56, it is 70, 56, 28, 8, 1. What we can see is that this Pascal triangle is reflected. Those numbers are on this side. there is a symmetry here, right? Numbers on the left are equal to the numbers on the right. And those numbers, what we want to check are those. This one, this one, this one, this one, and so on. And for every row, it is 2 to the power of the number of row where this is 0, right? This is this formula that 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. In total is 2 to the power of 4. So the sum of the rows are 2 to the power of the number of rows. So in 0 row we have 2 to the power of 0, it is 1. First row we have 2 to the power of 1, it is 2. Second row, first row in fact in our case, but okay, maybe do some arrows. So we have now the third, 2 to the power of 3 is 8. 4, 2 to the power of 4 is 16. 5, 2 to the power of 5 is 32. 20, 32, right. 6, 64. 7, 2 to the power of 7 is 128. And the last one, 8, 2 to the power of 8 is 256. Okay, so what we know, this is a symmetry. We are only interested in those rows. Second row, fourth row, sixth row, eighth row, and so on, right? Only in those. And in this case, what we have some one number in the middle. Maybe go here. So we have number that we want to prove that it is even, because what we want to prove is that this number, which is on the center, is even number. We have number, we have some numbers on the left, right? Some on left. We have some numbers on the right side, some on right, and it is equal 2 to the power of k. Let's write that it is even number, because 2 to every power is even, I mean started from 1. Even number. And we know that this and this thing are equal, right? So this plus this, it is 2 times something, so it is even number. So we have number plus some even number equals some other even number, right? 1 plus 4 is 5, but plus 4 plus 1, which is also 5, is 10, and it is even. So this number that we are interested in is some even number, even first, minus this even number, even 2. Even minus even, when we subtract even from even number, it is even number. And it implies that 2 divides our number. And this number was what we wanted, 2n choose n. And that is what has to be proven. So that's it. Like you see, knowing the Pascal's triangle is beneficial for us. Okay, see you in the next lesson. Hello, at the end of this chapter, let's present an important formula related to binomial coefficient or Newton's binomial. For certain m, n, and r, we have this formula. Here is a note, actually 2 notes. The first note is that this formula holds for non-natural m, n, and r, and not just for integers. Also for m being, for example, the square root of 2, n being pi or e, r being 7 because we are still summing our sigma, but also minus 7, in fact, the formula still holds. This is beyond the scope of our course, entirely outside the scope of discrete mathematics, so this is just for your information. Second note, that to prove this formula, you need to use either mathematical induction. This is certainly a part of discrete mathematics, but we will not cover it in this course. At the end, I will present this proof, as it is possible you had mathematical induction in high school. Not everywhere, but some teachers introduce it, so you can analyze this proof if you wish. Or by of so-called falling factorial, which we saw for a moment, but we didn't explore it enough, and we won't explore it in this course. So please just believe in this formula for now. And now we have example of use. 8 choose 4. It is not two numbers, but we can split it to, for example, 5 plus 3, choose 4. And now just use this formula. Here you might be surprised, because the last term will be 3 choose 4 for k equal to 0, right? It's perfectly fine to assume that when k is greater than n, the result is simply 0. So for the sum, we just plug in k equals 0, 1, 2, 3, 4. We have 5 terms. The first of them is 0 because we have 3 choose 4. And then it's quite straightforward. 5 choose 1 times 3 choose 3. We can compute all of them, and it is 70, which is exactly the same as 8 choose 4. Of course, we don't use the Vandermonde formula identity to calculate 8 choose 4 or anything like that, because it's easier and faster to do it directly anyway, because 8 choose 4 is easy to compute. Let's compute it. 8 choose 4, it is 8 factorial, 4 factorial, 4 factorial. It is from 5 times 6 times 7 times 8, 1 times 2 times 3 times 4. This eliminates, this is 2. We have 5 times 7, or 5 times 2 is 10, times 7 is 70. So it is easier to use direct computation than this formula. So we don't use and shouldn't use this formula for such cases, but I wanted to show that it works if needed, or to help you understand the notation here. Vandermonde's identity is a powerful proof tool. Many theorems related to operations on Newton's binomial or binomial coefficient, n choose k, can be proved using this formula. If ever there is a tricky problem involving binomial coefficient where something has to be proven, there is a good chance this Vandermonde's formula identity will make it possible, will make it easier. So let's do an example. Prove that n choose 0 squared, n plus 1 squared, and so on, in total is 2n choose n. You can see 2n choose n quite often. It is appearing for the third time in our course, right? The solution isn't hard, just use the formula. We apply Vandermonde's identity where for m equals n equals r. Why those numbers? Because when here is n and n, it is 2n choose n. So let's use it in that way. Applying Vandermonde's identity for m equals n equals r, we obtain on the left side what I have said. On the right side, we put m and r and n equals to n, so we have this thing. And now from this formula that is known from our first presentation in this chapter, we know that it is n choose k squared. So it is exactly n choose 0 squared plus n choose 1 squared, and so on. And that's basically the end of the proof. When can you use this again? Of course, if, for example, it would be 3n choose n, then let r be n and m be 2n. Then 3n choose 2n, naturally the left side will be completely different, but again, Vandermonde's identity can be used. Also, if there's something to prove for n plus k choose k, then m is just k and r is just k. And again, we can prove it with this identity. In reality, the applications are endless. And now, proof for those who know mathematical induction. The theorem holds for m equals n equals r equals 1, we'll prove the formula by induction with respect to m and r while n varies. So we just check n plus 1 case. Here we have used just a definition, the recursive definition for binomial coefficient. For both, we are using Vandermonde identity. Then, because here we have different numbers, r and r minus 1, so we computed this sum for k equal r. It is this, because it is m choose r times n r minus r, which is 0, so it is 1. And now we have left the same sum up to r minus 1, this sum, so we can gather them together. Then we factor out common factor, which is m choose k. We can see that this is again the definition, like we use it here. So we compact the formula, simplified it, and we have add here n plus 1 choose 0, which is 1, to show that it is really the same as here, but for n plus 1. Because now we can move it again here, because it is the next term, right? So it is not for k equals 0 to r minus 1, but to r, and we have m choose k, m plus 1, r minus k. What was to prove? So it really works for m, n, and r natural numbers. To prove it for every number, you can search it on the internet, but it's not a part of discrete mathematics, and it is a really hard thing. Okay, see you in the next chapter. Hello! With the knowledge gained from the last 3 chapters, we can now move on to a chapter on selected topics in discrete mathematics. And the first such topic will be the Dirichley's pigeonhole or box principle. Pigeonhole box principle states: if we place objects into boxes and we have more objects than boxes, then at least one box will contain at least 2 objects. This is quite a simple, even obvious fact, right? Suppose we have 4 drawers. It can be anything, a box, drawer, room, or anything like that. Yeah, so suppose we have 4 drawers, we have 5 objects, here 5 balls. If you want, we can put all the balls into one box, and then certainly one box will have more than 2 balls. But if you want to avoid this by putting one ball into each box, the last ball must go somewhere where a ball already is. So one box will contain 2 objects. As I said, this simple observation has many applications. First, a fairly simple example. Show that among 11 chosen natural numbers, you can always find at least 2 whose difference is divisible by 10. Any numbers, right? 1,000,007, 33, etc. We have 11 randomly chosen natural numbers. We know that the last digit of any natural number is one of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So every natural number has one of 10 unit digits. We have 10 boxes, here last digit, and 11 numbers. Therefore, among 11 numbers, there will be at least 2 with the same unit digit, like 23 and 173. And so, the difference of 2 numbers with the same last unit digit is a number ending with digit 0. This difference is divisible by 10, which was to be proved. Similarly, we can prove that among 11 numbers there exist at least 2 with the same last digit, alternatively giving the same remainder when divided by 10. Among 5 numbers there exist at least 2 giving the same remainder when divided by 4, because when dividing by 4 we have remainders 0, 1, 2, 3, so we have 4 remainders. So with 5 numbers, 2 fall into the same box. And generally, among n numbers, there exists at least 2 giving the same remainder when divided by n-1. But also problems with a certain context. Like in a group of 13 people, there are at least 2 who were born in the same month. We have 12 months, so for 13 people, 2 must have been born in the same month. At least 2, because all could have been born in the same month. Similarly, for 32 people, at least 2 were born on the same day of the month. For 8 people, at least 2 were born on the same day of the week. As I said, it's a simple observation, but with it you can solve very complex problems. One of them is prove that among the consecutive powers of 7, 7, 7 squared, 7 cubed, 7 to the power of 4, and so on, there exists one, probably more than one, but at least one that ends with the digits 001 in decimal representation. That is, the last 3 digits are 001. Again, we can analyze reminders of powers when divided by 1000 because those are exactly the last 3 digits. 7 is 007, 7 squared is 049, 7 cubed is 343. So there are 1000 boxes, which are the reminders when divided by 1000, being 000, 001, and up to 999. And we have 1001 powers of the number 7. Thus, there exist at least 2 numbers, 7 to the power of k and 7 to the power of l, and as a matter of fact, we can assume that k is more than l, so 7 to the power of k is more than 7 to the power of l, with the same reminder. So, 2 numbers will have the same reminder, say 555 and another 555, or something like that. The difference is 7 to the power of k minus 7 to the power of l, with l smaller, so we write 7 to the power of l, and in bracket 7 to the power of k minus l minus 1, which is divisible by 1000, because they have the same reminder for some k and l. For example, 123 and 123, subtracted one from the other gives 000 at the end, so divisible by 1000. Notice that 7 to the power of l or k or any other number are numbers built exclusively by multiplying 7s, while 1000 is made by multiplying 3 2s and 3 5s. So these 2 numbers, 7 to the power of l and 1000, are coprime. So 7 to the power of l times this bracket has last 3 digits 0 and is divisible by 1000, right? But 7 to the power of l can't be divisible by 1000, being just 7s. The greatest common divisor of 7s and 2s and 5s is 1. Therefore, 1000 must divide the bracket part, this part. So, 1000 divides 7 to the power k minus l minus 1. That means 7 to the power of k minus l minus 1 has last 3 zeros. Now, before subtracting 1, it had 2 zeros and 1 at the end. So 7 to the power of k minus l must be 001, because after subtracting 1, it is 000, right? So 7 to the power of k minus l is really 7 to some natural power, because k is bigger than l. So this statement is indeed correct. There is some, we don't know which one, but there is some natural number that 7 to this natural number gives 001 at the end. But the problem wasn't easy. The pigeonhole principle, or Dirichlet's pigeonhole principle, is simple but can solve very complex problems. And yes, typically problems for this principle involve division, last digits and such, but it is not a permanent rule. There are quite geometric problems as well, so it's always worth remembering. There exists a generalized Dirichlet's pigeonhole principle that says, if we have n boxes and more than n times k objects, then in at least one box there will be at least k plus 1 objects. For example, if we have 3 boxes and 7 objects, then in at least one box there are 3 objects. Again, an example, we have 1001 natural numbers. Prove that among them there exist at least 501 even numbers or at least 501 odd numbers. We have 2 boxes, sets, even numbers and odd numbers. The total count of numbers exceeds 500 times 2 the number of boxes. Therefore, in one of the sets, there must be at least 501 numbers. And that's it. Similarly, we can prove that among 17 chess pieces placed on a chessboard, there are at least 3 in the same row and at least 3 in the same column. Because even if you split them evenly with 8 rows, 16 pieces gives 2 per row, and the 17th has to go somewhere where there are already 2 pieces. Similarly, among 30 people, we can find at least 5 born on the same day of the week, because 7 times 4 is 28. With 28 people, each could be born on a different day of the week, meaning 4 per day, and among 29 there is a 5th person on some day at least. It is even more probably with 30 people, of course. But again, there are very complicated problems as well. For example, from the 43rd first stage mathematical Olympiad, prove that among any n plus 2 integers, there exist 2 whose sum or difference is divisible by 2n. And that's not such a simple problem. If you want to solve it, it's worth noting that among these n plus 2 integers, if there are 2 with the same remainder when divided by 2n, then their difference is divisible by 2n, so we can analyze only numbers with different remainders and see that then the sum of some pair must be divisible by 2n. As I said, this is a tougher problem. Okay, that's all for this lesson. See you in the next one. Hello, now we move to the very interesting stars and bars principle, also called dots and dividers, sticks and stones. Generally, there are many names and we can come up with new ones ourselves. So yes, it's variously named as we see, combinatorial principle that allows us to solve many counting problems, such as determining in how many ways we can place n indistinguishable balls into k distinguishable boxes, or drawers, or anything like that. What are indistinguishable balls? For example, table tennis balls. The principle is very pleasant. I would even say quite simple, easy, it's fun to use, but hard to grasp at first. And the best explanation I have ever found so far is from Wikipedia under the entry stars and bars. Most of what I will present here is an explanation and illustration of the text found there. We introduce this principle following Wikipedia, like I said, with 2 examples, the same examples as there. Theorem first. For any 2 natural numbers n and k, both more or equal 1, the number of K-Tuples or the sequences of natural numbers whose sum is n equals n minus 1, choose k minus 1. To translate this, let's do an example. Example for n equal 10 and k equal 4. This theorem gives the number of solutions to the equation x1 plus x2 plus x3 plus x4 equals 10, where x1, x2, x3, x4 are at least 1 and all natural integer numbers. It precisely gives the amount as n minus 1 choose k minus 1, so in our case we have 4 variables and the sum is 10, so it is 10 minus 1 choose 4 minus 1. Which is 9 choose 3, which is 84. We don't know what those numbers are. Examples could be 4, 3, 2, 1, the sum is 10, or 1, 1, 1, 7, etc. The sum is 10. But there are exactly 84, not pairs, but 4-element tuples, right? Let's check this right away in Python. Let's write how many equals 0, how many equals 0. For a in range from 1 to 10, without 10 of course, in fact without 9 even, but doesn't matter. Again, it is not the best form of code, but we only want to know if we counted it properly. If a plus b plus c plus d equals 10, then how many plus equal 1? And that's it. Let's check how much is how many, and indeed it is 84 solutions. The second theorem is very similar. For any 2 natural numbers n and k, the number of K-Tuples ordered sequences of natural numbers, but now with 0, whose sum is n equals k plus n minus 1, choose n. Or from a familiar formula, by computing the difference, it is k plus n minus 1, choose k minus 1, because we subtract n. Analogous example for n equal 10 and k equal 4. This theorem gives the number of solutions to the equation x1 plus x2 plus x3 plus x4 equals 10, so this is the very same equation, but now x1, x2, x3, x4 are more or equal 0, so they are non-negative, they can be 0. And that's the number of solutions, not what solutions are, but the number of them. It is k plus n minus 1, so it is 13, choose 10, and it is 286. And again, we check that we indeed get 286 solutions, that the formula is correct, at least on this example. So how many again must be 0 on the beginning? We use the same code, however, now A, B, C, D can be 0 and can be 10 because 0, 0, 0, 10 is also the solution, right? So we need to put it 11. And this means from 0 to 10. That's how it works in Python. And if ABCD equals in total 10, how many plus equal 1? And check the result, and it is 286 solutions. Keep in mind, for 50 numbers, doing this in Python could be beyond a computer's ability, even with the best approach, with the best algorithm, but we have a simple formula for it. So where is the stars and bars principle here? Well, you can prove these two theorems using the stars and bars principle, which is exactly what we will introduce now. Let's start with theorem 1, and as a matter of fact, I used dots, so it is more dots and dividers here, but you can replace dot with a star, it doesn't matter. So again, back to the first theorem. For numbers, the sum must be 10, numbers are greater than or equal to 1. Assume there are n objects, represented here by dot, which we place into k containers. So we have balls in boxes, drawers, or something like that. The containers are distinguishable, for example, by color, but the dots are not. So important is whether we have container 1, 1, 1 ball, 3 containers with 1 ball each, and in the last container is 7 balls, or in the first container is 7 and the other 3 have 1 each. But it doesn't matter how balls are arranged inside and how they are always getting mixed around, right? Configurations are therefore distinguishable only by the number of dots, balls, in each container. Each such configuration can be represented by dots and bars, where a bar indicates moving to the next container. For example, for our n equal 10 and k equal 4, one possible arrangement is: we have 10 balls, 4 boxes or containers or drawers, and we have written it like here. And notice that we have 4 containers represented by 3 lines. In the first container there are 4 balls, so x1 equals 4, 4. In the second container we have x2 equal 3, x3 equal 1, and x4 equal 2, and the sum is 10. So see that containers and balls can be presented with dots and bars, and right away it's closely related to our x1, x2, x3, x4 equation. And indeed, that plus that plus that plus that is 10. I just moved things up so it would fit. Note that no container can be empty because x1, x2, x3, x4 must be greater than or equal to 1 in the first theorem. Yeah, no containers can be empty, so there can be at most 1 bar between a pair of dots. Dots and bars uniquely define the numbers x1, x2, x3, x4 such that x1 plus and so on equals 10. We saw that. And now, how many possibilities are there for such containers with dots or such stars and bars? There are n-1 spaces between the dots, possible places for bars. Here, 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 and here. 9 places. 9 gaps between the dots. And the configuration is determined by the placement of k-1 bars. We saw it. We want 4 boxes, containers, so we put 3 bars. The order of placing the bars does not matter. It doesn't matter if we put this bar first, then this, or we started with this bar, then this and this. It's the same configuration, the same solution. That's why we have combinations of choosing k-1 bars out of n-1 positions, right? So therefore, indeed, the number of solutions is n-1 choose k-1, as the theorem said. That's exactly what dots and bars are about. Other problems we transform into considering how to put bars between dots. Similarly, the second, faster now, for any two natural numbers and k, this time they can also be 0. The sum n can be composed in so many ways. K plus n minus 1, choose n or the second one. Here the restriction is loosened to non-negative natural numbers. Non-negative means that they can't be negative but can be 0. In this case, weakening the condition to non-negative integers means that the containers will be empty. Therefore, several bars can be placed next to each other. For example, for n equal 10, k equal 4, the tuple 4, 0, 3, 3 can be represented as this. We have 4 balls in the first container, 0 balls in the second container, 3 balls in the third container, and 3 balls in the last container, which also means x1 is equal to 4, x2 is equal to 0, x3 is equal to 3, and x4 is equal to 3. And that again in total is 10. Now we want to count the ways we can put such bars. Note that each configuration contains n plus k minus 1 symbols, dots and bars. We need 10 dots and 3 bars. So n is not changed, n of them are dots, and k minus 1 are bars. Thus, we only need to choose k minus 1 out of n plus k minus 1 positions for the bars. Equivalently, choose n positions for the dots. So really, we have 13 places and need to put 3 bars in them, right? Places are like this. The first place, the second, the third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, and 13th. So it really is from 13 places. So places is n plus k minus 1, or like written here, k plus n minus 1. Choose n. It means choose 10 places for dots, or equivalently choose 3 places for bars and put dots elsewhere. By using the dots and bars principle, we should be able to solve problems of that type, and only 4 types of problems we can solve with them now. How many solutions does the equation a plus b plus c equals 100 have for ABC in natural positive or integer positive? It's the same. How many solutions does the equation a plus b plus c equals 100 when a, b, c are non-negative? In how many ways can we place 7 indistinguishable ping-pong, table tennis, balls into 3 labeled containers a, b, c? In how many ways we can place 7 indistinguishable ping-pong or table tennis balls into 3 labeled containers a, b, c again, so that no container is empty? So here how many? 99, choose 2. Here how many? 100 plus 3 minus 1 is 102, choose 2. And so on. Notice the dots and bars principle lets us count situations where the objects are indistinguishable, but the places are distinguishable. Up to now we had either both distinguishable, or at least the objects were. So the dots and bars principle can't count how many ways can 7 people be placed into 5 rooms, because people are distinguishable, rooms too after all. How many ways? It is easy to compute. The first person can pick one of 5 rooms, so 5. The second one can choose one of 5 rooms, so it is 5 to the power of 7 by the standard multiplication principle. Another problem, in how many ways can 7 people be placed into 5 rooms so that no room is empty? And you may wonder how to do this problem. The correct answer is 16,800. You may consider how to do it in Python or mathematically. Hint for mathematical solution, since 5 rooms must be occupied. Among those 7 people, you must pick 5 who will definitely go to all the different rooms, right? And then 2 people can go anywhere. Okay, that's all for this lesson. See you in the next one. Hello. For several important future topics, we'll make some theoretical preparations. This is a very difficult problem from high school, from a book with an advanced profile, and you can wonder how to solve it. When I first encountered this problem, I simply couldn't solve it, and all my ideas when carefully analyzed turned out to be wrong. So the problem is as follows. Calculate in how many ways 7 numbered balls can be placed into 5 cells numbered 1, 2, 3, 4, and 5, so that exactly 3 cells, drawers or boxes are occupied. And I will present some of my failed ideas. One was this. From 5 boxes, 5 cells, I pick 3 to which I will put balls. So 5 choose 3. And then in the first box, I put one of 7 balls. In the second, one of 6 balls. And in the third, one of 5 balls. Then for the remaining 4 balls, each can go to one of the 3 boxes, so 3 to the power of 4. That was a quick guess, but it's completely wrong, because if you want the balls done this way, so let's say we have chosen 3 places where balls should go. First ball can use one of 3 cells, not 7. We do have 7 balls, but they can go to one of 3 places, not to 7 places. So here I wrongly assume that the first of 7 balls can go to one of 7 places. But that's definitely not true. The second idea was to improve this fact. So again, from 5 I choose 3. And at the first ball goes to one of 3 containers. Those are balls, not containers. So this one, first ball can go to one of 3 places. The second one to 2 of places. The third one goes to the last place. At that point, these 3 containers are filled with at least 1 ball each. And now we can put each next ball to any container, box, or whatever. So 3, 3, 3, and 3. And it might seem that this idea is quite good. If we number the balls, it turns out it's not that good. So we have those balls, 5, 6, 7. So namely, yes, the first ball goes to one of the 3 containers, the second to one of 2, the third to the last one. And later the balls go anywhere freely. But notice the ball number 7 can't go to a container alone, because every container is already occupied, which means there is no situation where container contains 7 alone and the other 2 containers are remaining balls. So the correct answer must be larger than this number. So this thing is smaller than correct answer. And we can keep reflecting on other ideas which are wrong. Another idea I had was to arrange 7 balls and in all possible ways. So we have 3 to the power of 7. And with the stars and bars principle, we have 7 balls. We put 2 bars to divide them into 3 sections. We can do it by picking 3 places from 6, right? But then if we think more carefully, it is also wrong, because stars and bars works for not distinguishable objects, right? And in fact, in here, by 3 to the power of 7, we mean that 4, 3 here is a different solution than 3, 4, but in fact it is the same. So no, it's not a good solution. So look at the correct solution available in the book from which I took the problem. Unfortunately, I don't know what book it is. Okay, I pasted the solution. We calculate how many possibilities there are to choose 3 cells out of 5 that will be occupied. 5 choose 3, it equals 10. That part we understand. We calculate the number of possibilities for placing 7 balls in 3 cells. We have 3 to the power of 7, like here. But from this number, we must subtract the numbers corresponding to situations in which 7 balls are placed in exactly 2 of the 3 selected cells. Namely, it is 3 times 2 to the power of 7, which is 384. And add the number corresponding to the situation. All 7 balls are placed in exactly one of the 3 selected cells, 3 possibilities. Hence, the number of all possibilities of placing 7 balls in exactly 3 cells is equal to. we calculate the number of possible arrangements of the balls according to the conditions of the task as choosing 10 balls, here times number of possibilities placing 7 balls in exactly 3 cells, which is 18,060. It is correctly solved by using the Inclusion-Exclusion Principle, but I must admit I read it several times to understand what's going on here. Let's explain it briefly. So, to scatter 7 balls into 3 containers, there are 3 to the power of 7 possibilities, and that we know. It might be that all 3 containers are occupied, or all balls are in 1 or 2 containers. So we have 3 to the power 7 gives us situations like some balls are here, some balls are here, some balls are here. But also situations like most balls are here and 2 balls are here. And 3 to the power 7 gives us situations like all the balls goes to the same container, because all balls have 3 possibilities and may happen that all the balls went to this box or this cell. So 3 to the power of 7 is 7 balls in 3 containers in max, not exactly, in max 3 containers. So let's write it. 3, maybe that way. Max 3 containers are occupied. All 7 balls goes to max 3 containers, right? 7 balls go to max 3 containers. This is 3 to the power of 7. But now we calculated this and this as a correct answer, but we do not want this. So we want to subtract situations when 2 containers are occupied. So for example, this and this. So first and second, first and third, or second and third are occupied. We do not want those solutions counted. How many solutions like that are? From 3 cells, we choose 2 that will be occupied, and then, and so dot times every ball, every of 7 balls goes to 1 of 2 containers. That is how much is this case, right? Not exactly. This is how many cases like those are. Why? Because we have chosen 2 containers, right? For example, let's say we have chosen this and this, and we put 7 balls into those 2 containers, but they can go anywhere. So we also counted situations like that. So 3 to the power of 7 minus 3 choose 2 times 2 to the power of 7. And it means that, okay, we have counted those, we subtracted those situations, and maybe you think, okay, that's correct, we subtracted also this situation. Not exactly, because we have 6 possibilities. Let's see it. That we have chosen those 2 boxes and all balls goes here. We have chosen those 2 boxes and all balls goes here. We have chosen those 2 boxes and all balls goes here. We have chosen those 2 and all balls go here. And we have chosen those 2, all balls go here. And we have chosen those 2 and all balls go here. So at the first time we have counted the situation when all balls are here, all balls are here, or all balls are here. But then the situation that all balls are here, we subtracted twice, not once. So we need to add it once to make it 0. That's why we need to add to this number situations when only one is occupied, and there are only 3 situations like that. All balls are going here or here or here. And then that's the correct solution. This thing, we need to multiply it by 5, choose 3, because we have 5 cells and we have chosen 3 to analyze. Then it is 18,060. If you didn't understand the solution here, don't worry, I couldn't grasp it either. Back then, when I was studying, I definitely wouldn't have come with this solution, with this idea. Even now, it seems unnatural to me, even I understand it, why we subtract and add those numbers. I presented this problem because it can be solved much easier. For that, we need a bit of theory, but before that, let's try to solve it in Python and confirm the result. See you there. Hello, before moving on to the mathematical theory that will allow us to solve this problem simply, let's see how we might do it in Python, and we may encounter how to do it in math somehow. Up to this point, we were just checking the result in Python, and our algorithms weren't too much sophisticated. But now I would like to show you the best algorithm and how to approach to it, how to gain to this idea. So this algorithm will be the best I can imagine. At first, you might try on your own. You might come up with the idea to list all the balls. So balls are from 1 to 7. Then accepted combinations would be some type of set. Also list out all the cells. So cells are from 1 to 5, as you remember. If we did that, it would take us a very long time. So you'd have to go through each box, each cell, just pick 3 cells. So for cell 1 in cells, for cell 2 in cells, for cell 3 in cells. Of course, ensure that those cells are not equal, and with some ifs, go through all balls and put them to those cells, or go just by balls and put them in cells. However, it would be torture. Another idea, I will delete that, I had was to use a list for our balls and index where each went. So for example, we have 1, 3, 2, 2, 2, 4, 4. It is 7 balls, and each ball is represented by the index. So this is the first ball, the second ball, the third ball, the fourth ball, fifth ball, sixth ball, and seventh ball. And the number here represents to which cell the ball goes. So this ball goes to the first cell, this ball goes to the second cell, to the third cell, sorry, to the second, to the second, to the second, to the fourth, and another list would represent another situation. So for example, here, this or this, and this would be incorrect one. Why? Because we put them into 1, 2, 3, 4 different cells, and we needed to put them in 3, and now we put them in 1, 2, 3. So this is correct. So it is enough to go through all the lists from 5 ones to 7 ones, sorry, to 7 fives. 3, 4, 5, 6, 7. And in fact, you can easily do it and count only those lists that have only 3 different numbers in lists. That would be great. However, we can improve that even. It doesn't matter if we name the cells from 1 to 5, 1, 2, 3, 4, 5, or from 0 to 4, right? It is the same idea. The number of combinations would be the same, right? So we can have something like that. Go through 7 zeros to 7 fours. Now going from 7 zeros to 7 fours, we do not need a list at all, because we can go through 7 zeros, through numbers 7 zeros to 7 fours. 1, 2, 3, 4, 5, 6, 7. 7 fours. So we go like this. 7 zeros, 6 zeros 1, 6 zeros 2, 6 zeros 3, 6 zeros 4. Then we go to 6, 5 zeros, 1, 0, and so on, up to 4, 4, 4, 4, 4, 4. So we go from number 0, which can be written as such 7 zeros, to number 7 fours in base 5. How much is that? How many numbers we need to check? You know, in our decimal system, we have, for example, when we have 129, it is equal to 100 plus 2 tens plus 9 ones. And for 4, 4, 4, 4, 4, 4, 4 in base 5, it is equal to 4 times 5 to the power of. Like here, this is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 1000 would be 10 to the power of 3. So it is to the power 0, 1, 2, 3, 4, 5, 6. And this is the last number that we need to check. But here is 5, 4, 3, 2, 1, and 0. We want to compute how much is that. Let's print it. So we need to check 78,125 because 7 zeros is also a number, and in that way it's not that much, right? So we can do it. So accepted is 0, 0 accepted combinations so far. For I in range, this 7, 8, 1, 2, 4, it is the last number, so we want to count it as well. And now every number I, which is in decimal representation, we want to change into base 5 and check how many different digits there are. That's all. To change it, it would be nice to install NumPy, because NumPy has a built-in function for that. Let's go to settings. Check here in Python interpreter if you have installed NumPy. I have, but if you have not, just click this plus, search for NumPy, and install the package. Okay, so import NumPy as np, and now we want this number I, which goes from 0 to 78,124. We want to change it to a number as base 5. So number as 5, base 5, but okay. And P is base representation. This is the function or method I told you. You need to put, you see, number and base, so I and 5. For example, let's see it. For example, for 1000 in base 5, it is how much? It is 13,000. For 129, it is 1004. So, for example, I is 129, and now we have 1004. We want to have 7 digits, so let's fill 3 black digits with zeros. Yeah, and that's what we want from 7 zeros to 7 fours. So number S5 equal number S5 Z3 because it is string. Maybe padding here does the same thing. I'm not sure what is padding here, but I know that it will work. So now we have we had this thing, and now we have this one. What's the problem? The declared number is 5, define it above without usage of course. Now we want this thing, change it to a set, so set of digits, and check how many digits, different digits there are. Set will do this automatically for us. Let's scroll it. So if len of set of digits is equal 3, then we want to increase the accepted value and then print accepted value. Let's see, it is 18,060. And we can print all of them, or only accepted, but let's print all of them for now. And you can see that we are really going from 7 zeros to 7 fours. Yeah, so 7 zeros to 7 fours. And the next number after 4 is 10 in base 5. And that's how it is working. And we only count or add 1 to accepted when there are only 3 different digits. So for example, this means that the first ball went to a cell 4 or 5th cell, to the second cell, to the first cell, to the 4th cell, to the first cell, to the 4th cell, and to the second cell, because as you remember, we changed cells numbering by 1. But this is incorrect one, right? Because we have 1, 2, 3, 4 different digits here, and we only count those that have exactly 3 different digits. So let's go to one like that. Should be 10, 10 at the end. For example, we counted this one because we have 0, 1, and 4 only. So both went to 3 different cells. And yes, this is the correct and easy program, but in fact, it is slow program, a very slow program, when we would have more than 7 balls. For example, for 8 balls, it would be, we need to compute last, print last. In fact, I do not need to put it that way. I can put last here, right? But let's look how much it is. Okay, and do what I told you. Okay, and for 8 balls, it would take some time probably. Yeah. For 9 balls, it would be a disaster for us because the program would work probably a minute or something. Oh, it was 5 seconds. 5 seconds around. Quite quickly. Okay. Let's go back to this one. What I want to say that we can do it even better because we do not need to use NumPy and change representation to base 5 because Python has a built-in solution to go through all the numbers from 7 zeros to 7 fours or do just this, right? So I have prepared the second one, so it stays here, and we will see how to write it differently. From itertools, we import product, and product is the function that does exactly what we want. So accepted for now is 0, and now let's see what product does. Product for 5 different cells. It is, let's name it this way and print the list of this. So it is only 1, 2, 3, 4, 5, nothing special. But there is a repeat word here. It is not told us that there is, but let's repeat it 3 times. What we have? We have exactly what we want. It goes from 3 once, 111, 112, 113, 114, 115, and then goes to 1 to 1. Of course, we can go from 0 to 4 or from 1 to 5. Maybe let's do this time from once, as it is in exercise, to 3 5s. And when we repeat it, not 3 times, but 7 times, it goes to 7 5s from 7 1s, but probably we can't see that. Okay, so the only thing is to go through all of those lists and count those ones that we want to accept. So maybe we can even shorten this more. For every shuffle, I'm not sure if it is a correct word for what we are doing. For shuffle in those tuples, if len of set, again we are changing it to set, so repetition will be cut off, set of current shuffle. If it is 3, we want to accept that. And print how much we accepted. That's all. Some simple program. And now when we change it to 9, we have seen that it was around 5 seconds for the first approach. It will take us much quicker, around 2 seconds, right? I think this is the best approach we could use. Of course, there are some libraries that can compute it without writing more than one line. But I wanted to show it that what we are really doing here is changing or writing, this, let's go back, this thing, that first ball goes to the third cell, second ball goes to the third cell, third ball goes to the second cell, fifth ball goes to the fourth cell. So what we are doing here is basically ball 1 goes to cell 3, for example. Ball 2 goes to cell 4. Ball 3 goes to cell 5. Ball 4 goes to cell 3 again. Then let's say fifth ball goes to the cell 5th. And those 2 goes to 3 and 4. And what we are doing is 7 different numbers from 1 to 7. We map them to 3 different numbers, right? And that's all. We can understand what we want to achieve mathematically, because we want to count all the possibilities that 7 numbers are mapped to 3 other numbers. So what we want to count is how many surjections like this are there. And that's all. And for that, mathematics has mechanism even faster than what we have achieved here. So let's start from the next lesson. See you there. Hello, now you'll get familiar with Stirling numbers, which let us solve problems like the ones we have seen and are simply another tool in discrete mathematics. Stirling numbers, 2 or 3. Depending on the literature, the third time is sometimes considered as a Stirling number as well. 2 or 3 types of special numbers that were studied by James Stirling. In fact, only those 2 were studied by James Stirling. Stirling numbers of the first kind denoted by the symbols. So it is denoted like n choose k, but in a square brackets, or s, n and k in parentheses, or s1 as the first kind, and k. Sometimes it's also a capital S. Nevertheless, we say n with k cycles. Sometimes in literature you can see also k cycles n, but mostly n with k cycles. So if n is 5 and k is 3, we say 5 with 3 cycles. Those numbers are defined by a recurrence relation like this. So to know, for example, 5 with 3 cycles, we need to know 4 with 3 cycles as well as 4 with 2 cycles. We haven't discussed recurrence relations formulas yet, but it's nothing scary nor difficult. This recurrence, where to know a value you need the previous one, obviously can't go on forever. So some initial results are known from the beginning. So n with n cycles is 1, n with 0 cycles is 0, 0 with 0 cycles is 1, and n with k cycles for k greater than n is always 0. To practice this Stirling recursion, let's compute 5 with 3 cycles. So we have this recursion formula here, and 5 with 3 cycles is equal to, we put everywhere where n is, we put 5, and everywhere where k is, we put 3. So it is 5 minus 1, 5 minus 1, 5 minus 1, and 3 minus 1. So it is 4 times 4 with 3 cycles plus 4 with 2 cycles. And we do not know how much is 4 with 3 cycles and 4 with 2 cycles, so we need to compute those. So again, we put for n this time 4, for k again 3, and we have 3 with 3 cycles, and we know that there is always 1. So this is 3 times 1 is 3, and we need to compute 3 with 2 cycles. 3 with 2 cycles, again, putting it n as 3, 2 as k, we have 2 times 2 with 2 cycles plus 2 with 1 cycle. And we know that 2 with 2 cycles is 1, and 2 with 1 cycle we need to compute. 2 with 1 cycle is 1 times 1 with 1 cycle, it is always 1, plus 1 with 0 cycles, and it is always 0 if n is not 0, so it is 1 plus 0. And now, once you reach a value, an integer, you can backtrack, plug 1 here, then it will be 3, so the blue part will be 3. Then the green part is 3 plus 3, so it is 6, and then we put 6 here to compute 5 with 3 cycles. So let's do that. 3 plus 3 is 6. So 5 with 3 cycles is 4 times 6, it is 24, plus 4 with 2 cycles, and we need to compute also that item. So 4 with 2 cycles, again with formula, we have 3 times 3, because 3 with 2 cycles, it was a blue part here, right? So it was 3. So it is 3 times 3 plus 3 with 1 cycle. It is 9 plus 3 with 1 cycle. And this pink part, it is 2. Again, 2 with 1 cycle was already computed. So it is 11, the yellow part. And finally, 5 with 3 cycles is 35. Note, you don't actually compute them like this. That is, you can, but there are certain properties that let you calculate them, the Stirling numbers of the first kind, faster. But I wanted to show the recursion, because for big numbers, unfortunately, you have to do it this way, or similar with recursion. Let's see the properties. First, our formula. With those conditions, constraints. Second, there are certain properties. If you have n with 1 cycle, it is always n minus 1 factorial. So we do not need to compute it with recursion. Similarly, n with n minus 1 cycles is always equal to n choose 2. n with n minus 2 cycles, it is this formula. And we could use this to compute 5 with 3 cycles, because then 5 is here and 5 minus 2 is exactly 3. And we will do that in a second. And n with n minus 3 cycles is n choose 3 times n choose 4. So sometimes we can use those formulas to compute Stirling numbers of the first kind even faster. So with this formula we can compute 5 with 3 cycles. It is equal to, we put 5 here and here. K is not used because k is equal n minus 2. So we have 3 times 5 minus 1 divided by 4 times 5 choose 3. I know 5 choose 3. We have computed this many times, but let's compute it again. So it is 4 times 5 divided by 1 times 2. So it is 20 divided by 2. So it is 10. So we have 15 minus 1 is 14 divided by 4 times 10. It is 7 here to here, and this cancels out as well. So it is 7 times 5, so it is 35. Much easier way to compute it. So in many cases you can use these shortcut formulas. Another interesting property is if p is a prime number, then p divides p with k cycles for every k between 1 and p, not including 1 and p. We have seen it because 5 is a prime number and 5 divides 35. 5 divides 5 with 3 cycles. Another interesting property, the sum of all n with k cycles for a given n is n factorial. So 4 with 0 cycles plus 4 with 1 cycle plus 4 with 2 cycles plus 4 with 3 cycles plus 4 with 4 cycles. It is 4 factorial 16. Well, we know the properties, we know how to compute, at least manually, Stirling numbers of the first kind. So what are the applications? Mainly, there are 3 of them. First, the number of ways to arrange n numbers into k cycles is n with k cycles. That's the origin of the name. Actually, they don't have to be numbers. They can be any set elements, most often numbers. They are used as coefficients in falling factorial and rising factorial expansions because those factorials have coefficients n with k cycles. And to compute other numbers like Bell numbers, like La numbers, like Stirling numbers of the second kind. We'll talk about all of them later. In this course, we won't focus on falling and rising factorials, but we can briefly show what they are. Rising factorial is the product written this way. So it's not x to n power, it is n with, let's say, head, with dash, and it is equal x times x plus 1, x plus 2, and so on. We multiply all those parentheses up to n minus 1. And falling factorial is the same, but in parentheses with a minus. That is, falling and rising factorials are polynomials. So you can see that rising factorial of 5 is just x times x plus 1, x plus 2, x plus 3, x plus 4 without x plus 5. Falling is the same with minuses. If you calculate, you will get such a polynomial. Here and here the same numbers, just different opposite sign. And it turns out those numbers 1, 10, 35, 50, 24 are first kind Stirling numbers. For example, here we have 5 with 3 cycles, right? 5 because of this, 3 because of this. 5 with 3 cycles was 35, and that's true. These coefficients, if you didn't want to expand or compute, are known from the beginning because they are Stirling numbers of the first kind. That's what they are for here. Note, some introduce first kind Stirling numbers with alternating sign, so you don't have to subtract here because they are negative themselves. For 5 with 1 cycle, it is a positive number, 5 with 2 cycles, it is negative number, and so on. In my course, as in some publications, we only count positive Stirling numbers and place the minus sign when we want to use a negative. Both approaches are essentially equivalent. But the most important use of the Stirling numbers of the first kind is, for us, the number of ways to arrange n numbers in k cycles. What does it mean to arrange n numbers in k cycles? The first lesson in this course, first real one explaining things from chapter 1, so lesson 2 I guess, as I remember, about factorials and permutations, talked about cycles. To recap, I just copied from that presentation. A cycle is any permutation of the form 1 3 2 4 3 1 4 5 5 2. This permutation consists of two disjoint cycles, one of length 2 and one of length 3. We can write it as 1, 3, 2, 4, 5, or with a circle here, but it doesn't matter. A permutation with no smaller cycle, that is one that moves all elements in a single closed loop, is itself a single cycle. So it was in the first presentation. So the first cycle is 1 goes to 3 and then 3 goes to 1, and the second, it was a cycle of the length 2, and the second cycle of the length 3, we have 2 goes to 4, 4 goes to 5, and 5 goes to 2. And this is the same, 2 goes to 4, 4 goes to 5, 5 goes to 2. That's what we talk about. And the question is, we have 5 numbers. In how many ways can we put 5 numbers into 3 cycles? Here we put them in 2 cycles, but it could be 3. The answer is 35. There are 35 ways to write 5 numbers in 3 cycles. If you want, you can write them all out. In the course, I include a program enrolling all these cycles. Instead of commas, I use spaces, doesn't matter. So, for example, the first answer means 1, 2, 3, 4, 5. So 1 goes to 1, so it is the first one, it is the same as writing 1 goes to 1, second goes to second, 3 goes to 4, 4 to 5, and 5 to 3. We have 3 cycles, 1 of the length 1, 1 of the length 1, and 1 of the length 3. Another one, for example, 22, it is like this, 1, 3. So we have 1 goes to 3, 3 goes to 1, right? 1 goes to 3, 3 goes to 1, 2 goes to 4, and 2 goes to 4, and 4 goes to 2, and 5 goes to 5. So we have 2 cycles of the length 2, and one more, 1 cycle of the length 1. That's 3 cycles. And indeed there are 35 ways. Stirling numbers of the first kind will not be used for our problem with putting balls into specific number of cells that given number of cells are occupied. It's a very interesting part of discrete mathematics, mainly related to permutations. For our problem, we will need at least the second kind of Stirling numbers and possibly the third one. But I didn't want to jump straight to the second kind without covering the first, even if they are not connected to much. But before that, let's try coding the computation of first kind Stirling numbers in Python or any other programming language to see how to code the recursion, what are the things that you need to remember coding those, and yes, see you there. Hello, now let's learn about recursion. Most often, recursion is introduced when introducing factorials. We didn't do that since Python has a built-in mechanism to compute factorials called factorial. But we could have done it, so let's do it right now. So, 5 factorial is 1 times 2 times 3 times 4 times 5, and we can program it that way. So, the factorial, the first approach is initially, the result is 1, result equal to 1. If n is 1 or n is 0, then return this result or return 1, it doesn't matter. And then when it is 5, we need to go through all the numbers from 1 to 5 and multiply them together. So for I in range from 1 to n plus 1, because we want to include n, 5, so that's how we write it in Python. Then result times equal I, and return the result. So I is 1, then I is 2, then I is 3, 4, 5, and the result increases. Let's check if this is correct. So print factorial of 5, it should be 120. And it is. And now recursion, there is a second approach to write this code. So 5 factorial is the same as 5 times 4 factorial, right? Because 4 factorial is 1 times 2 times 3 times 4, and then times 5. And 4 factorial, it is the same as 3 factorial. because 3 factorial is 1 times 2 times 3, then times 4, then times 5. We repeat this idea because 3 factorial is 3 times 2 factorial. Then 2 factorial is 2 times 1 factorial, and 1 factorial is 1. So this is 1. So 2 times 1 is 2. Then 3 times 2 is 6. 4 times 6 is 24. We have wrong number of parentheses. It should be like this. Here this way. 4 times 6 is 24, and then 5 times 24 is 120. So, recursion goes like this. You go in with deeper and deeper parentheses, and then you come out from the deepest one to outside. Let's write it out. So we have the factorial 2. The parameter is natural number. Of course, the code could be better because we could check if n is natural, if n is integer, if n is a positive number, and so on. But we want to understand the algorithm behind recursion only. So, if n is equal 1 or n is equal 0, return 1. Here, the exit condition for a recursive function should usually be right at the top. And now to compute the factorial, you need to multiply n times factorial of the number 1 less. So, we return n times factorial n minus 1. And that's it. The code is shorter. At least it is shorter. So, let's check if the answer is the same. It should be 120. And yes, it is. There are some problems with this code. For example, when you put 9000 here, it will say that recursion error, maximum recursion depth exceeded, because there is a fixed number of recursion that we can go through. And if you want to increase that number, you go to import sys and sys recursion limit. Set recursion limit. We cannot put infinite recursion, so we need to put some big number. Not debug, but I wanted to run it. And there is one more problem with exceeded the limit for integer string conversion, so set int max str digits 0. And now it works. Okay. There is another problem with this code. Not only that we need to set recursion limit for just this function, and that's not the case for the first factorial, but we see this problem that I have in my head when we program Stirling numbers of the first kind. But for now, just understand that recursion is calling function by itself. So let's recall the recursion formula for Stirling numbers of the first kind. It is nk equals to n minus 1 times n minus 1 k with k cycles plus n minus 1 k minus 1. So we have two branches of the recursion here because it should be this type of brackets because once we go here and the second we go here. And now the Stirling of the first kind and then k, it needs two parameters. If n is equal to k, then return 1. If k is 0, then return 0. If k is more than n, return 0. In fact, we can combine those two. Writing end here, it will be shorter. And then, when the initial conditions are written, we put return n minus 1 times Stirling of the first kind, n minus 1 k, plus Stirling of the first kind, n-1, k-1. And we can print our Stirling 5-3. It should be 35, as you remember. Oh, of course, not and by, but or. Sorry for that. 35. It is 35. And now we would like to compute Stirling of, for example, 50 and 30. Let's try this. And it's computed quite long, right? Probably we can't wait for the result. So let's stop it and see how this Stirling 5-3 is working and why it is so slow. So I debug this code and we have Stirling 1, 5 and 3. N is not equal to k, k is not greater than or it is not 0. Then we have this code and here it is 4 times Stirling 1, 4 and k3. And it will not execute this code yet. And it's like I said, so we go deeper, then we have 3, it is 1, and then we have n4, k3, and so on, and we go deeper and deeper as it goes back to k3 and n5. Then it will go to the second Stirling, to 4, 2. And again, it will compute those things again, even if N3 and K2 was here, was already computed. 2 and 2 was already computed. So we shouldn't go here, but it goes recursively here and then recursively here. And that's why we need to go now back to 5, 3 again. How many computations there are, you can see, and now we have it. It went down here many times, it went down here many times, then went back, and now we are at home, it will be 35. So you can see that when computing, for example, 20 and 15, it probably takes some time. 30, 15, let's check it. And yes, it can work more than a minute probably. We can wait for that. And I have a result after around half a minute. So let's check how long this function is working. So from time import perf counter, let's start counting measure the time here. Let's stop doing it here. And then print it took stop minus start, rounded to 2 decimal places, seconds. Let's check it. It took 22 seconds. And now you would like to lower the complexity of this function, forcing it to use previous values if they were already obtained. How to do it? Python has a built-in decorator for that, so we just import it from functools, import. It can be LRU cache or just cache when we do not care how many values we want to remember, and then we need to use it like this. And that's all. Now, if something was once computed, then the value will be stored and then received from the cache. It will be not computed twice the same thing. Let's check how long it will take now to compute Stirling of the first kind of 30 and 15. It took 0 seconds. And with cache, now we can compute Stirling for 300 and 200 easily. it took 1/100th of a second. So, what I wanted to show here is not a programming lesson. It is that how the recursion works. It goes deeper and deeper by definition, calls the same function, the same idea in mathematics, but with mostly smaller numbers, down to constraint, like n equals k, k equals 0 or something like that, and then it sails out. And the second thing that I wanted to mention is that when using the recursion in mathematics or in programming, it is really important to use previously computed values. And we did it in our presentation. You remember those colors, right? I haven't computed the same color twice. I've just used values that were previously computed. So those are things that it is good to remember. Okay, that's all in this lesson. We continue our introduction to Stirling numbers. We already know this. Stirling numbers of the second kind, denoted by the symbols n subset k. Right away, we more or less know what will be calculated. It's marked with a curly bracket symbol. Again, they are defined by a recurrence formula, very similar to the last one. We see that the only difference is the coefficient. Instead of n-1 for first kind Stirling numbers, we have k for second kind Stirling numbers. And we also have the same conditions, exactly the same as for the first kind. However, there's one additional condition. For first kind Stirling numbers, n cycle 1 was n-1 factorial, but here n subset 1 is 1. Again, let's see an example. Calculating 5 subset 3, that is, we will write 3 as k and break it into two cases. I won't write all the calculations now, so I use the formula that is in the right top corner. 3 here and 3 here, and 5 minus 1 is 4. I already calculated that. Again, we compute each component. 3 subset 3 is just 1. So 3 times 1 is 3. We need to compute 3 subset 2. 2 subset 2 is 1. And 2 subset 1 is 1. So it is 3. So for the green part, we have 6. So 3 times 6, it is 18. And we need to compute 4 subset 2. And for 4 subset 2, we have basically computed that already. So it's 7. So the result is 25. Yes, you can remember that Stirling numbers of the second kind are always less than or equal to Stirling numbers of the first kind. The properties are our recurrence formula. Also, when k is equal n-1, it is the same case as for Stirling numbers of the first kind. It is n choose 2. For n subset 2, we have 2 to the power of n-1 and minus 1. And n subset 3, we have this formula, and this is exactly what we just calculated. So we can calculate it with this formula. So 5 subset 3 is 3 to the power of 5 minus 1 is 4. So 3 to the power of 4. Everything will be divided by 2. Minus 2 to the power of 5 plus 1. 3 to the power of 4 is 81, minus 2 to the power of 5 is 32, plus 1, divided by 2. 81 plus 1 is 82, minus 32 is 50, divided by 2, so it is 25. So we can use this formula. But most importantly, unlike first kind Stirling numbers, there is a formula for all second kind Stirling numbers, and it is this. The formula looks complicated, or this one looks equally intimidating, but really it just looks that way. If you want, you can compute any value from this formula, but we know the value for 5 subset 3, it is 25, so it is 5 subset 3. We have I0, K3, so it is minus 1 to the power 3 minus 0 is 3 times 0 to the power of 5, but it will be 0 no matter what we have here. And yes, you can remember that here is I equal to 0 or I equal to 1. It is the same because here for 0 it will always be 0. And now minus 1 to the power I is 1. 3 minus 1 is 2 times 1 to the power of 5 divided by k minus I, so 2 factorial 1 factorial plus minus 1 to the power 3 to now 1. I is 2, so 2 to the power of 5 divided by 1 factorial 2 factorial plus, let's go here, minus 1 to the power of 0 times 3 to the power of 5, 0 factorial, and I is 3, so 3 factorial. It is equal to, this part is 0, this part is 1 times 1 divided by 2, plus this part is minus 1 times 2 to the power of 5 is 32, so minus 32 divided by 2, plus here 3 to the power of 4 is 81, so times 3 is 233, 233 divided by 6. So we have 1 divided by 2 minus 16 plus this cancels out by 3, so it is 2, and here is 81, so 81 by 2, and 81 by 2 plus 1 is 82, divided by 2 is 31, minus 16, it is 25. So you can use this formula for all n and k, say n 137, k 5, and it is easy to compute. We don't need to use recursion. And above all, there's a formula converting Stirling numbers of one kind to the another kind. So Stirling numbers of the first kind can be written as this sum, where here are used Stirling numbers of the second kind, and the same for the second kind, where here are Stirling numbers of the first kind, and the formula stays the same, only those brackets are changed. And as we said, second kind Stirling numbers are always less than or equal to the first kind. Now the most important part, what are the applications of Stirling numbers of the second kind? The number of ways to partition n element set into k non-empty subset is equal to n subset k. We won't analyze this, but the number of equivalence relations with exactly k equivalence classes that can be defined on an n element set is n subset k. Also, when calculating Bell numbers, also in the formula for converting a power, say 5 to the 7th power into falling powers or upper factorials. What matters for us basically is this. And you should already see the connection with our ultimate problem, the one we started from this section. Example, in how many ways can we place 5 distinguishable balls into 4 boxes so that each box or container contains at least one ball? Namely, the answer is 5 subset 4. Recall the formula. We use the formula, so 4 subset 4 is 1, so it is 4 plus 4 subset 3, and 4 subset 3 can be computed from the last formula, and it is 10. So in how many ways can one put 5 distinguishable balls in 4 boxes so that each has at least one? Exactly 10 ways. And these ways are as follows. We notice that there is no combination 1, 2, 3, 5, 4. Exactly the same. It is the same combination. Reordering elements in one set doesn't matter because the order of balls in a box doesn't matter. We apply this when the elements are distinguishable. The order inside a given subset does not matter. This is exactly what I've just said. And the order of the subset does not matter. So 1, 2, 3, 4 is the same as 2, 4, 3, 1. So we can reorder the subsets, boxes, containers, and it's still the same situation. With the help of the second kind Stirling numbers, we can now solve our problem. If you want, you can try to do this yourself. We will still speak about Stirling numbers of the third kind, or what are usually called Lach numbers, and only then we will solve our problem. Okay, see you in the next one. Discovered about 200 years after Stirling's death, Lach numbers are often called Stirling numbers of the third kind. Yeah, discovered by Ivo Lach in 1954, they originally allowed expressing the rising factorial using the falling factorial and vice versa. They are given by a reasonably manageable formula, like this one, and they are often written similarly to n choose k, or Stirling number of the first kind or second, but with square brackets without the upper part. It looks like a floor symbol. In mathematics, the floor function also has that L shape on both sides. So it is n minus 1 choose k minus 1 times n factorial divided by k factorial, and it is defined for n greater than or equal k greater than or equal 1. For other cases, it is either 0 or 1. Let's immediately see the fundamental application. The rising factorial can be expressed using the falling factorial, or the falling factorial can be expressed using the rising factorial. Let's see. Remember, the rising factorial for 5 is the first polynomial. The falling factorial for 5 is the second polynomial. They are the same, just different signs. If you want to write the rising factorial using the falling factorial, you just go through k equal 1, 2, 3, 4 up to 5. So we substitute. So for 1, we have 5, 1, x, 1 falling factorial, which is just x. Then k is equal to 2, it is log 5, 2, and falling factorial, it is this part, x minus 1. Then 5, 3, x minus 1, x minus 2, it is third falling factorial, and so on and so on. At the last I haven't written log 5, 5 because it is 1. And then we can compute easily log 5, 1, 5, 2, 5, 3, 5, 4. So this is that, and we expressed rising factorial in terms of the falling factorial. This application is not very important for us, but it was the original one. That's what Ivo Lach analyzed. So now, why are they called Stirling numbers of the third kind? There are several reasons. One is there is a formula connecting Stirling numbers of the first kind and the second kind, as we see. So if you want to compute Lach number 3, 2, Lach number 3, 2, it is j is equal k, which is 2, so it is 3 with 2 cycles, 3 with 2 cycles, times j is equal 2 and k is equal to, so it is 2 subset 2, plus, then j is equal 3, so we have 3 with 3 cycles, times j is equal 3, so 3 subset 2. And, okay, this is not the best bracket, but this is the formula. But that's not the only reason. Another reason is that Lach numbers have a recursive formula, almost identical to the formulas for Stirling numbers of the first kind or second kind. Again, the only difference is in the coefficient. Now it is n plus k minus 1. For Lach number n1, it is n factorial, just like for Stirling numbers of the first kind. Note, I will sometimes use this notation, sometimes that one, depending on how the formula proceeds. But most important for us is how Lach numbers are used. Applications of Lach numbers. So we know that expressing the rising factorial in terms of the falling factorial and vice versa. computing certain sums of products that involves both Stirling numbers of the first kind and Stirling numbers of the second kind. We have seen this, but above all, counting the number of ways to partition an n-element set into k non-empty linearly ordered subsets. Now, to put it in simpler words, the number k specifies how many subsets appear in the partition, but not their sizes. Just like for Stirling numbers of the first kind, 5 with 3 cycles. 3 cycles is not the length of cycles, but the number of cycles. Within each subset, the order of elements matters, while the order of the subsets themselves does not. And that's what we want to analyze and understand. Example, lag for 1 is just 4 factorial, which is 24, because there are 24 partitions of a 4-element set into one subset. Namely, they are permutations. When 1 is in front, the rest permutate. We have 6 cases, and the same for 2, 3, and 4 when it is on the beginning. So the subset is the whole set, but order matters. Now lag for 2, let's compute, that's 36. Now let's analyze. Possible partitions of 4-element set into 2 subsets are as follows. First, both subsets are of size 2, or one subset is of size 3 and one is of size 1. Let's analyze both. If both subsets are of size 2, we have 1, 2, 3, 4 and 2, 1, 3, 4 because the order in set for lag numbers only matters. The same if in the second set it is not 3, 4 but 4, 3. So we have 4. So we have 4 partitions so far. And the same if it is not 1, 2, but 1, 3, 1, 3, 2, 4, 3, 1, 2, 4, and the same for 4, 2. And the same when in the first set it is 1, 4. There is no more, because 2, 3 and 1, 4 is the same as 1, 4, 2, 3. The order of the subset themselves does not matter, only numbers in subsets. And we have the second case. So when one subset has only one element, 1, the other permutates, and there are 6 possibilities. And the same for situations where there are 2, 3, or 4 elements in a single element set. Right? When instead of 1 here there is 2, 3, or 4, then again we have 6 possibilities. So in total we have 12 here, and 6 times 4, 36 partitions. And let's compute also lag for 3. There are also 12 partitions of a 4-element set into 3 subsets. One must be 1 element, a second one must be 1 element, and the third one must have 2 elements. And there is no more. It is important to notice that partitions such as 1, 4, 2, 3 is the same as 4, 1, 2, 3, or when we put this to 3 between 1 and 4, it is the same. All are considered equal in the sense of lag numbers, so the order of sets does not matter, the order of numbers in sets does. Thus what we are really analyzing here is the number of ways to place 4 balls, in general n balls, into 3 boxes, in general k boxes, in such a way that the order of the boxes does not matter, but the order of the balls within each box does matter. And that's the difference from Stirling numbers of the second kind. In lag numbers, the order of the boxes doesn't matter, but the order of balls in a box does. In Stirling numbers of the second kind, order of boxes doesn't matter either, nor does order of balls within a box. So here for this example, it's half possibilities, because 1, 2, 3, 4 and 1, 2, 4, 3 are considered the same in Stirling numbers of the second kind, the same 1, 3, 2, 4 and 1, 3, 4, 2, and so on. So for the Stirling numbers of the second kind, those are partitions. We have 6 of them. For Stirling numbers of the second kind for subset 2, the result is 7. Since there are 4 possibilities when singleton 1-element set is 1 or 2 or 3 or 4, and the order of numbers in the second set does not matter. And when we divide it 4 numbers into 2 subsets, we have 3 possibilities. 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. So for Lach numbers, we had here 24 possibilities. And for here for 1, 2, 3, 4. And for Stirling numbers of the second kind, we have only 4. Because the order does not matter. So we divide 24, which is the number for Lach numbers, by 3 factorial, which is 6, and that's why there is 4. And for Lach numbers, we had 12 possibilities here for partitioning 4 elements to 2 subsets. And we divided by 2 factorial here, because the order for Stirling numbers of the second kind does not matter, and 2 factorial here. So we have 2 factorial times 2 factorial, which is 3. And that's why 4 plus 3 is 7. So those are very related. To remember, Stirling numbers count k subsets of n element set, with no concern for order of boxes nor for order of balls. Lach numbers and k no concern for boxes order, but order of balls in a box matters. That's now enough to solve our problem in an easy way. Maybe you have forgotten what our problem was, but we will remind it in the next lesson. See you there. Hello, we return to our task. Let's recall. Calculate in how many ways 7 numbered balls can be placed into 5 cells, numbered 1, 2, 3, 4, and 5, so that exactly 3 cells are occupied. The traditional solution, 3 to 7, is how to arrange 7 balls in 3 cells in general, but from that we must subtract the situation where the 7 balls are placed in only 2 cells. That's here, right? But then we have counted twice the case where the 7 balls are in 1 cell, and that must be added again. We calculated it here, presented it here. So from 5 cells we choose 3, multiply by that, and we have 18,060. We confirmed it programmatically, but it wasn't clear what exactly we had done. This time we will use Stirling numbers, so we will check if it is easier and if the result is the same, essentially the same. Stirling numbers of the second kind, but let's place this thing lower. See this solution here. So again, Stirling numbers of the second kind, maybe we'll use the same color this time. Or Lach numbers, both assume that boxes, cells cannot be empty. That's good, because that's what we want. So again, we choose 3 out of 5 cells. So 5, choose 3. Those 3 will be occupied. Now we multiply this and consider how to place 7 balls into 3 boxes. So we have 3 boxes, or cells, and that is essentially how to split these 7 balls into 3 sets, regardless of how many elements are in each. And these are Stirling numbers of the second kind. So this is Stirling of the second type, where n is 7, and we have 3 sets, because 3 cells. This is not the end, because we remember that in Stirling numbers of the second kind, we had that situation in the previous or previous to last presentation. We know that the order of those cells does not matter in Stirling numbers of the second kind, just as the order of the balls does not matter. And we already assumed the order of the balls does not matter, so these are not Lach numbers. For example, 1, 2, 3, 4, and 5 is exactly as 1, 2, 3, 5, and 4. We assume that, but in Stirling numbers, the arrangement of these boxes also does not matter. So these are the same, but it is not our case. We rather claim that this is not the same, this and this or this with this one, right? In first cell, we have one element. In second cell, we have one element here and here, but here 2 elements. So for us, it is different. And in Stirling numbers of the second kind, those 3 are the same. So if we want to include, in fact, those rearrangements, we need to multiply it by the number of permutations, and it is 3 factorial. And that's it. That should be the correct result. Let's check it. 5 choose 3 is like 5 choose 2, so 4 times 5 divided by 1 times 2 times. We can compute it or check it because it is constant value, so we can check it on Wikipedia. Stirling numbers of the second kind, and we have the Stirling number N7K3 is 301. It is 301, and 3 factorial is 6. So we compute that. This is 2, so it is 10 times 6. 0 times 6 is 0. 3 times 6 is 18. So in fact, it is 18,060. And now we should understand how we computed it. We have chosen 3 cells out of 5. Then we considered in how many ways we can rearrange those 7 balls in 3 sets. And we wanted to include information that those cells are not free and they cannot shuffle, and it is not the same combination. If we think that it is the same, it's just not multiplying by 6, by 3 factorial, right? And we should write it here that we think that in this exercise, positions of the cells does not matter. But I think that position of cells does matter. However, we assumed that those numbers in one cell, they can be placed anyhow, that they shuffle inside, but maybe it's not the case. Maybe those arrangements does matter, but those as well. Then we have Lach numbers. So again, we choose 3 cells out of 5, and then multiply it by Lach 7, 3, and multiply it or not by 3 factorial. It depends how we understand the problem, right? So this problem, this exercise is not precise, I would say, if 7 numbered balls that are in cells, if this order does matter or not. So if it does, then it is Lach numbers, and then we could compute it. Again, we need to check how much is Lach number 7, 3. Of course, we could use a direct formula. You can see here, additionally, Lach numbers are sometimes referred to as Stirling numbers of the third kind. That's what I have said. We have this formula, but we also have a table of values. So Lach 7, 3 is 12,600. 12,600 times 6. So it is again 10. And this thing, 0, 0. 6 times 6 is 36. 3 are going here. 6 times 2 is 12, so 15. 1. 6 times 1 is 6, so 7. So then it is 756,000. And that's all. Okay, but it was just as a matter of curiosity, some fun fact that we could understand this exercise differently and then easily compute that using Lach numbers. However, there is one more way, maybe even easier. In fact, it is the same way, but told differently. One more way to calculate this. Do you remember in programming we were checking how many lists there are that I'm not sure how it was, but we have checked from 7 ones to 7 threes or something like that. 3 is not 7. And compute only those that have exactly 3 different digits here. In other words, we were checking how many functions there are that for 7 different values, in fact, one value from the set of 7 values, but it doesn't matter. I only want to give you an idea how many functions there are that the results are from sets only from 3 possible values, right? So this is a question, how many surjections like that are there? So the number of possibilities is we need to choose, of course, 3 cells out of 5, and then times how many surjections there are that 7 balls are put into 3 sets that every cell is occupied. And this is surjection, so we want to know number of surjections. Number of surjections like that. Surjections like that. But for that, there is a special formula. So we can see it on Wikipedia. We need to go back to the Stirling numbers of the second kind. And it is mentioned somewhere here. Yes. This formula, this explicit formula, this can be derived by using inclusion-exclusion to count the surjections from n to k and using the fact that the number of such surjections is k factorial times n subset k. It's exactly what we want. So the number of surjections like that, we know how many balls and we know how many values and every value needs to be used, is just, let's check, k factorial. So 3 factorial times 7 subset 3. It's exactly the same as here, but we know now that if we can solve the problem programmatically by using those lists that we were generating, we can count them with this formula. And of course, we need to choose 3 cells out of 5. There is no matter of the order of choosing it. Okay, and that's all for this lesson. Now we have tools for solving problems like that. Let's move on to the last few lessons. Hello, we won't focus on Bell numbers or many others because knowing Stirling numbers somehow means we know Bell numbers. For now, let's write that Bell numbers, denoted by b with index n, are given by a recursive formula like this. To calculate b3, we need to first calculate b0, b1, b2, because from k equals 0 to n minus 1, we sum binomial coefficient times the corresponding Bell number. Again, the conditions of the recursive formula apply here. Here b0 equals 1, b1 equals 1. You can also remember that b2 equals 2. This is also easy. b1, 1, b2, 2. This formula can be written like here, or it can be alternatively written like this. So then from k equals 0 to n, this is easier, but then we have b n plus 1. It doesn't matter. Let's take an example and calculate b5, the fifth Bell number. According to the formula, we need to calculate 4 choose 0 times b0 plus 4 choose 1 b1 and so on up to b4. We have calculated all binomial coefficients without problem. 4 choose 0 is 1, 4 choose 1 is 4, 4 choose 2 is 6, 4 choose 3 is 4, and 4 choose 4 is 1. Now we need to calculate b2. b2 with this formula is 1 choose 0 b0 plus 1 choose 1 b1 This is 1 plus 1, so it is really 2. The same with B3. To calculate B3, we need to know how much is B0, B1, and B2, but everything is computed, 1, 1, and 2. So it is 5, 5 because 2 choose 1 is 2, and B1 is 1. Then B4, in the same way, it is 15. And when we know B2, B3, B4, we can apply those numbers to formula for B5. So it is 52. These numbers are obviously constants, so you can memorize Bell numbers. 1, 1, 2, 5, 15, and 52. B5 is always 52. As you see, they grow very fast. As I said, knowing Stirling numbers, we know Bell numbers. Look at properties. This is our formula for Bell numbers. But there is another. Namely, Bell numbers are simply sum of Stirling numbers of the second kind for given n. From that formula to calculate our B5, it is enough to calculate 5 subset 0, 5 subset 1, 5 subset 2, and so on. However, everything subset 0, not 0 subset 0, is 0. And 0 subset 0 is 1. But let's write it like it is. So it is 5 subset 0 plus 5 subset 1 plus 5 subset 2 and so on up to 5. You can see that here is n and here is n minus 1, right? Okay, so 5 subset 0, like I said, it is 0 plus 5 subset 1, everything subset 1 is 1. 5 subset 2, we have already computed it. It was 15. This is 25. I've, of course, just write it down from the table. And it is really 15 plus 25 is 40, 50, 52. As mentioned before, Stirling numbers of the first kind also have application here. And here we see it. Proper sum of Bell numbers can be presented using Stirling numbers of the first kind. We also have congruences. So, for example, calculate B8. B8 is B3 plus 5. And it congruent to B5 plus B6 modulo 3. Modulo 3. So it is not a value, it is not the result, but we know that B8 and B5 plus B6 has the same remainder when dividing by 3. And now we get to what interests us most. Applications of Bell numbers. We have mainly one application. Bell number Bn determines the number of partitions of an n-element set. So for n equals 0, it is assumed that the empty set has only one partition to the empty set. This is the same for one element set, that it is one element set, the only partition. For n equal 2, we have the partitions, the whole set, 1, 2, so there is no partition, and 1 and 2, one partition. So we have two partitions. Let's analyze an example where we can see what's going on. For n equals 3 partitions, we have 5 partitions. 1, the whole set, so there is no partition at all, but it is a partition, right? There is no partition like a line, vertical line here. 3 partitions where there is one element set and one two-element set. And 1 partition where there are 3 one-element sets. The count is 5. The Bell number, third number Bell is 5, which equals what we would calculate using Stirling numbers. Namely, here we have, it is n3, so it is Stirling number of the second kind 3 subsets 1. It is 1. Here we have 3 subsets 2. And here we have 3 subset 3, which is 1. For n equal 4, we have the partitions of the set 1, 2, 3, 4 into 15 sets. In fact, those curly braces should be also here and in many other places. I just omitted them like many authors do. We have one 4-element set. We have some partitions where there are two sets, one of the size 1 and one of the size 3, and 3 partitions with division into 2 subsets, 2 of size 2. Next, divide into 3 sets. There are 6 possibilities. And finally, divide the set into 4 sets, all singletons. These really are Stirling numbers. One partition for 4 elements, it is Stirling number for subset 1. 7 partitions into 2 subset, we computed that it was 7, right? Stirling number of the second kind for 2. And Stirling number of the second kind for 3 was 6. And only one partition of 4 subset of 4. If we go to Wikipedia on Stirling numbers of the second kind, and if we want to compute Bell numbers, that is how many partitions of an n-element set, say 5 elements there are, we just need to sum those numbers. 1 plus 15 plus 25 plus 10 plus 1. So for B8, instead of recursive calculation, we just add 1 plus 127, 966, and so on, plus 28 plus 1. That's why we don't focus on Bell numbers, because usually when we want to calculate really the Bell number, we compute sum of Stirling numbers of the second kind. Okay, and that's all for this lesson. See you in the next one. Hello, the last topic we will discuss in this course will be the Chinese remainder theorem. The Chinese remainder theorem allows for solving systems of congruences of coprime numbers. Everything will become clear shortly, but we should already be familiar with words like congruence, meaning remainders from division, and coprime numbers, meaning those that have only one common divisor, which is 1. Chinese mathematician Sun Zi solved the problem of finding integers that give remainders of 2, 3, and 2 when divided by 3, 5, and 7 respectively. So when divided by 3, they leave remainder 2, divided by 5, remainder 3, and divided by 7, remainder 2 as well. And these numbers, 3, 5, and 7, besides being prime, are above all coprime. The remainders 2, 3, 2 do not have to be coprime numbers. In various sources, Sun Zi lived at different times, spanning around 200 years, but he lived somewhere at the beginning of our era. So in other words, Sun Zi solved the problem of finding a number n that satisfies all 3 congruences at the same time. So there is a number n that divided by 3 gives remainder 2, divided by 5 gives remainder 3, divided by 7 gives remainder 2. We can solve this problem now, and we introduce the Chinese remainder theorem by solving this problem, exactly as Sun Zi came to it. Solution. To solve it, for each of these rows, meaning here for 3, division by 3, we need to calculate the product of other moduli. So 5 times 7 is 35. If there were more lines here, one would have to calculate the product of more such numbers. So n1 is 5 times 7, 35. Similarly, for the second row, for 5, we calculate the product of the others, that is 3 times 7 is 21. And the last one, for 7, 3 times 5 is 15. Next, we know that coprime numbers, that is 3, is coprime number to 5 and 7, and is also coprime to their product. So when the number is coprime with the rest of numbers, it is also coprime with their product. So 3 is coprime with 5, 3 is coprime with 7. So 3 is coprime with 35 as well. 5 is coprime with 21 and 7 is coprime with 15. So for now, we only calculate some products. And now for fixed coprime nm that are positive integers, positive natural numbers, we can find numbers a and b any integers such that an plus bm is equal to 1. This was in the lesson about coprime numbers, that coprime numbers are those whose only common divisor is 1, but also coprime number nm, positive integers, are those that we can find integers a and b that this sum is equal 1. And here our n is the given modulo number, the one we divided by, which is 3. And m is the number n1, so 35. So we want to find a1 and b1. Similarly for the second and the third row, right? So this number comes from here and this number comes from here. And the last will be 7 here and 15 here, right? Because they are coprime numbers, we can write these three equations. So for now we only computed products and we wrote those three equations. Now these equations need to be solved, which is basically always simple. Namely, we take 135 and some numbers of threes to have 1. Indeed, 12 threes is 36 and minus 135 is 1. So 12 times 3 minus 1, 35. And similarly with the others, here 4, 5 is 20, so it is easy to have 21, 121 and minus 4, 5. Right? And similarly here, because 2 sevens is 14, so it is easy to have 1. So those equations are always simple. And now we should always proceed this way. So we take those numbers that weren't involved so far at all, right? We take this number and multiply them times this part. We ignore this part, and this part. Those are ignores, and we compute the sum. This multiplied by this multiplied by this multiplied by this. So 3 times 1 times 21, and now will be 2 times 1 times 15. And it is 23. And this is the correct result. Namely, 23 divided by 3 gives the remainder 2. 23 divided by 5 gives the remainder 3, and 23 divided by 7 gives the remainder 2. Everything matches. But this is not the only result. As I mentioned, I hope, there are infinitely many results, infinitely many solutions. And how to find the others? It is also easy. Just calculate the number m, which is the product of all moduli. 3 times 5 times 7 in our case, it is 105. And all the results are 23 plus any number of 105. It can be 1, it can be 2, it can be minus 1, and so on. So n can be 23, as we checked. 23 is the answer, but 23 plus 105, which is 128, is also the solution, because 128 divided by 3 gives the remainder 2, 128 divided by 5 gives the remainder 3, and 128 divided by 7 gives the remainder 2. Plus 105, it is 233, it is also the solution. 338 is a solution, and 433 is a solution. And when we compute the difference, 23 minus 105, which is 105 minus 23, it is 82, so it is minus 82. It is also a solution. And there are infinitely many solutions, and we found all of them. It is 23 plus or minus any number of 105. 2 105, 3 105, and so on and so on. So we have found all the solutions. And what is the Chinese remainder theorem about? Because we haven't said anything about it. This theorem states that all solutions to a system of congruences involving coprime numbers, where the divisors are coprime, can be obtained using the following algorithm. So this is a system of congruences, and let's describe this algorithm. For the congruence system, like this one, it is a system of congruences of any length, where the only condition is that the greatest common divisor, GCD, of all pairs, n1 with n2, n2 with n3, and so on, is always 1. That is, these numbers are coprime. We can write it, that the condition is that GCD n1 and 2 is equal to 1, or we can write that n2 and n3, n1 and n3, and so on. So we can write that GCD ni and nj always equal 1 for any I not equal to j, right? And of course, I and j are between k and 1, right? So this is the only condition, that those moduli must be coprime. So for a system of such congruences where we look for one number, n, in fact infinitely many, but on the beginning we are searching for one number, we have a list of reminders, those, and a list of coprime numbers. We calculate m, which is a product of all moduli numbers. We calculate ni, which is product of n1, n2, and nk, but not including ni. Do you remember that? It was, let's go here. N1 was 35 because it was product of all those moduli not involving 3. N2 was 21 because it was product of all moduli numbers without 5. And the same with N3, which was product of all those numbers, 3 times 5. And we could compute first m as product of all, and then n1 is this product divided by 3. n2 is this product divided by 5, and n3 is this product divided by 7. It is also the way. So we could first compute m and then divide by 3, by 5, by 7, and then have n1, n2, and n3. So for this system of congruences, we compute m, we compute ni, which is m, this product, divided by specific row. For each ni, we find such ai and bi that this equation equals to 1, and it is always simple to do. Then we have a particular solution. The particular solution is this number times this, plus this number times this, and so on. We remember that it was here. 2 times minus 1 times 35, plus 3 times 1 times 21, plus 2 times 1 times 15, right? So we do that. We could write this formula in other way, and s, because it is a sum, right? So this is sum from I equal to 1 to k, ri times bi times ni. So this is the same. And this is a particular solution. So it solves the system. And the general solution, after calculating a specific concrete one, this is why it is S, specific one, it is that specific solution plus some number of m, which was computed here. 1m, 2m, 3m, and so on. T is an integer. And I used t because k was used here. So, knowing the Chinese remainder theorem states that doing always this algorithm, we obtain the global solution. We obtain all the solutions. Knowing that, example of problem. There are 100 soldiers in the unit. Most of them reported for assembly. When the command count off by threes, I hope that's what the commander says. So soldiers say 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. When this command was given, the counting ended with the number 2. When the command count off by fours was given, the counting ended with the number 1. When the command count off by fives was given, the counting ended with the number 4. How many soldiers were present? Can we calculate how many soldiers were there without counting them with just this information? Yes, we can. We have a system of congruences because when there was count off by threes, the counting ended with the number 2, so it was 2 remainder. The same with count by fours, the remainder was 1, counted ended with the number 1, and the same with count by 5, so it is modulo 5, and the remainder was 4. And we need to solve this system of equations, this system of congruences. We compute n1, n2, and n3. It is easy. 4 times 5 is 20, 3 times 5 is 15, 3 times 4 is 12. Then we compute m as product of all those moduli. We write those 3 equations. It is easy to solve. 20, so for 3's it is 7 3's. Then minus 120, it is 1. So we solve those 3 equations easily. Then we compute 2 times minus 1 times 20, 1 times minus 1 times 15, 4 times minus 2 times 12, and add those results. So it is done in 2 lines, let's say, if we say that this is 1 line, this whole. And this is a specific solution, and it is correct. So there were minus 151 soldiers. But how? That doesn't make sense. It makes perfect sense because this is one of the solutions. And all solutions are found using m equals 60. So the solutions are minus 151 plus 60 minus 91 plus 60 minus 31 plus 60 it is 29 plus 60 is 89. Further doesn't make sense because there were actually 100 soldiers, and if most of them showed up at the gathering at the assembly, the correct solution is 89. There were 89 soldiers. And in fact, there are many applications of the Chinese remainder theorem. The last I will talk is the most common used. So, the first one, calculating the size of a set based on the remainders from division by certain numbers. We know that, we saw that twice. So, for example, calculating how many soldiers there were in order, or we have a chocolate bar, we divided it among 5 people and there were 3 pieces left. Then we took some away and tried dividing again because someone else showed up, for example, and among 6 people there were 5 pieces left. Then again someone came and among 7 people there were 4 pieces left. From these 3 pieces of information, we can figure out how many pieces there are, pieces of chocolate. This makes sense with large numbers, like when we have a forest, perfectly arranged, right? And to count the trees, you can try to divide them into 3 rows, 2 columns, 5 or some groups, and always having those reminders, sometimes positive, sometimes 0. Still, given those reminders, we can determine how many trees there are in the forest with a certain step, like plus 80, and so on. But that is usually sufficient. In cryptography, in RSA encryption, the Chinese remainder theorem is used. You can see how I added the link, so you can see how the RSA algorithm is implemented in general. One of the implementations, or the most common implementation, is precisely the Chinese remainder theorem. We can use the Chinese remainder theorem for large numerical calculations, meaning when we have a large number of additions, subtractions, multiplications, possibly divisions, but not by modulo numbers. The calculations are enormous. For example, numbers with 1,000,000 digits. We can break these calculations down to perform them modulo certain prime numbers. We can invent 10 prime numbers and perform all calculations modulo these 10 prime numbers. This will be, for example, 3-digit results. So everything is very simple. Then if you want to get back the result as if we calculated on huge numbers, we just multiply the results. This is a great way to solve difficult problems where there are huge numbers, not calculating on those huge numbers, but on smaller ones, modulo prime numbers. Because prime numbers are always co-prime numbers. And then we combine results. This is very often used. Also, the Chinese remainder theorem is related to Lagrange interpolation and improves in discrete mathematics, and this is probably the most commonly known application for me. Many theorems about natural numbers, especially about divisibility by certain natural numbers, can be reduced to divisibility by certain prime numbers, giving that natural number in products, because every natural number is either prime or a product of prime numbers. And after combining the result, we solve the problem as if we divided by that original theorem. I added links so you can review Lagrange interpolation with the Chinese remainder theorem. It is here on blog on some guy at Art of Problems Solving. I do not want to try to read this nickname. This is connection with Chinese remainder theorem and Lagrange interpolation. And what example of a proof? For example, proofs of quadratic reciprocity. There is information that there is one proof that uses double counting. So we count something in one way, and then we count it in different way using Chinese remainder theorem. And if we computed both ways correctly, then those sums are equal. And in that way, it can be proved that some formulas are equal. In fact, we have seen it in our first chapter, I guess, when we used Inclusion-Exclusion Principle and some other way using just a multiplication rule. We have seen something similar with Stirling numbers and certain Inclusion-Exclusion Principle that are always equal for some problems, and that way the formulas can be given. And this is roughly how this type of proof is used. So there are many applications of the Chinese remainder theorem, and above all, it is interesting. And okay, that's what I wanted to show in this course. In the last lesson, I will tell you where you can go from here. See you there. Hello, I hope you want more, that everything was interesting and that you would like to gain even more knowledge, because there is more. There is more than one person can ever acquire. This should not be frightening, but fascinating. Let's talk about applications of the knowledge gained in this course and also where you can go further. You can go into graph theory. Actually, discrete mathematics courses are often courses in graph theory. Here are many topics like graph coloring, minimum spanning trees, Prim's algorithm, and Kruskal's algorithm, many more. Spanning trees and tree searches are also very close to programming. Many discoveries in graph theory implicate to solving programming problems. I have worked with graph theory. It is very interesting, and I could basically record a whole course on it, so you can request that from me in the comments. Generating functions are also very interesting. Without going into what they are and more what they are for, generating functions allow us to solve recursive formulas without using recursion. An example is Fibonacci numbers. You can also delve into interesting sets of numbers like Catalan numbers. If you feel you can't solve all combinatorial problems, at least up to university level problems, maybe because we have not yet talked about Catalan numbers, which also count sizes of certain sets, just like Bell numbers or Stirling numbers. Knowing Catalan numbers comes in handy. Diophantine equations. That is, equations where we seek integer solutions. At the end, we saw some examples of Diophantine equations in connection with the Chinese remainder theorem, because a1, b1, a2, b2, etc. were sought only in integers. If we allowed non-integers, any a1, a2 would have solutions, but we specifically sought integer solutions. And such solving equations looking only for integer or natural number solutions are Diophantine equations. Many Diophantine equations still do not have known solutions, and we do not know how to solve them. So it is really an opportunity to solve them. It is an open field for research. You can go into probability theory, including cumulants or statistics that include, for example, cumulants. Cumulants are concepts that the intersection of statistics and probability theory, which often overlap, just like combinatorics does. Classic probability theory is about counting favorable outcomes over the total possibilities, like we saw in this course, but you can move to full probability theory, which deals also with continuous variables, not just discrete expressions. Integer programming or 0-1 linear programming is not related to computer programming, not so much. These are mathematical topics where we look for integer solutions in systems of linear equations. 0-1 programming relates more to decision variables, but you need to study and read about it too. Close to what we did in this course, you can read about certain kinds of prime numbers. There is still the question whether there are infinitely many twin primes. There are Mersenne primes, Germain primes. There is also Goldbach conjecture or hypothesis, which we mentioned. So many topics involving certain prime numbers exist. Huffman coding, related to probability and binarities, is an example of lossless compression. If you want to understand data compression, starting with Huffman coding is a good idea. Error correction code, like BCH codes, is a whole field, a whole science. Graph neural networks, generally neural networks, are pure discrete mathematics. Someone might say linear algebra more so. Linear algebra is also part of discrete math, at least some parts dealing with integer solutions or rational numbers, which relates to integer programming or Diophantine equations. Information theory is also a whole science. There are many such sciences related to or part of discrete mathematics. Game theory, theory of computation, number theory, finite difference, and much, much more. No, I haven't dealt with all these topics, because no one can master everything. There is no person who worked on all of them. Euler worked on many of these topics extensively. I personally am closely related to number theory, numerical methods, graph theory, generating functions. I know Catalan numbers too. Those are fields that I understand, and I could record a course for that. So these are things I could explain more. From graph theory, as I said, one could make a whole course without exhausting the topic. So I encourage you to explore some topics from all these fields and to like mathematics, because when you dive into one of these fields, it's hard to get out. You forget to eat or go to sleep. It can be a little dangerous, in quotes. I truly encourage you to develop yourself. See ya, and thank you for watching.